Infrastructure. This is the Critical Decentralization Cluster. We have been here for the past couple of days. I suspect many of you have heard us, seen us. You know, we have a bit of a reputation as the bad boys of C3. So it's good that you guys have come to kind of be a part of that. We've got some great assemblies that are a part of us this year. If you go to decentral.community, I understand that with this Wi-Fi you probably can't, but maybe you can, and you would fare better than us. You go to decentral.community to see all of the assemblies that we have going on here, as well as all of the talks. We've got to schedule all of the talks that are going to be taking place today and tomorrow. There is currently a workshop that is going to be going on over here in our workshop area, which we don't have signed because we're losers. But there's a workshop area over there where there is kind of a discussion about outreach of privacy and how to frame things. So if that interests you, you can see Scott over here for his workshop going on over there. We are going to get started ASAP with our first talk about Almonit and decentralized websites. But there's a tiny issue we're fixing in that he sent us a video for ants, and so then when we blow it up on this screen, it's 4 pixels big. So he's getting it. He's trying to fix that so we can actually see the things that he wants us to see. Unless that is what he wants us to see, but he's gonna have to say that for himself. So my name is Diego Salazar. I am the MC of this stage. I work with Monero, and we would like to thank Monero Community and RIAT for all of their hard work in organizing and hosting this for the assemblies that we have, like FOSSAsia, Replicant, and all the others that are over there and slightly less important. We would like to thank everybody for all of their hard work, our volunteers, our video people, our sound people. We had a little bit of a mix-up that went on early this morning, and they were able to get up and going in like 10 to 15 minutes. They're real troopers, and we love them, and we'll buy them pizza at some point. We'll give them a gift card to Starbucks or something. So thank you, everybody. Thank you, Diego. Thank you, me. And thank you, audience, all of you guys for being here. You are the heart and soul. You are the reason why we do what we do. So that's enough thanking people. We've got Nefton up here. He's going to get that GIF size, that ant size GIF finally working here for us. So it's no longer for ants. It can be for mammals. Yeah, okay, it's working. So I'm going to invite our esteemed speaker, who needs no introduction, so I shall not introduce. Please introduce yourself for the audience real fast.
Hi, everybody. I'm Eyal. I'm a mathematician. I did a PhD in mathematics from Berlin. I do consulting, I do freelancing, and I do open source projects. I'm doing BISC since a few years now, but today I'm going to speak about Almonit and decentralized websites, which is quite new.
Okay, yeah, I need the microphone back just so I can say I'm leaving the stage, because if I was to leave the stage while he was talking, it would be kind of weird and awkward and stuff. So I am now leaving the stage. Let's give a great big hand. Not for me, guys, for him.
Thank you, Diego, who already thanked himself, but nevertheless. Actually, I was about to begin with introducing myself, but this happened. So let's begin with a project, right? How do you pass it here? Oh, yeah, right. Good. Almonit. Almonit is a new project. We began it about half a year ago. I don't know if you haven't began like a new open source community project, but when you begin, you're like aiming for the stars. And that's like why our first slogan was decentralizing the web. And when you see this, you think two things. One, you're like, what? Is it 2017? And second, you say, hey, ain't the web already decentralized? And yes, the web was designed in decentralized way, and it began decentralized, but I think that it didn't scale so well and still being decentralized. For example, DNS is supposed to be decentralized, but we are about to sell the dog.org domain to a third party, which is a commercial company, which we don't know what they will do with it. Email is supposed to be decentralized. I mean, it is a decentralized architecture. It's like a Fediverse. But everybody uses Gmail. I have my own email domain, and my emails often go to a spam folder, or sometimes they are just rejected. which is somehow okay for me because my professional hat is the crazy guy who is into privacy and decentralization, and people hire me because of it. But my lawyer had a private domain, and when her email started to go to spam folder, she had to switch to something which is backed by Google because she couldn't afford losing customers over that. It doesn't seem professional. So the web was decentralized. It's still quite decentralized, but there is a decentralization element in that. The other issue with this slogan, decentralize the web, is that it's very vague, doesn't really say what we do. And in the last 6 months, what we did was de-websites tools. De-websites is how we call decentralized websites. And what I mean by de-websites tools is, I'm going to show you a movie. Yeah, this one. Okay, I hope it's good enough. It's not so great. It's not so great quality. This is a record of what we are going to publish in 2 weeks. It's a search engine. I mean, you saw search engines in your life. Nowadays, they all look the same. The nice thing about this search engine is that it's a decentralized search engine, which is a decentralized website for decentralized websites. It's a bit long. But what you should really remember is that you can use it to find which decentralized websites exist, and it doesn't run on our server. So it's run like in a decentralized P2P network, which means it's completely private or as private as the P2P network is. And it's not really censorable because try to DDoS IPFS, it's quite, or even Zilla and lion and fox relates. So now we got a lion, a fox, and a lion, and together we got a jungle, which is cool because it's also kind of our statement. We want the internet to be like a jungle. There are entities who want it nowadays to be like a field, very organized, very planned, sterile maybe, something that like is being decided by the person who plans the field and not the people who live in the field. And we want to be like a jungle, which is slightly more chaotic, but also more rich, more fertile. And you know, in the jungle you have lions grow, in the field you have frogs. So we go for the jungle thing. It also, I like to read, so I try like in every talk that I give to at least mention one book. This book is from the 90s, the end of the 90s. It's Sing Like a State by James C. Scott. He speaks about and mostly against high modernism, which is how he called the states that were formed in the 20th century, which were trying to control and plan the lives of the citizens as much as possible. It's very thought intriguing. I don't agree with much of the stuff that he writes, but this goes for every book that I read. And what's relevant for us here is that in the first chapters, he speaks about the science of forestry, so designing a forest. Apparently, by the first chapter, it began in Germany in the end of the 18th century. And before that, forests were a bit like a jungle, but not as diverse, but still something rich and chaotic. But for the state, a forest was a place from which you take wood. And they started to design the forest such that it will have mostly wood and not other stuff, and also the kind of wood that they have, and also that you could access it. So the German forest, I do a lot of bicycle trips. The German forest is very organized. It's rows and this. I was never lost in a German forest. I was lost in Ukraine in a forest for half a day. In a German forest, if I get lost, I just have to choose a direction and suck, and after half an hour tops, I'm out. I noticed it like myself with the bicycle trips, and then I saw it in the book. And this, so it was good for the state for the beginning, because they got like really good lumber and a lot of it, and they needed it for construction. It was bad for the farmers, it was bad for people who live near the forest, who live off the forest, for the ecosphere. But what turned out that after a century, in the end of the 19th century, it was also bad for the forest, because suddenly the third generation of woods that they planted didn't grow. It grew up in the first and second generation, because the forest was so fertile, because it was so diverse. And then, again, I'm quoting the book. I didn't really found other good sources for that. A new word entered the German vocabulary, Waldsterben, which was a phenomenon that happened apparently in the end of the 19th century. And I think that this story makes you understand maybe why we want a jungle and not a field and not like something so scienced. Of course, you also don't want the internet to be a complete chaos because we are not living in the Wild West and there is also bad people who want to do bad stuff, but you should govern it around what people do and not tell people what to do around what you want. Then there is another element here, which is the word Almonit. Almonit is in Hebrew. It means anonymous. It's a feminine form of the adjective. So we are into privacy. The other cool thing is that Tel Aviv, I'm from Tel Aviv originally. Tel Aviv has an alley called Almonit Alley. It's Simta Almonit. Simta is alley in Hebrew. It's a very small alley. And if you enter the alley, in the end of the alley, you see a statue of a golden lion. And it's nice when things work out. That's about us, the project, the name, the lion. And now we can speak about the websites. So the websites was not invented by us. We also don't build the website. We make tools for the website. I know the websites from ZeroNet from 2015, which was a project that did decentralized websites. I liked it. It's different than us. It's quite different than us, but the idea is the same. Perhaps it was before. I'm not so sure, to be honest. And to explain what is it in the way that we make it or we refer to, let's first speak explain to me like 5 years old, what is a website? So this is me. This is a picture of me that a friend drew when I was 20. I already didn't have any hair, but I still didn't have a hat. And I want to surf the internet, regular website. So I got a name. I go to a name service, DNS, and I ask the name service, hey, where can I find the content of this name? And the name service gives me back the IP or the address of a server, and I go to the server and I ask for it. So the server gives me the website, and then nowadays begin kind of exchange of me and the server, like back and forth. This is the dynamics of websites, because the websites are not static nowadays. Sometimes there are always other people in the internet. I tend to think that all the people look like me, so it's written not me, but let's assume it's still me. And the other, not me, speaks with the server. The server lets us communicate, and you have more dynamics. And I stress this dynamic because this is the part which is difficult to recreate in the centralized website. The whole talking back and forth with the server being someone that connects people, that remembers states, that lets you know that you speak to one person which is connected to it and not to a million who try to scam you. This is what is difficult to recreate. So now we go to the websites, and it's still me. But now I have a different name. This name is not part of the DNS registry. It's some random name. And instead of going to DNS, I go to a decentralized name service, like Namecon, which was here yesterday, though we actually use ENS, Ethereum name service. It's based on Ethereum. There are two reasons why we use it. I'm not a huge fan of Ethereum, but I'm a huge fan of ENS. I think that they've been doing a very good job of trial and error of how to create a decentralized name service. It's still in alpha, so it's not perfect, but they did a good job. And B, they also did a good job of like business process. So it's supported by some browser. People know of it. And the third thing is that the D website in the current form was just began there. There were about 10 when we began, so it was natural to use it. I'm not going to say exactly how ENS works because that's like another topic for another lecture, but what is important for us, standard things, it's that you can buy there a name. The name points to some kind of value, like IP or something else. The purchase process is automatic and it's irreversible. So now you are away from the whole DNS thing, hey, my name can be taken, which happens once in a while, or the price can go up, etc., etc. It's predictable. And it is private as much as Ethereum is private. And I know that there are Monero people here, and I love Monero, who will tell me Ethereum is completely not private. But let's say it's a different model of privacy than buying with a DNS. At least I don't have to use my credit card and do KYC and this kind of stuff and give my address. The non-standard thing that it gives me is that one name can point to many values. So you can point it to a Monero wallet, which actually I think some people even do, or to Ethereum wallet, or to IP, or some decentralized storage. It has a complex ownership model. So now it's not like one person owns a name. You can have a multi-sig owning a name. You can do something that changes with time. Like today, I own the name, but in 1 year, it will automatically switch to someone else. And it creates some kind of interest in new stuff that you can do with it. And it also has the automation of ownership, which connects, of course, to number 2. So I go to ENS. I get from them something, and what I get is an address in decentralized storage or a file sharing peer-to-peer network of where the website is. We use IPFS for that because IPFS, again, it's a topic for a whole lecture, but it really fits this decentralized website thing. There are people who use Swarm. I think that there are also people who use DAT, which is another decentralized storage or file sharing peer-to-peer network. IPFS is definitely the most common one. IPFS, the standard thing where it's file sharing. So this we all know what it is. And the less standard thing is that names are hashes of content. So you cannot now copy my website and give it a different name because it will be a different hash. It's really easy linking between different repositories of IPFS, between different files. And this is important for website. You can link from one to the other really easy. You can link inside. It's so convenient in IPFS. And again, like ENS, they have good infrastructure. So they have libraries, JavaScript libraries and Rust, and they have a whole big ecosphere of people working on it, which makes easier for us to do stuff with it. Because I think one of the problems with ZeroNet was that the ecosphere was not so diverse. And here we are building on infrastructure of ENS and IPFS, which help us just to be more reachable. Why do you need decentralized websites? Well, I think that the first reason is what I call the big 3 lions of decentralization, what you get from almost every peer-to-peer network or decentralization project, which is its censorship resistance. It is super difficult to block IPFS or every other peer-to-peer network which is big enough. It's robust. The same thing goes for DDoS. It's very difficult to take offline. So if you're an activist organization, it can be a really good solution for you. And it's private as far as Ethereum and IPFS are private, which is up to discussion and can also be improved. And we will be happy to actually also check some more private networks to do it in. The non-standard thing is that you can do collective websites. So this comes to this complex ownership of names. You can do a website which is owned by a group, and every person of the group can change it, but then like half of the group can ban someone if he did something or she did something not okay. You can have like a society moderating and managing themselves, which is very nice, and it's really difficult to do with the DNS model. You will have to start to manage access to the server, and still there will be operators. Here it is so easy and natural to do that, and it's one big pro of the D websites that I like. The cons of the websites, and you should always say, of course, what is bad with what you do. It is slower. You know, Google has AMP, which I hate, but it's super fast. D websites are slower. How fast is it really depends, because if it's a huge website, then sometimes from P2P network you can get big files very quickly, but still the connection to the P2P network takes a time. And the privacy, as I said already twice, depends on ENS and IPFS. So it's also something to consider, because sometimes you can just monitor those networks and know what people do. So it is a consideration. Now the question comes, what do we do with those D websites? And the first thing that we do is the search engine. So right now we began with just a directory, like Yahoo-style directory from the 90s, where you have all the websites there, one by one. It worked well when there were 20. Now we are like in the hundreds, so it's a complete chaos. I designed it. I shouldn't be designing stuff, so it's also not so pretty. This one designed another member of the project who is much better than mine, and it's a proper search engine. The great thing about it is it's private, and this is really private because it's really done mostly client-side. I mean, people know that you use, if somebody really monitors the network, maybe they can know that you did a search, but not knowing what you searched. It's decentralized. And the other thing is, of course, it's more difficult to scale. It's great for a few hundred websites. It would work for a few thousands, probably for a few dozens, thousands, which should also be okay, especially using the special IPFS linking options, so we can do very decentralized databases. But if it gets to millions or billions of websites, we have a lot of research to do. There is a field called distributed information retrieval, and there is, I think, a relatively old and known project, even from Germany, if I'm not mistaken, of a distributed search engine called YAYC, if I remember correctly. We have a lot of study from them, and we want to see how we can use IPFS or DAT or Swarm special properties to scale it better and to make it faster. Second thing that we do, and that's the first thing that we published, was a browser extension. Because it's great if you do a D website, you still have to access it somehow. You can use our extension right now mostly to access websites. It works in Firefox, in Chromium-based browsers, and we also want in the future, like in the near future, to have it working on Tor, so you can have dark web there. Our end goal for this is actually to have it more like a decentralization add-on. And the other thing is that you may think that this is temporarily, because if this thing really takes off, let's say in 5 years or whatever, it's a dream, then Firefox and Chrome and Google will just add support for resolving it themselves. You will not need anymore the browser extension. But the thing is that it's very important to know how this thing is being resolved. Because if instead of going to a P2P network, you just took everything from a Google server or from some gateway, then you just added like a centralized bottleneck in between. And our extension, we always say, is the most decentralized add-on for decentralized websites. So we really make an effort to do random choices, so you will not always go for the same path, and one gateway in IPFS on one node, one seed node will not get too much power, and this kind of stuff. And the third thing, which is in planning, in the development, is what we call Almonit build. Name may be changed. And this lets you build decentralized websites, because if you find the topic interesting right now, there are two things that you can do. One, you can talk to us and try to help with infrastructure and the algorithms and stuff like this. But the other thing is you could build a D website, because we need more of those, and we need people experimenting with those. And if you're a web developer, you can experiment. But if you just want one, maybe you want an easy tool for that. With the Almonit build would be like a simple UI that you can build websites. It will be for personal websites, obviously the first thing that we will have, because it's so easy and simple. Blogs or CMS, like content management system, because everybody uses Medium, and I don't use Medium. I don't like Medium, and I would be happy. I have like my WordPress blog, but Medium is easy, and I would be happy to give like as easy but decentralized alternative for that. And e-commerce, if you want to open shops, and I'm in favor of legal shops, by the way. State of the ecosphere. So we've been doing it for half a year. When we started, there were, pretty sure, I counted there 13 websites, 3 of them were ours, so 10 besides us. And now there are like over 100. And the thing that people do websites on is, first thing of all, personal website. You know, I love developers. They do sometimes boring stuff, sometimes beautiful stuff, sometimes strange stuff. This Stripe bits here is like a shell website where you have to actually walk to see what's there, and it's really cool. There are many of those. The other thing which is there a lot of is blockchain projects, for very obvious reasons. One of them, I think, Blockchain Router, has only a D website. I couldn't find the regular website, which is cool. And it's a beautiful website. So if you actually download the add-on afterwards, the extension, and look for websites, check out their website. It's really beautiful. And then there are already people who try to commercialize it or to monetize it. I give you 4 examples. The first one, which for me was the most obvious, is decentralized exchanges. Because decentralized exchanges always have an issue of, decentralized exchange is not supposed to have an operator. But if you have a website, then you operate the website, and it looks like, and it is literally operating. BISC, the one that I did, that's why we didn't have a website. We are a software, and the software is supposed to be updated from the P2P network, but people like software less and less. So lots of decentralized exchanges have been moving to D websites. All of them seems to be in experimental stage, though it seems that you can still use it. I didn't try myself. Other thing is e-commerce, and this is mostly selling merchandise, but you know, that's what the internet is for, merchandise. Then gambling, only one, but it will come, I guess. It's also one of the first things that you do in anything. And this one, who is stacking sats, is actually selling subdomains of a decentralized domain, because Nick Johnson from ENS wrote kind of a repository for it for GitHub. It was cloned a few times, and then people were selling subdomains, and other people were buying that, which is nice, I mean, cool. And then, of course, I guess people here know what is Rule 34, meaning what if you do something in the internet, people will use it for porn. So people have been using it for porn, but it's censored. And when I say porn, in this case, this is like the most softcore of the softcore that existing. It's a hentai drawing of stuff. So it's light. It's like Rule 34 quotation marks. Yes, there are already some browsers that support it. Of course, the alternative one, Opera, supports it. They were, I think, the first one. Status, which is a DApp browser for the smartphone, supports it. And they've been doing a very good job with it. Brave have been announced that they are going to support it, but I'm not sure what is up with it. At least in my Brave browser, it's not working yet. And soon, like in a few years, other will come. So we don't really think of Firefox or Google, obviously, yet. That's it. If you want to follow us, go to our Twitter, Go Almonit. We don't tweet that much. What we tweet is like updates on the projects, kind of articles that we write in our blog, and when somebody makes a new decentralized website, because we monitor that, we let people know if there's a new interesting decentralized website. You can write us for any good reason in the world. You know, we are sitting bored near the computer waiting for emails, so we are always happy for those. We also have a D website, almonit.eth, and there is a blog in blog.almonit.eth. Or if you don't feel like going to a D website because you need right now to either have Opera or install an extension for that, you can go to our boring website, almonit.club, which is a complete clone of it. Thank you very much. This would be all.
Questions?
Oh yeah, so I will be happy to answer any questions if anyone has some. So there is one gentleman there, but I can hardly see you. I apologize.
First of all, thank you for the talk. It was quite interesting, and have a good luck with Almonit.
Thank you.
One question. So obviously IPFS is like the best at the time for the storage, but isn't ENS is kind of not that good solution in future-proof? I mean, because it's based on Ethereum anyway, and it's decentralized, but it is locked to Ethereum of sorts. Like, is it really a good solution, or are there any alternatives at all? Like,
it's a good question. I would say that the ENS people themselves don't think that what they have now is the final version, and now what they have is probably not a great solution. First thing of all, because what they have now is, I mean, you can they can change everything using like signatures of 7 people. So it's not the final version. They also have another issue which scares me a bit, which is squatting, which is, I mean, it was a problem with DNS. It will be a bigger problem with ENS, and it is tethered to Ethereum, which Ethereum itself has having changes going to Ethereum 2.0, and you don't know what will happen in this sphere. That said, I like ENS because it is the best naming system that I saw. Namecoin is great. I don't know it that much to really compare completely, but ENS has been doing great jobs, and Nick Johnson, who I think founded it, as far as I know, has been doing a good job, so it's a good reason to use it. We can switch from one ENS version to another, from one domain decentralized name service to another. We can even support a few. So we are not tethered to this. The decentralized search engine can really easily switch to another same system. So I think it's a best solution that we have for now. And I don't know, you know, you have to see how things develop. Other questions? Okay, so since this doesn't seem to be the case, I'm gonna give you back the lovely Diego.
Thank you, Neiman. Let's give him a hand. Namecoin is pretty good. You should consider it. The Namecoin guy is floating around here somewhere. And I disagree about squats. He says squats would be a problem. Everybody should be doing squats. It's a different kind of squat, but you should be squatting. If you want to extend your life, lift weights. Great. We have a thing on the thing. We have a workshop that is going to be coming up. We actually have 2 workshops that are going to be coming up. One of them is from high school math to ZK Snarks. It's a 6-hour workshop. Bring your own lunch. But they just like the name says, they're going to take you all the way from high school math so you can understand ZK Snarks. If you are interested, like how does Zcash work, how does ZK Snarks work, this is the workshop that's going to be for you. It's going to be way back there in the corner. If you see the replicant sign that's hung up, that's going to be over to the left of that. I think that is scheduled to start at 2:30. Look at our schedule, Decentral.community. It's there, I promise. But we've also got another workshop that's going to be starting at 2:10. The NIM workshop with Harry Haplin. Does that 2:10? My goodness, we need to work on this stuff. Yeah, I think it's either 2:10, 2:05, somewhere in that area. In the workshop area over here, Harry gave us a talk yesterday about NIM. So if that interests you and you want to kind of get a hands-on feel for that, that is going to be going on over here as well. So coming up next, we got Jan, who's going to be talking with us about WebAuthn. He was just here. We're going to take a teeny tiny break to get him set up. It's not going to take very, very long. But yes, that is coming up. That is coming up right after I leave. Bye-bye. For his workshop. As well, having a quick PDF issue. If any of you guys have used PDFs ever, you know, that normally doesn't happen. I don't know. Maybe it does. Maybe you guys are better than me. So in the meantime, who has a joke? Does anybody have a joke that they want to share? A nerdy joke is fine. We're at C3. It's okay if you don't know any others. No? Nothing from the audience? Look at you guys. You're just sitting there expectantly waiting for a talk of some kind. I'm just gonna plug C3. I don't know if you've heard about this conference. Highly recommended. I really recommend everybody goes. It happens once a year. It's the biggest nerd conference in Europe. Really, really cool. Check it out. You can look it up at c3.c3.c3. So that's looks. I think we're ready to go. No. The clicker's not working. See, the cool thing about technology, because this is like a technology hacker conference, is that it never works. And in regular conferences, you have to explain this to people. We're sorry. But I don't think we have to explain this to hackers because you guys know technology never works. So you guys are more than willing to give us a little bit more grace. Because if you start getting judgmental, we say, hey, remember that time when you tried to do something and it never worked? I will keep stalling. You know what? Can the camera follow me down here? Let's have a heart-to-heart conversation. See, now I'm on your level. I'm not talking down to you. We're talking with each other. Let's have a conversation about conversations. We don't conversate enough. We're on our phones too much. That's what they say. But our phones facilitate conversations because we talk with people with our phones. So which is it? Are phones destroying our social interactions, or are they facilitating them? Or is it a combination of the two? Let's poll the audience. Who thinks phones are destroying our intimacy with the world around us and people? Okay, we have one, we have two, okay. Who thinks that phones facilitate these things? We have, okay, the vast majority, but you guys are nerds, so your opinions don't count. See, if we talk about people with actual friends, I'm just kidding. Don't be offended. Don't leave. Oh no, they're starting to spill out the back. Boo, they say, boo, Diego. No, but it's something that's becoming a big discussion, like our relationship with technology. But you didn't come here for me. You came here for this presentation. You're like, Diego, get off the stage, and I'm more than happy to. So I'm going to hand this off to Jan, who's going to take us through WebAuthn. WebAuthn, guys, there should be vowels there somewhere, but I'm not going to ask you to justify that. So go ahead and why don't you take us through this? Let's give him a hand.
All right. Thank you. So I'm going to talk about passwords and the new web authentication thing. But first of all, a short introduction to myself. My name is Jan. I'm a founder of NitroKey. What we do is open source hardware made in Germany. We basically produce and develop USB keys for data encryption, cryptographic key usages like HSMs, and of course two-factor authentication and passwordless authentication, which I'm going to talk about today. But first of all, a picture how it looks. What we do is devices, so that you know what we are talking about. USB devices, USB keys like this, but not ordinary thumb drives. So why to use passwords? I guess everybody who has ever written any application or web service has introduced some, at least if you have some user management or anything like that, some access control, you have introduced some passwords. They are easy to implement. Everybody knows how they work. They work out of the box on any platform on where your application or your web service is supported. So it's a super easy thing. So why not to use them? There are a few reasons. We all are aware that they are inherently insecure, or at least it's hard to make them secure. So it's easy to use them insecurely. Say you share an easy to remember password among a couple of services, but it's insecure. So what you are going to do to have it more secure is to have a longer passphrase individually for each service, which you can't remember then anymore if you use more, say, than 10 services. So you need some way of password manager or something like this. So it can become very complicated quickly. It doesn't scale, and you don't have any form of phishing protection, which is a threat we can address by more modern methods like WebAuthn. I'm going to talk about soon. And one thing I want to highlight is convenience. So usually when we talk about security, making things more secure, it comes with a trade-off of usability. So often it's like, do you want to have something secure or easy to use? And I think here, now we are at a point, and in 2019, we are at a stage where we can have a solution which is more secure and more easy to use than before. And I think this has in the long term, can be a very effective, very huge leverage. So after, say, kind of after passwords or an add-on to passwords are one-time passwords, which you can use with Google Authenticator. This is one of the most popular forms of using one-time passwords. It's supported by many of the large websites by today. You can have clients on every platform. You can have USB security keys to use one-time passwords as well. The setup is, or the architecture is based on a shared secret among the client and the server, so it's not super modern. Also, this standard goes back, say, 15 years ago about. And how it works is basically it's a hash which is calculated over the time and this shared secret, so that then once a client logs in to a server, the client side can do the calculation and the server can do the same and do the comparison. So it's well, not so super easy to use. It's good and easy enough for us to use it, I believe, but maybe not for every average computer user, say my mom, so to speak, because you usually need some way of additional software, as I said, like Google Authenticator or some other things. And you don't have any form of phishing protection. Then there was, and there is, FIDO Universal Second Factor, better known as FIDO U2F. This comes as a second factor authentication in addition to your password. So services and web applications can decide to require this mechanism in addition to your username and password. It's a kind of more modern one-time passwords because it's more easier to use. It has support being built in by most modern web browsers. It has a more modern cryptographic architecture where you don't have a shared secret among client and server, but more public key cryptography, which you usually would do as of today. And nice benefit is the phishing protection. I will explain shortly how this works. And another thing which many people are not aware of is some form of privacy protection. So what has been designed in the specification is that a specific website is not able to track you as a user among multiple websites because there's not a single identity, but for each website there's an individual cryptographic key or cryptographic identity on the client side, and therefore it can't be tracked among multiple websites. Yeah. Usually it's not demanded by the specification, but most implementations I'm aware of do it this way, is that there is not a fixed amount of storages available on the client side, but there's a mechanism to derive those keys dynamically. When I talk about this key, I mean the client-specific key is derived dynamically on the context. Therefore, you can use it with an unlimited amount of websites or accounts. As I said, it is supported by most browsers, but it's not, or so far it has been a kind of proprietary extension to browsers, which has been changed with the WebAuthn. But looking backward, it has been kind of proprietary. Therefore, not so many websites supported it this way. The usability was good still, though, because it was supported by browsers. And the browser was aware of this mechanism and then had specific windows and queries to the user, like connect now your FIDO U2F device and press a button and things like that. So you didn't have to use any additional software. How it works, I'm not going too much into detail here, though even I think you can't read it very well, but just on a high level, you have this high level flow. You will see over all the other FIDO mechanisms I'm going to talk about. So on the right side, you see the server. Do I have a pointer here, by the way? Here's a server, which sends, and we have a web browser, and we have a FIDO device, like a FIDO dongle, perhaps a USB dongle or Bluetooth dongle. So the server sends here we are in the registration process. So this is the initial registration of a user who wants to add his FIDO U2F device to his account. It's not the login procedure yet. So what the server does, it sends basically a challenge and its own ID. It's called origin, which you can think of kind of as the domain name. It sends this to the browser. The browser verifies this origin or app ID, which is effectively the phishing protection. So if the app ID does not match to the domain of the particular website, the browser would reject the request. So it verifies that the domain matches the app ID. Then this request is sent over to the USB dongle, the FIDO dongle. The user confirmation means the user usually has to press or touch the device, which indicates he wants to confirm this request. He wants to do the registration. What the device then does is it generates or derives a website and account-specific cryptographic key pair. It's elliptic curve key pair, and do a cryptographic signature over a couple of parameters and sends it back. It sends back a public key, a key handle, the signature, also attestation key, so that the server can do verification, that the response matches the request, and register now this key handle to the user's account. And then in login, during the login or authentication flow, it's pretty similar. The server sends a challenge and its app ID and also the key handle. He has been registered with the user account previously and during the registration. And then the flow is pretty much the same: user confirmation, retrieval or derivation of the key, and a signature, and this is sent back so that the server can do the verification. Again, it sees the response, matches the request, it matches also a counter, and the user is logged in. So relatively simple. And now is FIDO2. That's a pretty new standard. It has been, I think version 1.0 has been released this year. What you can think of is this FIDO U2F. So this is two-factor authentication. Again, this is used to be in addition to username and password. And this FIDO2 now is the same as FIDO U2F, but also a couple of more things, most namely the passwordless authentication. And this can become very interesting because with this passwordless authentication, you as a web developer or app developer can replace username and password. Or first of all, you can replace passwords so that a user does not need to remember any specific password for his account or for your website. What he usually would remember or would require to remember is a device-specific PIN. And this can, so device, when I talk about device, I'm talking about a FIDO device. And this device-specific PIN can be, or is unique for the device and has nothing to do with a specific website. So a user only need to remember one PIN and not hundreds of passwords anymore. And it can be short thing, it doesn't need to be a long passphrase. Username-less authentication is very similar to the passwordless authentication, with a difference that, so to speak, the username is also provided by the server, so that the user does not have to even enter his username. It only needs to deal with this FIDO device to log in, and the username is then provided to the server. It's possible to use it in theory with different types of devices. USB dongle is one type, a TPM or some biometric built-in or external device or other options within this FIDO2 standard. And it's primarily written for the web, but not necessarily exclusively for the web, so it can be also used for apps or local native applications. Usability is great. Going to talk about this later. Acceptance, as of now, is quite poor. I'm aware of Microsoft, who has the most acceptance on, first of all, on Microsoft Web Services, and second, on Windows 10 local machine login. So it's very neat because people don't need to remember password to access a local computer anymore, but can log in with a FIDO device or FIDO2 device. And beside of Microsoft, I'm not aware of any website or service which is supported by now. But I think this will change very soon. Now, what is WebAuthn or web authentication? WebAuthn is short. This diagram should explain it a little bit better. When we have the server and the browser, the web authentication specification defines the API on the browser side, which you as a website developer would use. Behind this WebAuthn are this FIDO U2F or FIDO2, which were renamed in CTAP 1 and CTAP 2. And that's a protocol between the browser and say, the USB dongle or built-in TPM functionality of the laptop. So WebAuthn is kind of the keyword to address all of this, and it's not just specified in 2019 this year. It's also implemented by all large web browsers. Even Safari, the latest version, implemented it just a few weeks ago or something like that, a few months. How it works. First of all, I have to check the time. I'm not going to talk about this in very detail, but you see from the bird view, it's a very similar flow to the FIDO2F flow, with of course, a few changes. First of all, the terminology has been changed. Now we are not talking about a server anymore, but a relying party. Can be also a local app, perhaps. Also, the USB dongle or other implementation is called authenticator. The client is usually the web browser. Then the request has more options. So the website to some certain high security areas. Also, perhaps you want to have a second login, perhaps you want to have some biometric verification or something like this. So the web server has the possibility to request whatever he wants, even after the initial login, through this parameterization. So for the registration, again, this is registration means when a user wants to pair a FIDO2 device with his user account. Here again, a couple of parameters. We have kind of phishing protection by the browser who verifies the relying party against the origin. We have now here a hash is calculated, which is more detail. And then we have a user confirmation or verification. This sounds pretty much the same, but in practice can be different things. A confirmation usually means there has to be a confirmation, like pressing a button that the user really wants to approve and wants to execute this operation. Usually this login operation, or in this case a registration operation. But the user verification is, under WebAuthn, describes something different. It's more like verifying that the user is really the user he claims to be. And depending on the FIDO2 device, there are different mechanisms to ensure the verification. It can be entering the device PIN I mentioned earlier. It can be using some biometrics like a fingerprint to verify that the user is really the user. Say the owner of the FIDO2 device. Then again, a cryptographic key pair is generated, a signature is calculated, and the response is being sent back to the relying party who does the verification. And then the actual login procedure or authentication looks again similar. Here, first and second factor refers to FIDO2F mechanism, and the first factor refers to passwordless authentication. So actually it's not just a first factor, like a password is more a first and second factor. But the flow is very much similar. The difference are only the parameters. This is why it's here combined on a single slide. The relying party sends a challenge, a name of the relying party itself. The browser again does a phishing protection by verifying the relying party against the origin. Perhaps some credentials or the parameter of whether user verification is required or not is transferred. And again, the authenticator does whatever is required to log in, say requiring just press of the button or some PIN. And then the response is sent back to the relying party who does a verification against the key pair which has been registered with the user account in the previous step, in the registration step. So for username-less authentication, the main difference is that here on the client side, think of it as a web browser. The web browser it would show to the user a kind of user interface, a kind of window where the user can select the identity he wants to use to log into this particular website. So yes, there is a username involved, but it's not involved on the website anymore. It's only client side. So it's a native window of the browser. I think this feature by now is only supported by Google Chrome. I'm not sure about this. So this is kind of more advanced features of WebAuthn. Earlier I said all major browsers do support WebAuthn, which is true, but I think those more advanced features are not supported by all. I hope this is going to change. Then the user selects which ID he wants to use to log into this particular website, and then the similar flow is executed as previously. Here in the response, the web servers or the relying party also gets the username, of course. The username the user has chosen here. Now, what to use? This is kind of summary slide. Pretty much my last or second last slide, so that we may have a minute for questions, perhaps. I think password authentication is for simple projects, for projects without any security focus. I think there will be a shift among the ecosystem that more and more websites and apps are moving to one way or the other of this WebAuthn authentication mechanism, so that the acceptance or what user actually demand from websites is going to shift towards a WebAuthn-based authentication for security critical or on users' view for their important websites. So OTP I won't recommend to implement anymore. If it's there, it may be good, it may be sufficient, but I won't recommend you guys to implement it in any new projects anymore. But instead of OTP, use either WebAuthn with second factor, so FIDO-U2F, or use what I described as passwordless authentication or even username-less authentication. However, this requires more implementation effort. There are a couple of libraries available, say at GitHub or somewhere else in the internet you can use, depending on your programming language, but there are not so many. So it's still some pioneering if you're going to implement it. And also if you're looking at this passwordless authentication, make sure that the web browsers your user or customers use really support this. So here we have a couple of references. The first one can be very helpful for OTP, but also for WebAuthn. It provides an overview of popular and non-popular of a couple of hundred websites, and provides an overview which type of mechanism they are going to support. With mechanism, I mean either OTP or WebAuthn/FIDO mechanism. So this can be a good starting point if you want to decide as a user which secure authentication mechanism you may want to use. Then the other is more for developers who want to look into the specification itself, or maybe prior to looking into the specification, read on this guy here. He has a couple of good introductions, not only the single one here, but also some other follow-up blog posts about WebAuthn. Yeah, that's it from my side. Do we have time for questions? I think this means we do have time for questions. Okay, any questions? I think you were first.
Hi, thank you for your speak. How to validate the origin against the domain name? How is this validism realized?
This is implemented by the browser, so you as a developer don't, so to speak, don't need to care about it. Yes, you do need to understand how the validation is done, say if the subdomain is considered or not, those kind of things you do need to know, but you don't need to implement anything around this. This comes out of the box. One thing which is required is HTTPS, so FIDO and WebAuthn won't work with plain HTTP. And for the subdomain things, I think there's some better explanation visually where you can, which you can find there. There are some tables with examples. This is more easy to understand than me here in the open space. Follow the references, and you will find it.
So thank you for the nice talk. Do you know an overview about tokens which support FIDO2? As there, I searched a bit, and it was a big chaos of sources and information, which and it seems that some is not up to date, some sources are not up to date, and it's hard to find which features are supported by which FIDO2 keys.
So the information of which device supports FIDO2 in general is available here. First of all, our own NitroKey FIDO2 device is available. Then also to name SoloKey, which is kind of related other open source project too. YubiKey as a big competitor as well. And also a couple of others. I think the next question was here.
I'm next. I recently implemented WebAuthn as a proof of concept for my company, and I was very surprised that Safari on macOS was able to bypass the PIN required for passwordless login. Is the PIN implemented by hardware or by the browser?
That's by the browser. So the browser should prompt the user to enter the PIN, yeah, in the window.
I added the YubiKey via Chrome with a PIN required. And then I used Safari, and Safari could just access the key without a PIN and just use the first one. I've added multiple, but could not select which one, and I was very surprised by that.
Sounds like a bug or weird implementation in Safari, but in the end, the relying party, the server, should verify that the response also meets the criteria he's requesting. So there it should fail eventually and not bypass any legitimate authentication.
The response from the browser to the server includes if a PIN was entered?
So say this here. Yeah, I'm pretty sure yes, this information is provided in the response so that the server can verify this.
Yeah.
So the server must not trust any middleman browser, anything like that. No.
Yeah, I think then Safari is bugged.
Talking about business solutions, is this fully supported in a business environment where the user is on a thin client or something, a small device, then remotes into a server, for example, that is the FIDO2 or similar solutions are passed through, and is there some limitations?
So business environment, you're talking about Windows?
For example.
So I know that for Windows, earlier I mentioned the login to the local Windows machine. This, for example, requires an Azure Active Directory. It doesn't work yet with the local Active Directory. So that's a big limitation. I expect Microsoft to add, sooner or later, to add this feature also to local Active Directory. For other like environments, business environments, I'm not aware of any out-of-the-box implementation or support of this.
My question was less than the authentication against the Windows or the remote server, but then passing it through into the remote session. So I plug in my FIDO2 dongle and at my station, and on the server I can use it in a browser window, for example.
So you would need a way to pass through the USB device to the client session.
So it's just a normal USB device, not like special funky like smart card or something?
That's right. It's a very ordinary USB device. It goes as USB HID class, human interface device, where also mouse or mice and keyboards are assigned to this USB class. So that's a very default USB class.
Okay, thank you.
So if you are talking about a VM or thin client, somehow you need to pass through the USB device, but don't need any specific driver for FIDO. Last question? You? Okay. Okay. I think time is over. Maybe you can find me around here. Okay. Thank you.
Yeah, let's give him a great big hand. Sorry to cut you off, Jan. We do have another talk that's coming up, and we hit the time for this one. He's going to be off stage over here. If you would like to speak with him and ask the questions, you can ask him all of the questions. That's totally okay. We're going to get it set up for our next talk, which is by Christoph. He's going to be talking with us about user experience in something. What user experience are you talking about, man? Crypto UX design, so cryptocurrency user experience design. If that's something that interests you, by all means stay here. Workshops. We have workshops. Harry, who gave us a talk about NIM yesterday, is over in the workshop area over there doing a workshop about NIM. We also got a FOSS Asia workshop going on over here that just started a few minutes ago. That one is... create personal bots and web smart devices for Suzy AI. So earlier today we had a brief presentation about Suzy AI. If that's something that interests you, go visit the workshop over here in FOSS Asia. Once again, Harry giving a workshop over here with NIM. I also misspoke. It happened. They give me one mistake a day, and after that, I'm going to be thrown into the fires of hell. So everything I say from now on will be correct. The ZK Snarks math workshop, High School to ZK Snarks, is going to be taking place at 4, and that's going to be taking place at the very farthest corner of this cluster, over here to the left of the replicant sign, if you are facing the direction that I am facing. So we're going to get Christoph set up here to do this whole crypto UX something or other that he's going to be talking with us about. He is a deep, wonderful personal friend of mine, goes way back. He basically invented all of technology. So he's somebody that you're going to want to listen to. We'll be right back in just a couple minutes. us about cryptography UX design, even though that needs severe overhauls as well. So I'm going to pass this off. We ready over there? Yay? Yeah. Okay, we are set to go. Why don't we give him a great big hand as he talks about this cool little thing.
Hey everyone, can you hear me? Can you hear me all right? This better? Okay, cool. Can I get my slides up here? Hello? Okay, cool. Yeah, here we go. Okay, so crypto UX design. Who here is a designer? Who does some? Okay, awesome. Thanks for being here. There are very few of us. So generally, this talk will be super not technical at all. The main goal of what I do is just make things generally easier and more pleasant to use. Sounds kind of fluffy, but really there's a lot more to it, because usually you look at very specific user flows, like how people use things, how do they think about things, who they are, what they're trying to achieve. Like here's kind of a typical usage life cycle. So everybody, let's say everybody who uses Monero, at some point they don't know what Monero is. They're unaware. Then they find out what it is. Then maybe they get interested. Maybe they try it out for the first time. And maybe they become regular users. So at each point of this cycle, they need different types of information. They have different types of problems. And if you design the whole experience from, let's say, a website or what they see on Reddit to the wallet itself, then there's a much better chance that they can actually make sense of things and can make really good decisions and actually keep their privacy intact, not lose their keys, not lose their money, and all of these things. Pretty much all of my work with cryptocurrencies has been with Monero. And particularly this GUI wallet. Who uses the desktop GUI wallet? Also, some people? And generally, I hadn't done anything in open source. The way I got into it was I heard about cryptocurrencies. I was kind of curious. I didn't know anything. And one evening, I somehow stumbled across the Monero website, and I downloaded the wallet. And this is what I saw, and I had no idea what was going on. I had set up my wallet, I had my seed, and then it told me the daemon is synchronizing, and there are like 1.3 million remaining blocks. I just assumed this would take like 3 minutes, and then it would just be done, and I could just, come back and use this awesome wallet. But turned out it didn't quite work that way. So I was waited like 10 minutes, 15 minutes, and I thought, okay, this is what this wallet looks like. I'll just hop in my design tool and I'll just restyle it, just see what happens. This whole thing took like 10 hours total. I didn't work on it that long, but like until 2 in the morning. And I thought, okay, I'm going to go to bed. What do I do with my design? I'll just post it on Reddit. And I did. This is what it looked like. That was like late 2017. I just thought, okay, cool. I made this anyways. What do you think? And then this guy over here contacted me, DSC, and said, "Hey, I want to implement this." And I thought, "Okay, cool, let's do it." And he has been the biggest help ever in helping me understand all this stuff, help me figure out how to do design and open source and executing everything. So he's been super awesome. And then over the next months, I tried to flesh out the visual styling. So there was a dark theme and the light theme. It's pretty stark, the colors, which I like to think that reflect the, yeah, what's up? The problem I solved with this was, so 2 things. This was as you can see here in the title, it's a restyling, it's not a redesign. So it was basically just to create a solid visual UI style that could be applied everywhere, so things look consistent. There's a nice component set. And I intentionally, because I didn't know what the functionality, how it worked, I just thought I'll keep the functionality the same. And then after fleshing out all of this stuff, created this component set with all the nice little button variations and the card up there that shows how much Monero you have and all this stuff. That's when the next step was to get into more of the actual design work. So, for example, we tackled the onboarding. There's a whole flow. The first time you set up your wallet, there are some very crucial moments, like writing down your seed. Those need to be the explanations need to be very clear. people really need to understand what they're doing and how to do it really well, because there's no reset password if you lose your seed. It just doesn't exist, and that's really unexpected. So we went through, and after the restyling was done, to tackle the functionality and make that easier for people. So this is, for example, the recovery phrase. We added these little numbers. You can, instead of telling people, grab a piece of paper and write it down, which then, everybody takes a Post-it and it forgets it somewhere. There's a template you can print out, and it looks nice, and you can write your seed down. It's easier. So we tackled these things. There was some other work. I saw that the transaction flow involved 6 overlays, and they all looked totally different. So it just made everything a lot more consistent. There were some details in here, like the transaction was created before you could review your transaction. So it just made that, just have to create the transaction, do that processing while you're reviewing your transaction. So you don't have to wait around. You don't have to look at a spinner. So a lot of detail stuff just to make everything just easier, smoother. I skipped that one. I can't. So this is one of the example where, just pick one flow, try to make it easier. There's a merchant page. This is really just kind of an exploration. So if anybody wants to create a really awesome point of sale merchant system in the Monero GUI and wants to develop that, please. DSC is way too busy with so many other things. This was a recent very interesting conversation. There are really split opinions about accounts. Some people think, hey, we should just support 50 accounts out of the box. Other people say, no, nobody uses accounts. One is enough. Other people say, hey, we should kind of think about how people use bank accounts. There's like a savings one. There's a checking or long-term savings, daily expenses, this type of stuff. So. And it's kind of unresolved. That's where we would really need some user testing and some user surveys to figure out how people actually use this thing, because it really changes how you would design it. If we assume people use only 2 accounts, then we can have a big dashboard that just shows them, and you just pick the one you want to use. Question? Sorry? That depends. There are 2 things. How do people generally want to use it? Like, what's their intuition? How do they do their personal financial planning, which is not really a cryptocurrency question. That's just a general, how do people organize things? Then you could attack it from the other perspective. What is a good system that we want to present to people that allows them to, for example, separate their finance for best privacy and protection? Do you want people to use sub-addresses or accounts, or do you want people to, sorry, too much? Okay, cool. A mobile concept that was really just for fun, site exploration. This was some user testing I did in March. Question? Partially, yes and no, because, so this was actual user testing. There's like was an event. There were 7 random people that used the wallet for like 10 minutes each, and I gave them a task. They said, so you paid somebody lunch, they want to pay you back in Monero. So download the wallet, set it up, and find your address. Fairly straightforward. There's actually a lot going on because they move from unaware to aware to interested to first use through all of these steps. And people really struggled, but not with kind of the things you would expect. People struggled finding the download page. The download page itself had like 200 options of what you can download, and the buttons weren't clear. They were kind of underlined, and there was all kinds of stuff going on. The checksums were there, and people were like, what's this? So there were all kinds of surprises in there. And so there's that type of user research, which is just random people, but there's also the type of user research which is paying attention to Reddit and see what people say. So coming up with a concept, putting it on Reddit, gathering feedback, or just seeing what discussions are out there. Like this account discussion, how many accounts do we want? That was really driven by paying attention over time and just seeing what people talk about and then reacting to that. But yeah, there should be a lot more user testing and user research, which I think is just not that common in open source, I think. Like one of the things that came up in user testing, people create their account, they come here. But you created your account, you don't have anything to send. This is the send page. Why do we get to the send page? And it doesn't tell you it's the send page, so people were just stuck. How am I doing time-wise? Okay. So what I just said, this led to a redesign of the download page. So instead of just listing out all the download options, it was about just tell me this is what the wallet looks like. These are the key features. If you want to use it for casual purpose, here are some features. If you're a power user, here are some features. And if you want to use it for business, it's not the best, but there are some features, and here's kind of how you can use them. So focusing on how people want to use it instead of just download options and just generic lists of features. All my designs are, for the other designs out there, I always try to keep them open source also. Open source and design is really tricky. The tools don't really support that. There's no workflow like Git and GitHub have, or like developers have come up with. So I kept sketch files on GitHub for a long time. I recently moved to something else, another tool called Figma, because I talked to them and they're trying to more actively support open source. So they came up with a thing where you can have public files and other people can duplicate them. So all my designs are in this file. You can duplicate it, you can drag components around and just mess with anything you want and then tell me, like, hey, I made something better, put it in there. And there is no process for collaborating yet. It's just very, very slow steps. And I think for once design tools just have never worked that way, and also designers' mentality, they just don't think that way. Because if you open a design tool, you start with a blank canvas and you start drawing lines and placing text. It's just not the same structure that code and code libraries and all these things bring. So it's tricky, but maybe we'll get there long term. That was a fun project. DSC sent me Monero at some point, and he sent me a link to Explorer, like, hey, here's proof of your payment. And I saw a page that looked like a Sudoku puzzle or something. I had no idea what was going on. So I thought, I don't get Explorers. So, because it's just numbers. So I created my own design and developed it, and I changed it around and said, what do you want to do? Like, here's the things you can do with an Explorer. What do you want to do? I want to verify a transaction. Just a lot more straightforward in what people want to do. And the awesome Monero community translated it in 8 different languages, which was super awesome, totally unprompted. So thank you very much for everybody who did that. And if you want to translate more, please feel to do so. And while I learned all this stuff, I thought, like, there's so much UX work that has to be done. There are probably other designers out there. I should just write down all the things that I've learned, and that's what I did. Call it the Crypto UX Handbook, and I try to keep it fairly simple. There are things about how to think about UX design, like the user cycle that I talked about earlier. Basic walkthroughs over how transactions work, how keys work, all these things. And lots of examples, because I tried out probably 100 different wallets, so I took lots of screenshots and put them in there. And it's also completely open for contributions. Anybody who wants to help out, change things. There are probably lots of things I got wrong, so let me know which ones they are. And because I think it would be awesome. Traditionally, in my experience, designers have been kind of protective of their design, but it would be awesome if there was more openness and sharing and collaboration around it. I hope that's, along with making Monero UX really good, that's kind of the second thing that I hope to push forward a little bit. And these are all the places you can find me. And any more? Do we have time for questions? Any questions? Yes, you were first. Yeah, please go ahead.
Is Monero paying you for UX design, or is this your free time?
So the first year and a half or so, I just did it because I wanted to, and I thought Monero has a really cool core both in terms of technology and the people around it. And then I dared to create a CCS, that's what it's called, right? Community proposal. So I said, hey, here's all the stuff that I've done. There's a lot more to do. Here are the things that I would like to achieve. Please donate. And then people were very happy or they donated. I hope they were happy to donate. Thank you to everybody who did. And then I did that work, and then I got that payout. So it was a really smooth experience. It was really awesome. I don't know how common that is in other open source projects, though. You had a question?
Yeah, thank you for sharing your experiences. I just wanted to know, how did you measure your success of the redesign or rethinking of the visual processes of the UX?
That is a really hard question. So I've worked. The funny thing is, while I did a lot of this stuff, I worked with a startup that had an insane amount of data on everything. We did A/B tests, like change this, and 2% more people convert. And then it's like, Monero, we have nothing. We don't want anything. We don't want to collect any data. There's no tracking in Explore Monero too. I have no people, and I wrote that on the About page. I don't know how many people visit. If you want this to be better, you have to tell me, because I don't want to know. And I think that's a really awesome thing about Monero, that there's not this hoarding of data. So my best access is really user testing, showing people, having conversations, but also always putting things on Reddit where the community hangs out, and just be very, very clear. Like I don't just post a design. I'll post a video where I explain my thinking and how I think it could work, what different solutions are, and just try to get people involved in the process, and then hopefully the end result is good. But yeah, that's a hard one. I think we kind of have to go back to basics if we don't want to have all this intrusive tracking. We need to just talk to people, which with Monero is of course harder because people like to be anonymous. So not easy.
One more question. Have you thought about creating use cases and posting them on Reddit and collecting opinions or something like that?
Have not thought about it. It's a good idea. Let's talk about it afterwards.
Because you said UX or design is not really common in open source project, not in all, but in most of them not. Did you find other designers who you could exchange like experiences or insights or stuff like that?
Very few. Diego here is an ultra master here. He knows a lot. There are very few. I found a lot in the Ethereum community for some reason. They have these groups because I think, what is it, consensus? They hired 1,000 people or so. So there are just designers in there and they talk about things. But otherwise very few. I also did a presentation last year. I'm doing another presentation in a month to a UX meetup. And just talking a little bit about kind of the technical side, a little bit about my experiences. And interestingly, most of the questions were about, they were like, what, you get feedback on Reddit? Why would you post your stuff on Reddit? What do people say? Like, how do you make decisions? It wasn't really about the technology or cryptocurrencies or the details of this work. It was just about, like, how do you even work that way? But yeah, and I tried to, but little success so far. Could be me, though. Cool. All good?
Let's give Christoph a hand. Thank you so much for sharing that with us. Up next, we were supposed to have a talk on the Monero hardware wallet. We unfortunately cannot get in touch with the speaker. We don't even know that he is here at C3. We hope he's okay. And so that talk is unfortunately going to be canceled. So we're going to have maybe a 30 to 40 minute break where we have to run some tests for our stream anyway. If you're a designer and you want to talk with Christoph about anything that he's been doing, I also want to talk with Christoph as another designer. I say we make an impromptu UI UX workshop kind of over there. I would love to talk with some of you guys also about some of the things that you're working on. So yes, we do have an ongoing workshop with the Suzy AI thing over here. I'm not sure of the status of Harry's NIM workshop, but maybe you can check to see. Okay, no, they're still going. So if you're interested in NIM, they're over here in this area. So yeah, we'll be back after a break, and everyone have nice lives. this talk in just one moment. We're going to give a second for the stream to catch up. The stream guys are working hard all day, every day. You know, don't ever let anyone tell you that technology has come far. Okay? Like, there's so many problems. Half of the calls on my phone are spam. Half of the users on Twitter are bots. Right? Half of the emails you get are spam. Don't ever let anyone tell you we've come a long way. We've still got a long way to go. Maybe Drew can give us some solutions. Maybe he can't. It's not what his talk is about. Oh, wait. Open source hardware and open source chip design? Yeah. Huh. Okay. So we're talking about something completely different than what was on. Oh, it is the same thing. Okay. So see, when we say fill out your title for your thing, and in our form up there, he put in his title, and then he put in a different title here. Control C, Control V. Don't ever say that technology or people have come far, because we have not. I'm just kidding. So I'm going to hand this over to Drew. Let's give him a great big hand as he talks with us about open source hardware. Big hand, big. There we go.
Hi, I'm Drew Fustini. So this talk is going to be about open source hardware, specifically Linux on open source hardware, which I forgot to write there. Originally I was saying Libre Silicon, but it turns out there's actually a group called Libre Silicon, so I'm going to use the term open source chip design because I don't want it to be confuse people that it's about that group specifically. So I work for a PCB manufacturing service in the U.S., also part of the BeagleBoard.org Foundation. We make small open source hardware Linux computers. And I'm also part of the board of directors for the Open Source Hardware Association, which I'm going to talk about in a bit. So how many people have heard of open source here, like open source software? So probably most of us, at Congress here. So examples of open source software, if you haven't heard of it before, Apache, the web server, Linux, operating open source. Also, the thing underneath it is Linux. LibreOffice, which is like a alternative to Microsoft Office. I use LibreOffice to make these slides. Firefox, the web browser. So I want to, before I talk about open source hardware, I just wanted to go into what is open source in what is open source software. So open source, it refers to something that people can modify and share because its design is publicly accessible. So with software, we're usually talking about source code. And you have source code that anyone can inspect, modify, and enhance. There's also the idea of free software, which is more of a philosophical idea around these 4 essential freedoms, that you can run the program as you wish for any purpose, that you can study how the program works and change it so it does your computing as you wish, and you can redistribute copies so you can help your neighbor, and you can distribute copies of the modified version of the program. So when we're talking about hardware, some people use different terms. I'm going to just use the term open source hardware, and I want that to be inclusive of the idea of free, Libre, and open source. Even though those terms kind of have different philosophies behind them, in the terms of hardware, I'm going to just use the term open source hardware to keep it from getting confusing. Though some of you might know that there's different philosophies behind those terms, but I'm just going to conflate them into one term for to be succinct. So what is open source hardware? So we came up with a definition about 10 years ago at an event called the Open Hardware Summit. A bunch of us got together that were doing hardware at the time and wanted to kind of make a definition for what we meant when we say open hardware or open source hardware. So it's hardware whose design is made publicly available so that anyone can study, modify, distribute, make, and sell that design or hardware based on that design. Also, I should have mentioned before, there's a lot of links in these slides. I put the PDF up on GitHub, and also if you go to the page for this talk, there should be a link to the slides in there as well. So I mostly do electronics. The open source hardware is about more than just electronics, mechanical designs, all sorts of things. Anything that's physical that you build could be open source hardware. But in the context of electronics, a practical example is what are we talking about when we're talking about publishing the design for your hardware. So this could be the schematic, the board layout, and the bill of materials or the parts list, what parts go into the project. And when we're talking about the schematic and the board layout, we're not just talking about something like an output format, like a PDF, or an image like a PNG. We want the editable source files. So if you're using a program like KiCad or Eagle, this would be the KiCad file or the Eagle files. And the reason for that is if you want to enable people to modify that and make derivatives, then having the source file, so the CAD program, is much more useful. Another thing to note with the bill of materials is if you want other people to be able to build your project, it's good to use components that are available in low quantity or even single quantity from distributors. Some chips, you can only buy like in a million volume or something like that. So if you want to build projects that other people can contribute to, it's important to make sure that they can build it themselves. So how many people here have heard of Arduino? Okay, so a good number of you. So Arduino is a really popular microcontroller board. There's workshops all around Congress with it. There's one called the Arduino for Total Newbies in the hardware hacking area. So this was a board that was created at a small school in Italy. I think definitely over 10 years ago now. And the reason we all know of it is because they released the designs as open source. And at the time, it was good enough to do a lot of projects, interactive electronics projects and things like that. And they shared the design and they shared the source code for it. If you go to the link in the slides, there's a good documentary done back like 10 plus years ago about the original team in Italy that did it, which is quite interesting. So how do we know that the Arduino is open source? So probably the most popular board, the one pictured there, is the Arduino Uno. So if we go to the Arduino website, we can see that we can download the CAD design files from Eagle. So we can download the schematic, and we can inside that Eagle file zip is the board layout and the schematic. So when we're talking about publishing your hardware project as open source, you need to choose an open source license. And this can get kind of confusing because there's a lot of different options. So there's a suite of licenses from Creative Commons, some of which are open source licenses. So one common one you might see is CC, Creative Commons, BY, which means attribution, and then SA, which means share alike. One thing to note is if you see NC, that stands for non-commercial, and if you use the non-commercial clause, that's not compatible with the definition of open source. So some Creative Commons licenses are open source, some are not. They have different use cases. You can also use things like copyleft licenses or reciprocal licenses, which we see more so in software like GPL v2, GPL v3. There's also permissive licenses like Apache and BSD and MIT. So people are using all these licenses for hardware projects. And then there were licenses that were created specifically for hardware projects, which I'm going to talk about mostly is the CERN, the physics laboratory, created one called the Open Hardware License, the OHL. There's also one called Tapper and one called SolderPad. But I want to talk about the CERN one because I think that's one of the more popular ones, and CERN put a lot of effort into thinking about what's a good license for if you want to publish your hardware project as open source. So they have the idea of an open hardware repository where they're designing all these different electronics for their particle detectors and things like that, and they want to share it with other laboratories around the world. So they have this open hardware repository, and they created the license out of that to have a license for the designs that they were publishing in their repository. Javier Serrano is one of the people that runs the group at CERN that does this. If you click on that link in the slide, there's a good interview with him about why CERN is doing this and their motivations. So licensing can get confusing. There's also copyrights and patents. At the Open Hardware Summit a few years ago, Ari Douglas gave a nice talk that kind of reviews different licenses and kind of tells you about what might work well for your project and your situation. But what is the point of all this? What's the point of open source hardware? I think the point of it is you want to publish everything that will enable collaborative development. So why would you publish your hardware design? It's because you would want to have other people contribute to your project. And I would say if you're just doing it to kind of put a label on your project that it's open source, that might not be the right thing for you. The really key thing here is that you want people to help contribute to your project. So there's the Open Source Hardware Association, which I'm part of. I'm one of the board members of. Matthias, who's helped running this cluster, is also part of it. And this came out of this annual event we have called the Open Hardware Summit. So we're a non-profit in the U.S. The 501c3 means we're a federal non-profit, so we can get donations. People that donate things to us can deduct that from their taxes. And one of the main things we do is we host the definition of open source hardware. We also have things on our website, which I should really put there. It's oshwa.org. So if you type in oshw.org, you'll find the website. So we have things like best practices if you're doing an open source hardware project, a quick reference guide, a checklist if you want to go through and make sure you're publishing everything that's needed to be an open source hardware project. And one of the main things that OSHWA does is we help run the Open Hardware Summit, which is an annual event that's been happening since 2010. And we have it coming up on March 13th in New York City. So if any of you can, it would be awesome to see you there. It'll be our 10th one, in fact, so it's going to be our 10th anniversary. One of the things we did this year, we didn't have a summit this year. We skipped this year, and instead we did a thing called Open Hardware Month. So we wanted to have people around the world organize local events. And this was really cool. It kicked off with some events in Vienna and in Colorado in the US. And then we had 40 events in 14 different countries. This was things like meetups and talks and workshops. So we'll be hoping to do it again next year. So please check out, hopefully you can see it there. It's ohm.oshwa.org. We'll be doing it again October 2020, and hopefully we'll get more people involved around the world. If you're curious about what happens at the Open Hardware Summit, we have all the talks from the last one, which was in 2018 online. So if you search for Open Hardware Summit on YouTube, you'll find it. So one of the things that we did with OSHWA is we wanted to have a way for people to make it really easy to identify that a project's open source hardware, that it conforms to that definition. So we created this thing called the Open Source Hardware Certification Program. It's a self-certification program. You just go to certificate.oshwa.org and you can fill out a form, with the name of your project, description of it, the license you're using, point to things like your repo where you have your design files, your documentation, and what license you're using. And then you get this logo here. So there's a 2-letter for the country code, and then there's a ID number, a sequential ID number. So we did a badge last year for the Open Hardware Summit, and I registered it, and it was US 0071. And I put that on the silk screen. And the nice thing about that is if you get this board, or it's on the packaging, some people put it like on the packaging or like the little anti-static bag label that your project might come in. You see that, you can go to certificate.oshwa.org and look up the project ID and find the documentation, find the design files. So it's useful both for the hardware designer, the person making the project, if you want people to be able to find your documentation and design files easily, and for someone that's looking for a project, it makes it really easy to identify that the project is open source hardware. So if you are interested to learn more about OSHWA, you can, we have a mailing list that you can join. You can also join OSHWA as a member. And we have the OH Summit on Twitter is probably a good one to look at. We'll have a lot of news about what's going to be happening at the summit coming up. And the executive director of OSHWA, Alicia Gibb, is one of the people that started the summit, and she's our current executive director. And a few years ago, she wrote a book called Building Open Source Hardware. It has essays from a bunch of different people that have done different open hardware projects. So that's a good thing to look at if you're looking to learn from other people's experiences. So my two favorite things are Linux, the operating system, and open source hardware. So I wanted to talk about different projects that you can run Linux on open source hardware. So one of my favorite things is the Novena laptop. This was created by Bunny, who gave an awesome talk on day one here, and Sean Cross, goes by Zobs, who's also here. And they wanted to create a completely open source hardware laptop that they could use for the different projects that they work on. So this was a great example where they designed everything, the motherboard, everything was all designed and released the design files for it. And it had some cool stuff like an FPGA and a software-defined radio. I need to add a slide for this. This was probably about 5 years ago. There's someone now doing a current laptop that's open hardware called the Reform, and they're all the way in the back here behind the stage. Lucas from MNT is back there, and he has a really cool kind of the successor to the Novena laptop called the Reform, and it's all open hardware as well, the mechanical design, the electronics, and everything. One of the organizations I'm involved in is Beagleboard.org. So we're a nonprofit organization that helps design small computers that ranges from everything from makers to educators to professionals building products around it. So what we do is we work with different manufacturers and our community to get these boards manufactured. So it started off with the BeagleBoard, which was kind of one of the first low-cost ARM development boards back in 2008. And this was important at the time. Free software and open source software developers needed to get their hands on ARM boards so they could start building their software for ARM. Now we take it for granted that like Debian and Ubuntu and all the different software runs on ARM, but back then it wasn't necessarily the case. And then we made a smaller one called the BeagleBone in 2011. I don't know how popular it is here, but in the US there's these little mint tins called Altoids, so the board fits in the Altoids mint tin. Then we came out with the BeagleBone Black, which just kind of had better specs and cheaper price in 2013. I bring this up because this is probably the most common BeagleBones. If you ever seen a BeagleBone project, it was probably using this board. So these boards are all open source hardware. All the designs, the board layout, the schematic, the parts lists are available. All the parts are available from distributors like DigiKey and Mauser in Quantity 1. And because it's open source, there's many different companies that make different versions. So Element 14, Seed Studio, SandCloud, Arrow, they have different versions with different features. So that's kind of the cool thing about open hardware is like Seed was like, oh, well, we don't want HDMI, we'll take that off and it'll save money, it'll be cheaper. Arrow wanted to do an industrial one, so they bought industrial temp chips, which makes it more expensive, but then it serves the industrial market. So the idea of being open hardware allows them to create different versions for different use cases. This is a board we created for robotics projects. One of the neat things about this is we started using this chip that integrates a lot of different electronics into one package called the system in package. And this meant the board design was much simpler. So the other BeagleBones, like the BeagleBone Black, it's kind of a complex circuit board. It's using chips that are made for like things like cell phones, and they can get pretty complicated. And the nice thing about this one is a simple 4-layer board, which means that you can use it in simpler software like Eagle. Then we made a smaller one called the Pocket Beagle. And the cool thing about this one is that we also published the design files in KiCad, which is an open source circuit design software. So we want to lower the barrier to entry. So now we have the Pocket Beagle. It's a 4-layer board that's designed in KiCad. So anyone that wants to can download KiCad, open up the design files, and modify them. And the fact that it's 4-layer means that it's simple enough that if you wanted to, you could get the circuit board made. If you have a little bit of experience, you can go over to the Hardware Hacking Village and learn how to do surface mount components. You can, with like some practice, actually assemble one of these boards on your own. And one person that did was one of our Google Summer of Code students a few years ago, Kumar. He wanted to make a logic analyzer based around the Pocket Beagle. So he took the Pocket Beagle schematic, and then he added on the stuff he needed to make a logic analyzer. He also added on an Ethernet jack to it. And this was really cool to see someone take the designs and modify them for a different use case. And he was one of the finalists in the Hackaday Prize, which was pretty cool. We just launched a new board called the BeagleBone AI. This has more capabilities, more features, also open source hardware. But I don't want to continually talk about BeagleBone because there are other projects. Here's a good example here. So we registered this, I think, in the summer, and we got US 000169. So it's close to maybe like 200 designs have been registered in the US. And you can go to certificate.oshwa.org and look at different countries. I think after the US and maybe Germany, one of the top countries is Bulgaria, which is pretty cool because it's kind of a small country. So there's a couple of people there that are doing a lot of open source designs. And I mentioned Bulgaria because a really cool open hardware company there is Alimex. And they have a line of boards that can run Linux called OLinux Uino. There's a really cool blog post that the creator of, the founder of Alimex wrote, Svetin, about open source hardware and why it matters. You can go to Alimex, go to the blog, or you can click on the link in the slides there. So one of the things they did a few years ago is they wanted to make a 64-bit ARM board with one of the Allwinner chips, and they wanted to design it in KiCad. I think previously they were using some other proprietary CAD software, and they wanted to use KiCad because it's open source. And Svetin, who is the person that runs Alimex, he gave a great talk at FOSDEM a few years ago about the process they went to of switching from one CAD software to KiCad and their experience of designing this Linux-capable open source hardware computer. So to me, this is kind of like the a goal for me. I want to see boards that are designed in free software that can run free software that are in the hardware itself is open source. So if you haven't heard of KiCad before, or KiCad, people say it different ways, doesn't matter. It's an open source EDA suite, so it's an open source CAD program. So if you've heard of Eagle or Altium, those are also CAD programs that people use to design circuit boards. But this one's great. It's cross-platform, runs on Mac, Windows, and Linux. One of the coolest things that's happened in the last couple of years is organizations like CERN has developers working on it now. Also recently, the project leader, Wang, he just got hired full-time to work on the project. So it's kind of growing up from one of these things where everyone's working on it in their spare time to now people are actually working on it as their day job, which is really cool. If you want to learn more about KiCad, search for Getting to Blinky on YouTube. It's a great tutorial you can go through over a weekend and learn how to make a little circuit board. One of the things that Alimex did was they took that board that they designed and they put it into a laptop. So they wanted to make a kind of a open source modular laptop called the Terrace One. So you can find out more information on that. That was a few years ago. There's an event coming up called FOSDEM in Brussels that I'm hoping to go to, and they might have new stuff there. One of the other open hardware projects that I was a big fan of was the chip computer, which you might remember it made a lot of news. It had a big Kickstarter. It was called the $9 computer. They were a small company in Oakland. They did a Kickstarter. It happened in 2015. Unfortunately, the company went out of business in 2018. But the cool thing was, because it was open hardware, they had the schematics, the PCB, the bill of materials, all released under the Creative Commons share-alike license. People were able to take the designs and do other things with it. So, do I have a picture of it? Well, it's kind of there. So, one of the things they did was, oh, here it is. This was really cool. So the little circuit board is the chip, but they made this thing called the Pocket Chip, which was a really cool, like, little portable handheld Linux computer. So you could basically have your little Linux computer in the palms of your hand. It was a really cool design. Unfortunately, like, the chip went away when the company went out of business, but people still had pocket chips. So a person named Christopher Alessandro, he goes by Grogard, took the designs of the chip and then made his own version of it that plugs into the pocket chip. And if you click on the slides, you can see a little demo of him running Doom on it. So that's kind of like the standard demo is you can run Doom on your little Linux pocket computer. And if you want to find out more about the Giant board, it's also open source hardware. So Christopher went on to make a little tiny one that fits into a really popular form factor for boards called the Adafruit Feller form factor. And he recently did a crowdfunding supply campaign for that. So that's called the Giant board, and which is ironic because it's very small. So one of the other things that I'm very excited about, and this is kind of a thing that's come out of a lot of people here at Congress, is the idea of open source toolchains for FPGAs. There's an open FPGA assembly here. There's also a lot of people working on this stuff over in the hardware hacking area. So there's now a couple of FPGAs where you can use completely open source toolchains to program them. And one of the things that this lets us do is put a processor core on the FPGA that can run Linux. So there's a board called the Orange Crab by Greg DeVille. He's here at Congress, and yesterday he actually got Linux running on this little tiny board. The Orange Crab, oh, there's a picture of it. So it's a little board in the Adafruit Feller form factor, and this board is running Linux. So we got Linux booting on it yesterday. So if you check out Greg on Twitter, you'll probably find him somewhere in Congress. So you can see the Orange Crab yourself. Radiona is a hackerspace in Croatia, and they created a board called the ULX 3S, which has one of these FPGAs that's supported by open source toolchains and can run Linux. One of the people that did a lot of the software development behind this is David Shaw. Unfortunately, he's not here, but he's developing a board called the Trellis board. That's going to be kind of a higher-end board with like, I think like a gigabyte of DDR memory on it, so like pretty decent amount of memory. And this is another board that can run a Linux core that can run a soft core that can run Linux. Recently, back in November, Hackaday had a conference every year in Los Angeles in November, and the badge this year had an FPGA in it, and the FPGA was capable of loading a processor core into it that could run Linux. So I have that with me. I'm still trying to get that working on the version I have here, so if you're interested, find me later. Hopefully I can show a demo of that. And I mentioned RISC-V, so what I wanted to jump into next is talking about open source when it comes to chip design. So if you've heard of, you probably have all heard of x86, Intel x86 or ARM. Those are instruction sets. Those are the instructions that a processor executes. So a group out of University of California, Berkeley created something called RISC-V. So the cool thing about RISC-V is that it's a free and open source instruction set. So it means that anyone can take this and implement it. There's no royalties. If you make an ARM chip, you have to license the instruction set from ARM. So you pay a certain amount per device. And you also can't necessarily like modify it the way you might want to. One of the cool things was there was a group in Columbia, at a university in Columbia, that created their own microcontroller based on RISC-V, which was really cool to see. Now this unfortunately is not big enough or capable enough to run Linux, but it was pretty cool to see them do open source chip design based on RISC-V. There's an organization called Low Risk in the UK, and they're looking to make a system on chip or SoC that's RISC-V based, that's capable of running Linux and doing something like a simple smartphone. There's an organization called the Free and Open Source Silicon Foundation, or FOSSI, and they're kind of similar to OSHWA, but they're focusing on open source chip design, and they do a great job of organizing conferences throughout the year. So they have a conference called OrConf, which happens in Europe every year, and then they also have a conference called Latch Up that happens in the US. They also had the Week of Open Source Hardware in Zurich this past summer. So they host a bunch of different events. If you go to the FOSSI Foundation on YouTube, you can watch all the talks about all the different sorts of things people are doing with open source chip design. One of the other things they do is they host this website called LibreCores, where people can share their chip designs or the modules for the chip design. So when you're trying to make an open source chip design, you don't want to have to design everything over again, like the memory controller, the different peripherals and stuff like that. So the idea with LibreCores is people can share the designs of different parts of the chip. So what about actually making chips based on RISC-V? So there's a company called Sci5 that's actually making chips that can run RISC-V. This is a microcontroller, but they ended up coming out last year with a chip that was capable of running Linux. So they have a chip called the U540, so it's a 64-bit RISC-V chip that's capable of running Linux. And a lot of people at Sci5 are working on getting Linux working on that platform well. So this is the board here. It's a really interesting board. So it's a multi-core board that can run Linux on a RISC-V processor. The one downside to it is it's very expensive because it was made in low quantity. So unfortunately it's $1,000. So right now we're in a position of there's not really any commercially available low-cost RISC-V processor that's capable of running Linux. All the ones that are out there are microcontrollers. They don't have enough memory or processing power to be able to run Linux. So I'm excited to hopefully maybe in this coming year see chips come out that would allow us to build boards that could run Linux that would be, in my mind, I would like to create a RISC-V based board that could run Linux for less than $100. Now one route is to use FPGAs. The downside to that is that they don't run particularly fast because they're soft cores, they're not hard silicon. So like the board that Greg has, the Orange Crab, is cool, but it's only running at like 100 megahertz. So maybe by 37C3 there'll be some RISC-V chips out there that are capable of running Linux, and we can design an open source hardware board that they can run on. So if you're interested in that too, please get in touch with me. And in lieu of the silicon, we can start hacking on boards that have FPGAs on them. This is a link to the slides. And then I think I only had 30 minutes, so I don't know, do I have time for any questions? Okay, so if anyone has any questions. All right, I don't see anyone, I don't think. So, all right, thank you very much.
Thank you, Drew. Thank you for everyone who clapped for Drew, and thank you for Drew's research for being presented on. So we are now moving forward through our day. We have a workshop. If you missed the first Suzy workshop, that is going to start over here at FOSS Asia, if it has not already started. There is another workshop over in the very back corner, High School Math to ZK Snarks. So if you ever wanted to learn how ZK Snarks work, things like Zcash, which have implemented them, that's where you're going to want to go. It's a 6-hour workshop. Pack your lunch. It's back there, kind of to the left of the hanging replicant sign, where they have a whole bunch of big papers all put up there. So High School Math to ZK Snarks. Coming up, we've got btchip. Is that okay? Okay. Oh, that's you. Oh, you're here. Great. We're going to get this set up real quick. He's going to be presenting us privacy coins and resource-constrained hardware wallets. So talking about privacy coins, talking about hardware wallets, how they intermingle, the resources that required thereof. We're setting up. That talk will be here in a couple of minutes here. Everybody, fixing to get started one last time. Got a couple workshops. FOSS Asia over here with Suzy and developing things for Suzy AI. ZK Snarks workshop over here in the back. If you want to learn how those work, starting at 4, so in just a couple of minutes. But we're going to get btchip up here. He's going to be presenting to us about hardware wallets, privacy coins, as you can clearly see on the thing. You know what's really weird? We have like pocket of people here, nobody in the middle, pocket of people here. So it's like we kind of, you guys just don't want to like teacher to call you, sit in the front row type thing. You know, when you go to the supermarket and you either have to go super far away from the supermarket or super far to the side because all those close ones are taken. That's what I feel like. It's the opposite here. There's so much prime real estate for btchip to kind of point you out. Okay, look, we got some people moving. That's great. Go on and come on up. Let's go and introduce you. Let's give him a great big hand. Is it time to start? It is. It's not. It isn't. You have 2 minutes. So we have to. Can you banter well? Are you good at banter?
Not really. I mean, but yeah, well. So thanks for being there. Well, I hope you will enjoy the talk. So I will talk a little bit about privacy coin, but from a very high-level perspective. So well. What can I say? I mean, I can introduce myself in the remaining 2 minutes, in the remaining 1 minute before starting, so that could be something. So I'm Nicolas Baccar. When I'm not called by my handle, am I in the light over there? It's correct? Yeah, perfect, great. So I'm a co-founder at Ledger, so company manufacturing hardware wallets. What do I do every day? So I would say I am basically leading a team that is immune to roadmaps. I think that could be a good definition. I love smart cards. You probably have a smart card in your pocket and in your phone. So if you are attending CCC, you know that smart cards are very good at keeping secrets. You also know probably that they are very hard to break and that they are not open at all. And we are trying to change a few of those things. So basically we are trying to make them keep your own secrets and we are trying to open them. So I would say that the definition of where I want Ledger to be in a couple years, we want to be a successful smart card manufacturer. Which is where, well, most of the smart card manufacturers failed. They stayed in the 80s and, well, so I still have probably a few seconds, but anyway, I can start. So let's go. The idea of this talk is to give you an overview of some challenges and pitfalls that you can have when you implement privacy coins in a hardware wallet. So I will give a definition about all that. I think that probably the audience should be knowing what is a cryptocurrency, so I will remind you maybe a little bit about differences between signing something normal and signing a privacy coin. The overview will be very high level, so I want to give you some tools when you're looking at a privacy coin to know what you are looking at. I don't want to dig too precisely into details because I don't want to bore people to death, and I'm trying to keep the presentation as short as possible. And I will also use as little math as humanly possible because, well, you have a Zk-Snark workshop if you want in the background. I'm not a mathematician myself, I'm not a cryptographer, so if I'm trying to get into that, it will be boring probably for you and it might not even be right. So I will try to keep things small. So first, I can begin with what's a hardware wallet. So a hardware wallet, we can summarize it as an independent device that will hold your private keys and that will sign your Bitcoin transactions. So here is an example of, well, the hardware wallet we are manufacturing. It looks like a fancy USB stick with buttons and a screen. But inside, the main task, so apart from signing, is to provide human-readable information about what is being signed. Here, the very important thing is that the hardware wallet should make you sure about what you're signing. Because if you have a device on which you click buttons without really understanding what you're signing, you are not helping the user. So here, the idea is more than just protecting keys. It should really make cryptocurrencies and whatever you are doing easy to use. If it's not clear, you can imagine working with a hardware wallet with something completely different as well. For example, if you use it with SSH, a hardware wallet used with SSH will tell you that you are connecting to this server using this user, and that's the kind of idea we want to make clear. So we want to help both on security and user experience. Oops, yes. So today we face challenges when we design applications for hardware wallets because, well, those are not your typical computers and those are not even your typical microcontroller on which you can run Linux, as you saw previously. We are working on things that are much smaller. So we are working on things that we call microcontrollers. The idea is that the RAM is going to be pretty limited. So you can have, for the more powerful microcontrollers, some 100 kilobytes. And for something that looks like a smart card, if you have 10 kilobytes, you can consider yourself lucky. So if you are not used to write code, I mean, fitting in 10 kilobytes, that's really not much. And well, puts a lot of constraints on what you're writing. Apart from the RAM, the performance itself of the chip is very the chip is very slow also, so it doesn't have a lot of memory, and it's pretty not powerful. Let's say that 40 megahertz is something that works pretty fast as well, so the most powerful one would have, in the couple 100 megahertz, but that's again not a smart card, and the I/O is slow. So with all that, you see that if you want to process a lot of data, it's going to be pretty painful, both for the chip and for the user. So now a privacy coin. So what am I calling a privacy coin? Compared to a standard cryptocurrency on which you can track everything on chain, a privacy coin will be a coin that tries to hide part of the transaction, or at least part of the information. So we'll see that we have different kind of privacy coin. For example, you could hide the destination address, you could hide the amount, you could hide what you are transferring. Let's say if your coin supports different kind of assets, for example, the privacy could be hiding what kind of assets you are transferring. It could hide who is signing, and it could hide all of that or only a part of that. It really depends on the implementation, but as long as you see that your coin provides this kind of feature, I'm talking about a privacy coin. If you are a signer, something important to understand as well, so if you're just a user signing a privacy coin, privacy gets actually in the way. Because the hardware wallet, as I said, should display all information about what you are going to sign. And if part of the protocol is to obfuscate this information, it's hard for the hardware wallet to display it natively. And by natively, I mean when you send a transaction to sign to the hardware wallet, you should have no time of check to time of use possible bugs. So the hardware wallet should be processing what you give to it, and what you are actually passing to the hardware wallet should be as close as possible as what is native to the protocol, because otherwise you get a lot more issues, and part of that talk would be discussing the kind of issues you can face if you don't pay too much attention about the protocol that you are currently handling. So ideally, even the hardware wallet shouldn't even care about privacy, because if your system is designed in a way where privacy and security are two isolated blocks, we'll see that privacy shouldn't be really important for a local observer. The main goal of privacy in a privacy coin is to make sure that if somebody is looking at your transaction over the network, they are not going to be able to extract information from it. But locally, you already have all this information. Your wallet is displaying your transaction. You know who you are sending a transaction to. So regarding the host, privacy could completely be handled by the host in the end. It's just that, so in an ideal world, in an ideal design, we would do the privacy part, which is cost intensive, by the host, which is much faster than the hardware wallet, and the security could be done fully by the hardware wallet, because that's, initially its job. That's still in an ideal world. In the real world, it's a little bit more complicated, and things are put together. So you have to work to remove those things and to extract those things the best way possible. And we will see, what this means for different kind of coins. So then, first, maybe if we want to think a little bit back about the network and how consensus is working when you are sending a transaction, you can think that privacy features are getting in the way of consensus as well, because the consensus should maintain the integrity of the chain. So when you're sending a transaction, part of the consensus is checking that you are not spending transactions that do not exist, that you are not creating assets, that kind of things, because otherwise, your blockchain is not very useful. It's going to fork. You are going to create fake assets. You don't want that. But now you want to operate those checks, which are very easy to do when your blockchain is fully public, on something that's obfuscated. So you don't see the information, but you should still be able to perform checks that guarantees the integrity of your blockchain. And for that, you need a few new cryptographic primitives compared to just signatures that are used in a typical blockchain. So we'll see that first. I mean, to start, well, you need a new set of primitives. In those new sets of primitives, you need to blind some data. So blinding means that you are going to encrypt a value using a secret, but this secret is going to, the keys you are using for blinding are going to change because you want to make those keys variable and you want to hide different, you want to make those keys, well, flexible as well. So usually the secret is obtained by performing an elliptic curve Diffie-Hellman, so between ephemeral keys. So the idea is that you have a public key and a private key for each party, so for the sending party, for the remote party, and both parties can agree on a secret by multiplying the private key by the public key of the other party. So, and the idea is that you will obtain the same secret. After you have this secret, you can do pretty much whatever you want with it. So it's just a number. So you can use, for example, a symmetric cipher to encrypt what you want, or you can run it through another algorithm. But here, well, you can. I mean, you're free to run it through any kind of algorithm you want. The idea is that this secret is related to the key that you picked for your privacy. So you can decide to share this secret if you want. And if you do that, you reveal information about this information, because then someone having this secret could reverse what is seen in the blockchain and could basically do what you would do as a receiver when you get this information. So you could extract information about the transaction. And this concept is, well, is pretty common for all privacy coins, and typically you will find it, oops. Hello. So it will be called view key for Monero. And I'm trying to turn it back on, but it doesn't want to. Help! Hello? Oops. Yeah, well. Okay, so while we are booting, I can try to finish that slide. So the idea when you blind is that, well, you can provide this to an auditor a little bit later, but well, this will have no consequence on your own security. So you are just choosing to reveal your transaction only for one. You are choosing to reveal information voluntarily for one information, and this action can be done very easily by the device, because in the end it's just a point multiplication. So that's in any case not a concern for a hardware wallet. Commitments. So commitments are a new thing that you won't find in a typical cryptocurrency. So the idea is to use a simple cryptographic algorithm to commit to a chosen value, keep it hidden, and then reveal it later. So that's the general definition of a commitment. Here we are talking usually about homomorphic commitment, because the idea is that you can perform computations on the commitments, and the computations will be similar to computations that you would compute on the clear value. So one use case for that is if you want to prove, for example, that the sum of your inputs are equivalent to the sum of your outputs in a transaction, you could do an homomorphic commitment on top of that and then verify at the consensus level that you enforce that property. So one popular commitment scheme that works with on elliptic curves is the Pedersen commitment. So a Pedersen commitment is just, again, point multiplication and addition. So if you want to commit to a secret and a value, you would take two generators, multiply by your point, add a random, and well, so that's also very easy to do for the device. Getting into something a little bit more complicated, once you do that, you want often in your consensus validation that a number that you can't see, is in a given range. For that, you need a cryptographic construct called a range proof. So range proof is a zero knowledge proof, so you don't know the numbers, but you are able to verify something. The performance and size will vastly depend on the implementation. And vastly, I mean, it can go from a couple kilobytes to a couple 10 kilobytes, 100 kilobytes. So you had, for example, in Monero, you had a modification from the proof changed from typical old proof to bulletproof. So that was kind of an optimization that was done. Today you have different set of algorithms. You have so very complex ZK snark circuits, which I think the workshop is probably going to talk about that. You can find an implementation in a library called libsnark, for example, if you're interested to dig into that. Here, the interesting thing is that, well, Adam Back and Greg Maxwell published an interesting implementation for range proof that will work with only usual maths that we use for elliptic curve signatures. So the idea is that you will keep doing some point addition, point multiplication in your usual group, and you have a proof which is small and fast. I mean, it's fast for a general purpose computer. For a microcontroller, it's still very slow. So you can't really run that proof on your device, but still you have an option to have something that's short enough, let's say. And finally, concept of a ring signature. So ring signature will be a signature on which, well, you have a group of signatures. You don't know which is the signature that you are going to verify, but you have one verification which is possible. So in this kind of construct, each individual verification, each individual signature can be easily performed by the device. The problem might be, depending on the size of the ring, to know exactly if you can compute all the signatures. So the construct, well, I will skip very quickly around that. The main idea is that in your ring you have set of private keys and public keys. You call that a ring because you can actually close it. So you start by picking a point, then you will keep your next point compared to the first point that you picked, and in the last one you will make it loop. So well, in here you can reduce the signature to have a simple construct that looks like a Schnorr signatures. So you are just doing a multiplication and a point and a subtraction, and well, you will have a lot of that in your signatures. So in the Monero, if we want now to see how those constructs are used in Monero, so Monero is a custom blockchain, so the destination and amount are hidden. The range proof can be fully computed on device. The security uses a ring signature for anonymity, so with a ring size of around 10. So the problem with that is that we have too little RAM on the device to handle the signature in one go. So what do we do when we face this kind of constraint? Well, we will split the signature in different parts because we can keep all parts, we can do all parts of the process, send it in an encrypted way to the host, and then continue to produce the next stage of the signature. So here, we still have an issue if we want to display something on the device, because the transaction hash will already commit to all elements, so we don't have a security concern here. Hello. So we don't have a security constraint here, but well, we still need to provide this because otherwise we can't display anything on device. So a way to solve that is to create a commitment, but the commitment won't be part of the Monero signature, it won't be part of the process, it will only be linked to, well, to the device to recognize that previously you agreed on a value, and that when you sign, you verify that the value you agreed on previously is still the same value. And well, if we want to do that on device, given the spend key and given the view key, so the spend key is the key that you are using to create to sign your transaction, and the view key is the key that you are using for blinding. We will generate a symmetric key. So the symmetric key, we call it SPK. It will be derived from the spend key, the view key, other elements. And here, so that was our first implementation. We had a key that didn't change given a wallet seed. So the seed is what personalizes your wallet when you create it for the first time. And well, a simple way to encrypt stuff is just to use AES in that case. So we would send the different elements to the host, And well, what we are signing, so as a reminder, here we are signing here as a Schnorr signature, and we are using a hash of an index involving a view key and the span key. So the problem when we do that is that, oops, yeah. So if we add this, if we keep this protocol, you see that we don't have any way to distinguish between the different teams, the different sequences of the signature. So if, as a host, you keep a part that was sent by the device and you resend it to the device, you end up in a scenario when you can force the device to do something that it's not supposed to do. So in that case, the example is that you end up with a signature. You end up with two signatures that are computed with different nonces. But in the end, they are signatures of the same. They are signature of the same key with different nonces. If you have been following the story about, well, cryptographic attacks, you know what happens when you have a signature with different nonces and the same key. You have a PlayStation. Well, more commonly, well, I would say a PlayStation attack. So you can recover your key because you have the nonce. In that case, you can recover everything because you know all the other parameters. The other parameters were already passed by the wallet, were already passed by the, you can find them in the chain if you want. So here you end up with, well, by simplifying the protocol, or at least making it runnable on the device, you end up in a situation where a malicious host can extract the key. Because, well, just because we didn't pay attention in the way the key was generated, and it's easy sometimes to get lost when the protocol is a bit complex. So here, good thing is that it's very easy to fix. So the main problem was that the key was fixed. If we end up with a key that's not fixed, and if we, well, create an index in a new protocol to make sure that we can't be fed back something that was coming from another step of the signature, we fix the problem. So here we just decided to switch to an HMAC instead of using AES, and well, and then we don't have an issue anymore. So to summarize what are our experience with Monero, going through the crypto is clearly an adventure because the crypto is complex. You can review the code for it, I mean, in the Monero client, but in the end, you have to talk to people on IRC to really understand what is going on. Good news is that the community is always ready to help, so that's clearly a big plus. And if we want to see how privacy and security mixed in the case of Monero, in the end, they are already quite separated. So the way where they mix together is when you create the ring signature, because then you would commit, I mean, the privacy part would commit to some part of the security part. But that's a good thing, because that's in the end, that what guarantees that you don't have values which get recoverable in one case and lost in another case. So that's giving a small teaser about the next part. So in the end, Monero implementation is not difficult once you get the crypto. The only constraint we had here is that we don't have enough RAM to do everything in one go. So on another device with a bit more RAM, we would have been able to do it much more efficiently. If you want to dig deeper, I'm providing a few links. So you will be able to see that because the presentation will be public. So you can see a security bulletin that we published regarding this attack, and the documentation of the Monero application, which describes with a lot more details all the different steps that are actually done by the device when it's signing a Monero transaction. Then I wanted to talk about another example, which is a little bit less known. So I think it's interesting as well. It's Elements. So Elements, which can also be called Liquid, is an open source privacy extension which is built on top of Bitcoin. It can be run as a custom chain or pegged on Bitcoin. So by pegged on Bitcoin, I mean it can be run as a sidechain, and you put Bitcoin in, you put Bitcoin out. So Liquid is a commercial version of Elements that runs with a fixed federation model. So you have a few people already involved in Liquid. Well, they take part in this federation because for them it's faster to exchange assets over Liquid. And from a security point of view, they have the extra privacy. So as far as the signing logic goes, we can completely forget about Liquid and we can focus on elements. Because Liquid is, in the end, just an instance of an element federation. So if we look at a Liquid transaction, if you are familiar with Bitcoin transactions, you will see that everything looks quite the same. So you see a segregated witness transaction, you recognize the witness, the script is completely standard. Here you have, well, the main difference with that, you will see that the transaction is marked as confidential, so you don't see values in the outputs. That's a big difference compared to Bitcoin. And you see that the transaction fees appear as kind of a new output, so which is not something common. Usually in Bitcoin, the fees are computed are given as a difference between the outputs and the inputs. But here, as the outputs are confidential, you see that the fees appear as an additional output, because otherwise you would have no way to compute them, and the fees are not hidden. So you reveal some information about your transaction. And of course, you reveal the address as well. So it started from confidential transaction initially. The Bitcoin transaction structure is mostly unchanged, as you've seen. So the transaction, the signature model is very similar to SegWit. You just add a few additional commitments for the values that are hidden. So you can still track addresses and transactions. So unlike Monero, which is more confidential on that, you can still follow a few things if you want. The amounts are blind. Well, the fees is not blind, but well, let's see that I think it's acceptable. And the basis of elements, so the range proof plus the ring signatures, was reused for Monero. So that was, if you look at the ring city paper, the idea was coming from Monero initially, and then it was slightly modified. It was coming from elements, sorry, and it was slightly modified to fit on Monero. So I would say it's a model that has already been, well, living in the field for a couple of times, and we know that it's robust. Then another extension has been created on top of elements called confidential assets. And here the idea of this extension is to encode an additional data inside the transaction and define a concept of asset. So here, well, the idea is to say that in a transaction you could send, for example, Bitcoin, gold, wood, silver, whatever, and you can put all those exchanges in the same transaction and not reveal to an observer what you are currently sending. Bitcoin is a confidential asset itself, so which also explains why it gets in the clear when you are sending a fee, because you need to know what kind of asset you are sending. So maybe later you could choose to pay the fee in a different asset. For the moment, it's still paid in Bitcoin. But the type of asset and the amount that you are exchanging is always blind. Here, if you look at cryptographic elements that are used by elements, so you will find roughly another instance of the same toolbox, so which you are going to find for all privacy coins. So the blinding is done through ECDH. There is a new concept called a confidential address. Confidential address is in the end just a Bitcoin address to which you append a key that you are going to use for blinding. So it's a public key plus another public key. There is a new proof introduced for assets to verify that assets are not creating additional assets called a surjection proof. So this one is not a range proof, it's based on Pedersen commitment. So it's easy to compute and easy to check. And the range proof in that case is a special construct. So it's using something that is quite similar to ring signature, the way you build it, but not done exactly the same way. And well, something extremely specific to Liquid, to elements in that case, is that when you when you verify the signature, you can encode values as a side channel in the signature itself. So when you unblind the signature, you will get the value that you use to encrypt, to blind the different assets. And you recover them, so you have your blinding key. You verify the signature by providing your blinding keys, and by doing that, you get two things. You get first validation that your signature is correct, and you get the values that you use to blind your assets. So I'm just being a little bit insistent on that because you'll see that it's useful for when you compute a signature. So it seems very easy. I mean, you have the clear assets and values, you give them to the device can compute commitments. In the end, you are signing like Bitcoin, so you can just use a Bitcoin application, modify it a little bit, and you're able to sign an elements transaction, because then the host can compute the range proof. I mean, like everything that was done previously, so it seems really, really easy. But, well, in the end, if you look again at the two black boxes, as privacy and security as black boxes, you'll see that both are using the same asset with no commitment. So there is one which is the security part at some point needs to blind the assets because the assets that are signed are going to be blind. As a range proof, which is run by the host, is using the blinding key, because when you recover, as I said before, when you are going to verify the signature, you are going to use this blinding key to recover the values that you used to blind the assets. So ideally, both should be, you should have a commitment in the range proof on the values that you picked, but you don't. So here, a consequence of that is that you can run an attack scenario with your malicious host where the device is still computing the commitment, so everything is done as expected. The device is signing, so you are in your transaction, the security part is signing the right commitment, but the malicious host can keep the commitment. It knows everything that was used to generate the commitment since, well, you are generating that from the host. So you end up with a transaction, but the host can force its own blinding key. In that case, the blinding key won't be the blinding key which is expected by the remote party. The transaction would still be valid on the consensus level, which means that the remote party would receive a transaction, which is in the end a blinding transaction that is not recoverable. And well, it seems like a denial of service attack here, because well, what can you do with that? You're just thinking, well, you're not going to be able to do much, but it's kind of a ransom. Because you could negotiate, you could end up going to the receiver and negotiate that, well, that's okay, well, you can have your funds back, I can give you the keys, but you need to pay me for that. So it's more than a denial of service, it's a real case of an attack. So how can this be fixed? First, it could be fixed by running everything on device, so not splitting the privacy and security parts, but we can't really do that because we don't have enough power, we don't have enough RAM to do that. So we took the easy way out in that case, is that we are going to generate all the blinding values deterministically on the device. So if the host is compromised in the end, the receiver can see that the transaction is not really, well, cannot be decrypted. It can always contact the host and ask to recover the original values that were picked. So that's not I would say, super comfortable, but at least it's better than losing money. So that's what we decided to do for the first implementation when we are going to sign liquid transactions, elements transactions. So to summarize here, the cryptographic primitives are quite isolated and nice to reuse in libsecp. So if you want to look at that, you can do it. You can reuse them for your own project. But I would say that the privacy and security blocks are not really designed to be split at the moment. So we tried to do it because we had to do it. But there might be ways to create constructs that are a little bit more appropriate to do that. So here, the conclusion is that the implementations that we picked had a non-trivial impact on security if you consider a compromised host. So those kind of attacks where you can create more than a denial of service are getting more common. If you think, for example, about picking a random change or picking a random pass, derivation pass, when you are sending a Bitcoin transaction, that's something to think about. So it has impact on the way you are presenting transactions to the user. It has impact on the way you are displaying confirmations, and well, that's something to keep in mind when you are designing those protocols. So few links if you want to dig deeper. So specification on confidential assets, elements tutorial, specification, the crypto library, so the elements version that is used for elements, and Bitcoin applications that we have, the modifications that will be available soon on GitHub, so not yet. Another thing I want to look at, but we didn't look at it yet, is sapling, so the privacy construct that is used in Zcash. So here we have much more exotic cryptographic primitives compared to the others two, which were just reusing elliptic curves in the end. So we have a new curve. We have new algorithms for the hash and signature. The snark proofs are much more complex than what was done previously. So maybe that's something that people will be talking about in the workshop. But the nice thing is that it's getting popularity outside of Zcash. For example, there is a Rust implementation which is actually used by Tezos, and well, so I think it's something interesting to look at for a signer, and just more complex, and it will require a lot more study. I mean, to be sure that it can be done properly. So as a conclusion, I would say that, well, the way you can look at a privacy coin at a super high level, so when you are just a signer, is that you can try to isolate privacy and security, see how they fit together. And, well, if you are implementing the signature part in a resource, in a device that is lacking, I mean, the proper resources to do it, you have to think properly about how to split the blocks, because it can have completely unexpected consequences. So, that's it. So it was even much shorter than what I thought. So if you have questions, feel free.
One. Oh, sorry. Are you okay? What about Mimblewimble with Ledger? Is it going to be available, or?
So Mimblewimble, I will probably put it in the same category. In the same categories on sapling, the cryptographic primitives are going to be a little bit exotic, so we will need to see how it can be split properly. We might be running into the same kind of issues. So I didn't look at Mimblewimble yet. I know that some team is looking at green currently. So they probably have some. Well, I have already seen the kind of roadblocks that they have hit. They try to port directly from libsecp. So of course, so it's not enough RAM in the device to run properly. So they had to change a few things that are not working yet. So I think the integration is, in my opinion, doable, but complex. Okay, thank you.
Yeah, thank you very much, btchip. Thank you guys for all of your hard work in integrating Monero into Ledger. The community was really excited when that happened, and it's good to actually meet you. I saw you. I didn't know you worked for Ledger. Now I know. So my respect for you has greatly heightened than for the average nerd. So good that I know now. So. He was scheduled to go on for an hour, but he said he wanted to skip over all the math, so it didn't go over, so we wouldn't be so confused. He is available for questions as well. Wait. I shouldn't say that, because maybe, are you going to be available for questions, or are you getting out of here? Okay, I just assume they are going to be, but maybe they want to get out of here. So he is available for questions. If you do have them, you can go talk with him about that sooner. So because he was scheduled for an hour, he finished after half an hour. That means we have half an hour where we can kind of take a break. Coming up next at 5 o'clock, we have the RMX hardware wallet, which Pavel is going to be talking with us about. So if you're interested in more hardware wallet stuff, that's great, because we're going to have more of it here in 30 minutes. So lucky you, today is your day. Actually, I thought, there is also a Swarm Talk. Yesterday, we did have a Swarm Talk scheduled, and that there was some sort of something that happened, and we are now going to have that Swarm Talk today. So be here for that afterwards. Workshops, the ZK Snark workshop is still going on back there. They take you from high school math to ZK Snarks. So that's going off in the back corner over there. I think NIM is done. Yeah, I don't see those guys anymore. And I'm unsure about the Suzy thing. Maybe they're still going for the Fasasia if that's in Suzy AI is interesting. We'll be back in half an hour, everybody. Don't go anywhere, or go someplace for half an hour and then come back.
Okay, thank you, Diego. Do you hear me? Yeah, okay. It sounds quite different here than there. Okay. Okay, hi, I'm Pavel. I'm here to speak about Remix Wallet project, which we are working on. It's definitely not only me working on that. There are more people, but I will talk about it here. Okay, so what I would like to go through today is there are 4 main points. One is how we are trying to keep the project going. Then there is a hardware messenger which we are trying to implement. There's also Monero wallet implementation we are trying to do. And the last point is hardware security of the project. So, building hardware is challenging itself. I don't know how many of you ever tried to build something and do it in an open source manner. And it's not so easy to find the contributors and developers who will like for free do that stuff, and they do some commits which actually have a sense. So at the end you find out that there is like a combination of a depression and hard working nights, and it's not so easy always. We are a lot of thinking about the next steps, because every time when you are working on something, you should have at least clear picture of what is coming after, because otherwise there are people asking you what they should do and why, and you must coordinate them somehow. It's very important to have some policy how to avoid burnouts, because it's very obvious. And the last thing is funding. The best is if you don't need the funding at all, but it's very hard again with the hardware, because actually you are burning the real world resources. You are building a board, you are soldering stuff, ordering parts, and it's really expensive if you compare it to the coding, because coding is for free. Okay. So what we have here is we have a device, and because we are trying to be very lean on the development, we are building it in a couple of pieces. So it looks like that. It has alphanumeric keyboard, and the first thing we were implementing on that is a hardware messenger, and it looks like that. You have 2 devices. You plug them to USB, and you write down a message on one device. You write it down like SMS. If you remember the old Nokia style keyboards, so it's sort of like that. And then you can send this message over internet. We are using XMPP protocol because it's very easy to work with. But we are open to another options. So if you think that you understand messengers and you think that we can use something different, please tell us. We can implement it later. So right now we are able to send a message from one device to another, and it's it's encrypted. So it's escape the device is like binary blob, and nobody can read it. Okay. Implementing a Monero wallet. For those who don't know how Monero wallet concept works, so basically Monero uses 2 keys. I hope probably a lot of people you know about it, but just briefly, you have a Monero blockchain, which is like a bunch of data, and then you have a secret view key and secret spend key, and those 2 keys are in a wallet. And what wallet does is that it just takes the key for a certain operation the wallet wants to do. So if you want to distinguish, for example, which output belongs to you, you are using a secret view key. And if you want to sign transaction, you are using a secret spend key. Or if you want to distinguish if the output is spent, you are also using the secret spend key. Okay. So basically, if you want to implement Monero wallet, you must be sure about the way how we are using the secret view key and secret spend key. Yeah, this is what I described. Okay. At first, the difference between Bitcoin and Monero is that in Bitcoin, everything is in plain text, but the Monero uses a blockchain where everything is encrypted. So if you are doing a scanning, if you want to distinguish how many outputs are there, are yours, and balances and all the stuff, you must do a lot of cryptographical operations. You just basically take a piece of data, then you unlock it with some cryptographical magic, and then you see if it's yours or it's not yours, and then you go more into that. And this is really like resources hungry. It needs a lot of computational power. So that's why usual approach in this like cryptocurrency field of a different manufacturers of hardware wallets is they choose a public scanning to do a Monero scanning of blockchain. If they are doing a public scanning, that means that they offload this view key to the host, and this part of the scanning is done on your PC. And then, when you distinguish which output is yours, then at that point, the private key comes into play and starts to do that unmasking and more operation on that. And this is the point where we think that we are a little bit wasting the beauty of the Monero protocol, because it was designed in a private way, and by leaking out the view key, you are basically like crippling it a little bit. So this is why we wanted to do a hardware wallet which is doing private scanning. The problem is that with with the hardware wallet, you want to use like a dump processor, which is simple to program and doesn't have too much anything more than you need. And at the same time, you need a lot of computational power for that. That's why we are working with this microchip CEC1702, because it's basically Cortex M4F with a block which is used for hardware accelerating the certain functions which we are using in the code. So we are trying to re-implement the whole Monero scanning and whole stuff, and we are using these certain accelerated functions to make it faster also on this dump processor. Okay, so those numbers are what we estimate could be feasible. We have a working wallet right now, but it's a little bit slower than that. But there is a lot of room for improvement. So I believe we can get close to this. Okay. There's a big question also, because right now we have maybe 7 transactions in a block on the Monero mainnet. It could be enough now for our project, but in the future, when there is more transactions, there is probably more need to do something faster. Okay, but this is what we have now. And if I want to speak a little bit about hardware security of the thing which we are using, like of the CEC1702, it has a secure boot feature. It's booting only signed images. Okay, it's vulnerable, of course, to some fault injection and glitches, as every kind of this Cortex M4 processors. You can avoid these security problems with using a passphrase. You can have your own source of random, which we also have on the board. We have our own true random number generator, and also we are using a couple of secure elements to combine the random to make a seed. So there are some ways how we would like to improve it, but basically we know about these the possibilities of attacks, which people usually do on Cortex M4. But we want to avoid that by using secure elements and own source of random. Okay. Now I would like to speak a little bit about the project itself, because we are so lean in terms of management that sometimes I'm not sure if we even exist. But we are working 1.5 years on that, and we have like 5 prototypes, and the last prototype is I would say quite working. And we would like to continue more with work on that. And in case we find out that it's not enough in the terms of speed or computational power, we will probably switch to FPGA, or maybe we will do some experiments with RISC-V in a short-term future. Who knows? But right now we would like to use that microchip because it has enough computational power. And if it's not enough, we will just improve with something faster. Okay. Yeah. Okay, that's all. If you have some questions. No questions? It's time for Diego.
It's time for me. Thank you so much, Pavel. Let's give him a second round of applause. Okay, stop. Let's give him a third round of applause. And that's all you get. So thank you so much, Pavel. We're going to go ahead and send him off the stage. Let me pull up my little schedule that I got going on here. Oh my gosh, why are there so many apps open on my phone? Where is my schedule? Oh, it's in another tab. Are any of you people the kinds of people that have like 60 tabs open in your browser at any given time? If you are, oh my gosh, you guys are the most frustrating people in the world, okay? Don't do that. For your poor computers, it hurts my soul. We have, coming up next, a talk on Swarm, which is not going to be for 30 minutes. So if you're here for that talk, then you're a sucker, because it's not going to happen for 30 minutes. So you guys, go get yourselves a hot dog, go get yourselves a bathroom, go get yourselves a water, and come on back here in 30 minutes if you want to hear about Swarm from Viktor. And we'll be all set up and ready to go by then.
I can hear you.
Okay, great. So I am going to pass off this figurative microphone to you for you to tell us all about this Swarm project that you guys got going on. So go ahead and take it from here.
All right. Thank you very much, Diego. I don't know whether we have audience and when you can hear me well. Can you give me some feedback whether it's going okay? Okay, wonderful. So the Swarm project is pretty ambitious. It's been started as a project within the Ethereum Foundation. And as you might know, Ethereum from the very beginning has on its banner to realize the Web3, basically the decentralized internet. So this is what I'm going to talk about to you. And the talk is quite timely because the Swarm project is going through a phase transition, as it were, because we're graduating as an autonomous project from the foundation, and in the process of making our own Swarm Foundation, and with some new ecosystem support, kind of breathe new life in the project, and going from an exploration phase and phase of 5 years of research and development, going into phase of delivering actually a proper product. So what's the basic promise of Swarm? So Swarm is trying to build base layer infrastructure for the new decentralized web, the old new decentralized web, the way we always imagined it to be. Our motto is to create a storage and communication platform for self-sovereign digital society. So basically, we're trying to define infrastructure primitives that provide a tool set for Web3 development stack to build real-time interactive web applications over decentralized infrastructure. And it's basically using the decades of R&D behind peer-to-peer networking and learning from the successes and limitations of BitTorrent. And most importantly, it recognizes that the final missing piece of the puzzle is to have programmable self-enforcing incentives to make the network self-sustaining economically. And what we needed for that is blockchain technology, basically to have smart contracts, making sure that both the micro commitments or micro payments in the bandwidth incentives of the network are properly settled on chain, as well as to be able to incentivize, give positive incentives for file persistence, as well as have negative incentives against file loss or content loss in the form of insurance. So basically have the punitive threat over individuals' head if they, in case they lose the content, they stand to lose their deposit and collateral. So there are three areas in which Swarm is trying to provide infrastructure for basically storage, communication, and access control. We have an exceptionally strong privacy proposition, including anonymous browsing, anonymous uploads, and censorship resistance. So basically permissionless access to upload to the cloud, to download from the cloud, and also anonymous messaging. And what's even stronger proposition is that we propose basically zero-link communication, which means that on top of confidentiality with the end-to-end encryption, which is kind of trivial these days, and anonymous and unlinkable sender and recipient, we provide zero-link communication in the sense that the very fact of messaging or very fact of communication can remain obfuscated. It's a very, very interesting use case of the Swarm infrastructure, and it kind of shows us that it shows very good signs of good design, because most of these solutions kind of fell out of it kind of organically. It provides, apart from exceptionally strong privacy guarantees, it provides a comprehensive incentivization where sharing of bandwidths and storage is optimized and incentivized. It's also a maximum resource utilization network and a proper cloud service, as it were. So it sets it apart from normal or kind of usual file sharing systems, even the kind of progressive ones like IPFS, because it provides a proper upload and disappear experience. It also provides a maximally responsive dynamic adjustment to capacity shortage and surplus, with basically self-regulating pricing. That if the price signal is strongly following capacity constraints, then the principle of supply and demand can be maximally responsive in these cases. It also provides, apart from storage and communication user experience, with the vision that we have ahead, we provide a product suite to basically for incentivizing decentralized service networks, which means that it's basically supporting all kinds of services as part of the digital service economy, and also infinitely scalable, provable, and decentralized database services over the network. So Swarm is kind of coming out of the 5 year of incubation and research and development, and it's ready for prime time soon. We're transitioning from exploration and incubation to product development, and we started to consolidate the organization that started out as a dev team within the dev team within the Ethereum Foundation, now as a proper organization with all kinds of branches, including legal help, finances, etc., and marketing. So we gained autonomy from the Ethereum Foundation, graduated as a project now, enjoying support from the ecosystem, and hopefully we're going to be cross-chain compatible. We have strategic partners, including IOV Labs, who work on RSK, like a Bitcoin-based Ethereum virtual machine-based blockchain, and the Swarm that is going to come out, so the version 1.0 will be compatible with this chain, as well as Ethereum Classic and Ethereum itself. To mark the transitional phase, we're writing the book of Swarm, which is going to be out in Q1 2020, after which we soliciting peer review to audit the solutions, as well as the prototype code that we have. It's basically, the book is basically consolidating 5 years of research and proof of concept development, and contains the entire exposition of the design and architecture of the system, as well as consolidates very rigorously composed specs, which would allow multiple language implementation of the Swarm client, which we have already some candidates for in some strategic partners. Swarm achieved a wide range of true innovations and has as design principles modularity, and I have to say that managed to reach a system which is very clean and elegant, easy to understand, and shows very signs of good design. Basically, it provides solutions to unforeseen problems that kind of fall out of the system without too much uncertainties. So, just to conclude, and then I give over the microphone for the audience to ask some questions. So to conclude, basically, we saw the recent revolution in decentralization, starting from Bitcoin. Basically came up with the genius idea of combining proof of work and worker chains to provide an immutable ledger. And it started the cryptocurrency revolution. Ethereum, with its system, generalized the state transitions to allow Turing-complete virtual machines. And it invented how gas accounting can practically make the Turing-complete system resource-bound. and by which it's solving the hosting problem and related computational problems. While the blockchain revolution is steadily recovering from the throw of the hype cycle and hopefully going strong, I argue that the next big thing is in the making, and it's basically in the context of a lot of people disappointed with the current web technologies and the productization of end users, problems with data sovereignty and censorship. Many fear that the time for Web3 and the truly decentralized World Wide Web has come, and Swarm is hopefully contributing to this need and building on decades of R&D and in peer-to-peer networks, combining it with the power of blockchain can provide a very elegant and very comprehensive solution for storage and communication on the web and power the real-time interactive web applications as we get used to in Web 2. So hopefully continuing what's good, but eliminating what's bad in terms of the data silos and the misaligned incentives that we currently see in web. Thank you very much. This was the introductory talk, and please feel free to ask me questions, including technical details, organizational changes in Swarm, status of the project, or comparison to other related work. Thank you.
Okay, thank you, Viktor. So you can't see here, as far as I understand, so I will let you know. Do we have any questions for him? If so, we can pass you the microphone. Going once. Going twice. It does not look like we do. Thank you for your presentation, Viktor.
Thank you very much.
Let's give them a round of applause. I don't know if you'll be able to hear it through the microphone, but they are all applauding. And we are good to go, I think. We are ready for our upcoming things. And those things that are upcoming, blockchain sharding is going to be happening at 6 o'clock. So in about 15 minutes, we're going to talk about blockchain sharding, which for those of you who don't know is some sort of like scaling thing where you shard the blockchain and give certain pieces to certain people and stuff. And if you want a better explanation than that, you're going to have to be here around that time. So once again, Zero Knowledge Proofs workshop going on way back there. They've probably advanced to junior college math. They're supposed to take you from high school math all the way to ZK Snarks, which is very difficult to understand. So if that kind of thing intrigues you, you're a mathematician, you just want to get a feel for how all this works, back there is where you're going to want to go, all the way to the back left of the... I'm getting they're holding a sign for me, which because of the beautiful lights that they've set up so you can see my face, I cannot see. And because of the wonderful contrast or lack thereof of the sign, it's black letters on a dark gray background. It's wonderful. I really appreciate everything they do to communicate clearly with me. But I think it says that they need some time, or they need, that's basically the only thing they tell me is that they need time. So that's why I'm assuming this is what they're going to say. Blockchain sharding with Cheng Wang, and that's going to be happening here at 6, unless they were telling me that it's not going to be happening here at 6. So stick around, and once I find out what they have to tell me, I'll come tell you guys if it's important. do this whole blockchain sharding talk. I probably butchered your name. Can you say it for me?
Cheng Wang.
I didn't butcher the name. I probably just can't hear how I butchered the name is actually the way to say it. I could Jackie Chan. Okay. So we are going to be talking about blockchain sharding here. So if you're out there and you're interested in blockchain sharding, what it is it a buzzword? Is it more than a buzzword? Is Cheng a buzzword? All the answers to all these questions is going to be revealed. So go ahead and come on in, take a seat. I'm going to pass this off. So why don't we let's give Cheng a big hand.
Thank you for the introduction. Yeah, so first a little bit about my background. My academic background is from number theory and distributed computing. And then I joined the crypto space. My focus right now is a sharding project. It's called RFU. We are trying to deliver decentralized and lightweight scalable blockchain with very fast core shard transactions. So in this talk, I'm going to first give a short overview about the existing research has been done by other projects, for example, Ethereum 2.0 and also some other similar projects with a highlight on the problems. And then I'm going to show you how our project is trying to solve it, resolving all the open problems in the field. So here is a single blockchain. Let's say it's Bitcoin or Ethereum, and we want to improve the transaction throughput. Probably all of you have heard about the scalability trilemma. It says that if we want to scale the blockchain, we need to sacrifice one of the three dimensions to some extent. So actually, if we look at it a bit deeper, there are much more things we need to, or much more dimensions we need to consider and the trade-off for blockchain. So here is a more academic model to analysis blockchain. So we usually say blockchain is a state machine replication system. For state machine replication, it has three parts: data, execution, and consensus. So data part, it has quite a lot of constraints. We need some assumptions about network bandwidth, and also network topology is important. Is a P2P or is a little bit more centralized with different type of nodes. And then it's about the execution. So in blockchain, the execution is first you have the state tree. In Bitcoin is the UTXO set. In Ethereum is the word tree. And so here there are some limitations or bottlenecks. First is the I/O bottleneck. Then the second part is the executing model. You assume that all the commands are executed sequentially, or you want to support the parallelized execution of commands. The third part is about the consensus. Consensus, we need to model to first assumption, give assumption about networks. Some of the projects assume is a synchronous network. Some of the projects assume is a partial asynchronous, even asynchronously. And also security model, we assume majority honest money or majority honest hash power or etc. So the last most important part is for consensus we have the liveness and the safety trade-off. We cannot get both. We have to do a trade-off here. So actually scaling blockchain is a very complicated topic. We have seen a lot of different proposals. Usually when they say we can achieve 1 million TPS, they did not tell you some of the dimensions actually or some of the assumptions actually sacrificed a lot. So here is some methods to scaling blockchain. We first have the centralized exchange. So it definitely could improve the transaction throughput a lot, but the security model is sacrificed, right? And also large blocks. Large blocks could help a little bit, for example, to scale Bitcoin, but the sacrifice is like the network assumption, the network bandwidth, also network. You wanted to assume it to be a synchronous network or it's a partial synchronous network. It will affect the delay. And also there are some methods I will not go through it. But sharding is still considered to be the one of the most promising way to scale blockchain. Why it is like this? Because sharding is the way to scale blockchain by parallelize data execution and the consensus in the same time. The subtext is we want to achieve this by very few by sacrificing very few the other stuff. For example, network assumption. For example, the security model, we want to keep it the same. If we want to scale blockchain, we want to make it still decentralized. We want to make, assume that it's still correct with honest, majority honest hash power, something like this. So sharding has been researched and investigated for quite a few years. We have all almost all people in the field must have heard it and also noticed that the progress is not very well, especially Ethereum 2.0 got delayed quite a lot of years. So here I'm going to give a short review of the popular methods that is behind the Ethereum 2.0 and also some other similar projects, and discuss about the problems. So here is a very simplified picture to demonstrate the idea of sharding. So basically, it's like we in Bitcoin Ethereum we have just one blockchain, and here we have a number of blockchains, and the miners, they don't focus on one chain, but instead they focus on all of the chains. The problem here is the miners are distributed to different shards, then the security is decreased for each shard. So the idea to solve the popular method to solve this is using POS and validated sampling. The basic idea is like we have a big chain, we maintain a set of validators, and then we use a randomized algorithm to distribute these validators to different shards. So here comes the first assumption of this approach. The assumption is basically like this: we have a large set of validators, and we assume that the validator, a very high rate of the nodes actually are honest. It's not just majority assumption anymore. Actually, if you want to assume that it's pretty safe for each shard, you need to assume that around 70% or even 80% of the validators are honest. Of course, it depends on the size of the validators. Another thing is, if the size is not big enough, actually it's pretty insecure. If you, in the beginning when you start the project, if you only have 200 validators, actually you can basically say it can never be secure. So I will not show you the proofs, but basically this is one of the assumptions, and actually this assumption cannot hold in short term and also in long term, because staking service will become a thing. A lot of users, they don't want to run a node by themselves. They will delegate the staking to a staking service, and this will make the assumption also questionable. There's another even critical security issue with this is something called adaptive adversary. It means when you distribute the validators randomly to different shards, actually once the validators they are assigned to a shard, then you can try to bribe the validators in this shard to make an attack. This is very doable actually. If you give incentivization incentives to the validators, by using, for example, a smart contract, you can automate this process. It's very like in practice, it's very doable. Here is a very simple example. If you have 100 shards and 50% of the tokens are staked, actually for each shard you only need to have 0.5% staking to attack it. So this is also a problem. Another problem is about shuffling, because as we say that we need to distribute the validators to randomly to the nodes, and after April, because of the security issues, we need to reshuffle it to make sure that the validators are not in the same shard. Okay. So the problem is shuffling actually has quite some overhead, because when you switch from one shard to another shard, you need to sync the states of the new shard, right? So this means you need to download this. If you only download the latest state of Bitcoin, you need to download like several gigabits. This will take quite a lot of time, given depends on the network assumption. So here the problem is if we try to shuffle it too frequently, then the overhead is too high, right? If we shuffle it too like not very frequently, then the security is an issue, because the validators are kind of static for like half a day or for 1 day. Then you can basically, if you want to attack it, you can take some action in just 1 day, right? There are some ways to ease this problem. One of the solution is to use stateless clients. Stateless clients is a good way to solve this, but the problem is stateless clients is not very practical for the moment. For Bitcoin, there are a lot of researches, but still it's not practical. And for Ethereum, it will be even more tricky, because the smart contract is more complicated. Right now, Ethereum is doing some research using Merkle tree proofs for this, but they are quite a bit overheard, because the Merkle tree actually the depth is pretty high. So whether we can have practical stateless clients in the near future is also open problem. So let's assume on the previous run, the validator run sampling is acceptable. Then let's say we want to do transaction between the shards. How can we do it? So in this model, in the existing approach, people usually use the so-called two-phase commit protocol. Basically, it's like Alice in shard A first. If she want to transfer money to Bob in shard B, it first need to create a receipt. So here she first create a transaction to say that I want to debit this amount of token, this amount of money, and I want to send it to Bob in shard B. Once this transaction is got committed into shard A, then in shard B, Bob could use a proof of the receipt to claim the money. So in this way, it has to at least 2 steps or 2 transactions used. But in practice, actually, is even more complicated, because the gas fee stuff and also security issues. Here, I only talk about one of the issues is about the dependencies of the transactions. Because right now in shard B, the transaction of Bob actually depends on the transaction of Alex in shard A. So this will make because each shard actually could have forks. So then the forks will have complicated dependencies because of cross-shard transactions, and we need to take care of this. If we have like 1,024 shards, the dependency graph could be very chaotic. It will be very hard to resolve the correct dependencies. There are some ways to solve this, but not perfect. The first way is we try to arrange the shards in a directed acyclic graph. For example, in a tree, then whenever you receive something, you don't only check the data of your shard, you also check the data in your neighborhood shard. Then in this way, you can validate actually the cross-shard transaction. Both sides is correct. So this method is the first is proposed by Vlad, but it has some issues as well. Because if you have let's say if you have a transaction from A to B and to C, then basically C cannot validate the original transaction from A, because A is not a neighborhood of C anymore. Yeah, so here is it kind of solves some more problem, but it does not solve it completely. And the second is like you just don't handle it. Depends on the finality algorithm. Some of the system can like claim that they can never have forks, but PLS, personally, I'm a bit skeptical about it. Besides this, we still have two very critical issues with sharding. So the first issue, both of the issues are also related with the dependencies. The first issue is state validity. So it means if something bad happened in one shard, it's very hard for the validators in another shard to notice this. There are some ways to solve this problem. The first one is called Fishman by Polkadot. So basically, it's like you have another type of nodes. You try to monitor the network to check if there's something weird happened in the state, and then once they found it, they try to punish it. But this has some issues because it will introduce some delays into it, and also still there are small some timing window you can take advantage of. The perfect way to solve this is using ZK proofs to prove that something actually happened in that shard. It's a bit like the one I said before, stateless clients. But ZKB, as I said before, ZKB for state validity is also not practical. Another problem is data availability. So in this architecture of Ethereum 2.0 or NeoChain or other similar sharding methods, they always have a main chain. So the main chain, it will not download the other blocks from the other shards. It will only download the block head of the shard. So in this case, the validators actually they can CRUD for a shard and produce one block, but they only disclose the block head to the big chain. So big chain will commit it, but actually the validators they never disclose the full block. This will make the block not available. It basically can make the system hot. Yeah, so we have seen quite a lot of open problems in the current approach. I call this approach as POS plus validator sampling method. Some people call it as commit-based protocol or approach. So what is the issue of this approach if you want to describe it in one sentence? So basically it's transferring from the don't trust verify approach to the don't verify trust approach. So in Bitcoin or Ethereum we download all the blocks and we do the validation, and if something weird then we don't just reject the block. But in this new PLS plus validator sampling approach, it's not like this anymore. You have to trust the validators. You have to trust also the assumption that in each shard actually no more than 1/3 of the validators are malicious, and then you trust what they verify for you. So in the end, each shard actually is is a light node or is stateless node. But we actually, even now today, I don't think like we have practical, mature enough light node that you can have very high security like a full node. So I think this I'm not saying that this approach is totally wrong, but it's still like in the research progress, and many open problems need to be solved. So now I would like to show you how we are going to do this to do sharding in RFU. So we proposed a new algorithm is called a block flow. That's our sharding approach. So basically, there are several points I want to highlight first. So first, we still following the don't trust verify approach. I think this is critical and important to keep a high security. The second thing is we use POW and the UTXO model. Actually, this gives us a very lightweight design. I will explain it. The third point is in our system, the cross-shard transaction just need one step. As I said, that in the existing research proposal is always two-step commit protocol. It will affect the user experience. We have a complete solution for sharding. It's not like research in progress. We are developing this for quite a long time, and we have an alpha system. So it's kind of we have a proof of concept already. Yeah. Now let's show you how we do it. So first we use UTXO model. We first divide all the addresses randomly into G groups. In this way, the transactions, because transaction could happen between any two of the groups, right? So there are G times G possible types of transactions. For example, in the left graph, we have 9 types of transactions from A to B, A to C, A to A, etc. We build a blockchain for each one of these types. So in total, we have G times G chain, right? So what's the beautiful thing about this this kind of decomposition? So the first good thing is, if you want to do a transaction from group B to group A, we just prepare the transaction just like what we do for Bitcoin. And we commit it to the chain corresponding to the age from B to A, right? Then it's done. We don't need to have 2 steps. The second thing is about, so now for group B, it does not need to download the transactions between A to C and C to A, right? Because that's not relevant for group B. And so in this way, the amount of data a single node need to save is reduced to 1 over around 1 of G. But actually, the main challenge is the data dependencies between shards, and with this, it's very hard to reach consensus. You can consider it as like a forked system. So we propose a very specific algorithm called block flow to resolve the forks and to reach a consensus. I'm not going to go to details. Here is a very conceptual description. So basically, it's every new block, it will select very spatial hashes as the dependencies, following very specific rules, so that guarantee that the first thing is guarantee that there's no kind of how to say invalid dependencies, because for example, if one transaction depends on 2 forks of another shard, this is invalid. So we basically should like forbid this kind of dependencies. And then the second thing is like we should make sure that this kind of dependency selection is efficient enough. Because otherwise we can simply choose the latest hash of all the other shards. But this is not efficient, and it also has other drawbacks. Okay, so once we have this specific dependencies data structure, each new block actually could determine a unique flow of blocks. It's like a net, as you can see in the left graph, is like a network flow of blocks, right? So each new blocks using these dependencies to depend on a unique flow of blocks. And then we simply choose the best flow based on the POW proof of work weight. So now for the nodes, they need to validate the dependencies and also transactions. The dependencies validation is something new compared to Bitcoin or Ethereum. So what is the cost? The cost is, so first we need to take time to compute, use some algorithm to compute the dependencies data structure. The calculation could be use very fast heuristic in most cases. And validation is quick. It's much faster than calculation is. Like even I remember it's 2 seconds for G equals 32. Anyway, it's very 2 milliseconds. Anyway, it's very fast. And also we need to have more space to stop these dependencies. Basically, it's several hashes, and actually we can move this to the block body and just include them in the Merkle tree, and then for the light clients, it's not a big deal, and for the full node, this G dependencies is quite negligible. So, in case that if you are not very familiar with the technical details of sharding, so here I want to convince you, like conceptually, why this approach could work. So the first way to look at it is this method is actually a shift from state machine replication to state class replication. State machine replication is just a single blockchain, and here is like we first decompose the ledger to be stored in a small cluster, and then we replicate this cluster, and the size of the cluster will increase from very small to large gradually. This makes totally sense because when the market cap of the blockchain is very small, actually we don't need to shard it quite a lot, right? And then later, when the adoption increases and the market cap increases and the hash rate increases, then we can increase the size of the cluster. And actually, in our algorithm or architecture, it's very easy to increase the size of the cluster. It's not that hard. It could be very dynamic. And the last point is because it's a replication, so it is still follows the don't trust but verify approach. So we don't have all the problems from the POS plus validated sampling method. We don't need to trust validators. We only trust ourselves. And also in some cases you can even, but this is optional, you can even trust your friends. You can connect to your friends to form a for ledger. I think this is much more like acceptable than you trust the random validators. I mean, but this is optional. You can still run very small clusters, because in the early days when market cap is very low, the cluster is like you can even hold it with one node if your computer is powerful enough, or you can decompose it to run like several lights, very cheap nodes in Amazon. It's fun. Another way to look at this approach is we can analogy this to the computing model. We all know that the computing model evolves from sequential computing to concurrent computing, basically multi-threading, and then distributed computing. You have a set of computers. Each computer could do concurrent work, concurrent computing. So in blockchain, actually, we have the single blockchain, Bitcoin, Ethereum, and then we have some proposed DAG-based blockchain. But actually, most of the DAG projects are not designed properly. And BlockFlow is, you can see, is a distributed DAG blockchain. So it's very much like the distributed computing evolution. And this is also give us, we kind of learn from history, give us confidence. That's why it makes sense. Yeah, that's all. And if you are interested in more about details, you can go to visit our website or follow me in Twitter, ask me questions later. And tomorrow I have another talk about how to reduce the energy consumption of proof of work. So if you are interested, please come to have a look and ask me questions. Yeah.
Thank you very much, Cheng. We don't have time for questions, but will you be able to take questions off stage over here? Yeah, so he's going to be over here. If you would like to ask him some questions, we're going to get set up for our next talk, which is Monero Bitcoin atomic swaps. That's a big buzzword. Everybody likes to say atomic swaps. So we're going to get that set up. We're going to be back here in a couple of minutes. Yeah, stuff was going down, huh? Oh, pretty interesting. I mean, can't be C3 without at least one something or other going down. So we'll be back very soon. Bitcoin, Monero, atomic swaps. This is what we're going to be talking about. Two more minutes. I'm just going to stay here with my my hand up here until they give me the OK sign. This audience is ravenous. They're going to consume me if we don't get this going up very quickly. They're already... I have to kick them off the stage like zombies. So let's get this up and going. It's just a couple of minutes, guys. It's okay. It's okay. Calm down. Somebody else can go get me an ice cream like that previous guy. He's my favorite. You're my favorite. The ice cream guy is my favorite. If you two can become my favorite. All it takes is one ice cream. Just go into the next talk before we're ready. And I'm just trying to keep them on their toes. Otherwise they get lazy. They kind of just put their feet up and they're like, nah. But they're like, oh shoot, they're already started. Here's the record. Here's the stream. They don't get a lot of cardio on the day-to-day, so I need to make their heart pump really fast for a few minutes. These guys are ready. These guys are ready. We're almost ready. Everything's almost ready. We're ready. See, it all came together in the end. So I would like to introduce Hashed and Zcow. They're going to come up here and talk about Bitcoin, Monero swaps. I'm going to pass this off to the two of them. Do you guys want two mics, or are you okay with this one? Oh, just you. Oh, you're gonna they're gonna do atomic swaps on stage. They're gonna do an act. They're gonna. I was gonna say something cool, but then I butchered it. So I'm just gonna pass off this mic to them and let them take it from here.
Hello, everybody. So 2 years ago, we were here sitting between the Monero and Bitcoin. We were sitting between the Monero and Bitcoin tables, and I was talking to Polto, and Polto suggested, why don't you try to work on a BTC Monero atomic swap? And we started. We didn't think it was possible, but well, after 2 years, we have something more concrete. And we would like to talk about it. So, a lot of people got into Bitcoin because they thought it was like an anonymous currency. So, like, for example, this tweet from 2011 from WikiLeaks. WikiLeaks now accepts anonymous Bitcoin donations on this address. As we know, Bitcoin is based on outputs, and you can trace. So this is a Bitcoin transaction. These are two outputs. These are the UTXOs. And so here this output gets spent on this transaction and produces output that gets spent on this transaction and produces output. So you can link these three outputs together, so you can trace all of everything. So here's another example, which is a little bit more interesting because here you take one output, you split in two outputs, and then you merge them back into one output, which means like it's the same person. So, like, this address here is this address here, and these are all the addresses that send money to it, and the size encodes the volume that pass through those addresses. And what is it? So you see these three big addresses. These are probably businesses like exchanges, and of course you can de-anonymize people if you can trace it back to such a big hub. So the Bitcoins cannot be easily tracked back to you, which was what was in WikiLeaks website. Well, not true at all. So how do you avoid traceability on Bitcoin? You can't. But if you have a way to trustless swap Bitcoin to Monero, for example, then you can. So, and it's very important that this has to be trustless, because otherwise you need identities, and then it's like, then you're not anonymous anymore. So the basic idea of cross-chain atomic swaps is that, like, Bob has, for example here, Bob has Bitcoin, Alice has Monero, and you either want this transaction to go through, like, meaning Alice in the end ends up with Bitcoin, starts with Monero and ends up with Bitcoin, and Bob starts with Bitcoin and ends up with Monero. Both have to go through, or none have to go through. This is the atomicity of the atomic swap. So why Bitcoin Monero? So Bitcoin is the real thing, but it's traceable. Monero is untraceable. So Bitcoin has a large market cap. People use it a little bit. And additionally, just like as a side note, is like many users are unable to move their coins. So if 10% of Satoshi coins would go into Monero, like, the market cap doubles already. So again, like, atomic swaps are trustless. There is no trusted party involved, so anonymous trades can happen. So we are here presenting today because we started this project here, and there are some things that we didn't work out. For example, we need a zero knowledge proof that we don't know how to do, and we would love to have help from the community. additionally, a few libraries got developed on this work, and it would be great if to get community participation and community contribution to these libraries. With this, I will pass to Hashed, and he's gonna go through the protocol carefully.
So right, left, and this one. Yeah. Thank you. Hi, everyone. So I will cover a bit in detail the protocol, but before starting, let's talk about the scenario. So here we have Alice that has some Monero and she wants Bitcoin. Bob has Bitcoin and wants Moneros. They already agree on the price and the quantity, and they want to trade, but they don't trust each other. And in the protocol, we assume that one can be malicious. So first, I need a bit of notation and little math, and I promise it's very little, but it's the boring part, but the fun part will come just in a few seconds. So first, we denote Bitcoin private key as BY and BI, and I can be either A or B for Alice and Bob. And we use capital B for the Bitcoin public key for Alice and for Bob. For the Monero keys, we denote the private keys with small k and small kv and ks for the private view key and the private spend keys. And we use capital K again for view and spend keys for the public keys. So we can define an account with a pair of 2 public keys, and we can parse an account with the knowledge of the private view key, and we can spend from the account only if we have the knowledge of the private spend key. And for the protocol, we defined partial keys or shares. And we denote a share with a share for the spend key with a small a and small b for Alice and Bob. And we define the full spend private key with just an addition modulo L. And that is a parameter for the Edward 25519 curve. And last slide on the boring part, notation. When we say KSA capital A, we mean that KSA is known by Alice. It's for the next graph. We use this small a, big capital A and capital B for who knows what secret. So now we can go through the protocol, and here is the fun part. Here we assume that first, because they want to trade, they both completed the initialization and locking phases. I will go in detail about these 2 phases later, but now all the parameters are initialized and the funds are locked, and we can start the swap. So what's happening is Bob. Sorry. Bob knows some secrets, and he will share the secrets to Alice. So we move one step. Sorry. Yeah. So we move one step. We do the transition in this state diagram. We do one transition. We do the start, and the knowledge of S is shared with Alice. And now Alice have all the prerequisites to do the buy action. So by doing the buy action, the Bitcoin that have been locked are transferred to Alice on her Bitcoin wallet. And as a side effect of this transaction, this Bitcoin transaction, we on purpose we leak some information, and in that case is the knowledge KSA that was known by Alice was leaked during this transaction, and now KSA is known by Bob. And because Bob knows KSA and KSB, he can reconstruct the full KS key, private key. So we have the locked Monero. We have the knowledge of, Bob has the knowledge of the full spend key, and he can get the Monero. So basically, we just leak one part of the private key depending on the path in the protocol. So that was a quick overview of the successful path of the protocol. I said before that the protocol is decoupled in 3 main phases. First, it's the initialization. In the initialization, we will generate all the parameters that need to be specific and common to each party. And we will also, in these phases, generate the zero-knowledge proof. I will talk about the proofs a bit later. And when this is done, we can create the different transactions that will lock the found. And when the founds are locked, we can start the swap. So after the lock is done, we are in this state, and we can proceed to the swap. So in reality, the swap phase is the smallest and simplest phase. So first, the protocol initialization. We generate the view and the spent partial private keys. Each generate these private keys and derive the associated partial public key. Each generate a pair of Bitcoin keys. They compute a hash of the private spent shares. And Bob compute a secret and also the hash of this secret. And then comes the zero-knowledge proof that I will talk about it later. And they exchange the private view key because they want to have the view of what's going on the Monero blockchain. They share the spent public keys. So they can, with this information, they can have the locking address for the Monero part. They both exchange their Bitcoin public keys, and they share they share their hashes and the zero-knowledge proofs. And after sharing this information, each verify the zero-knowledge of the other party. And if everything passes the validation, we are good to go for the lock phase. So the locking phase for the Bitcoin side requires 2 transactions. If you are familiar with payment channel construction, it's a kind of standard construction, and here we have a first Bitcoin transaction that lock Bob's Bitcoin and have at least one UTXO that has this script, and the script will allow for the buy action, or allow the refund if the swap is cancelled. And if the refund is chosen, this transaction will again allow 2 different paths. The first is the refund is completed, so each gets their money back minus the fees on each chain. And the fourth path, the third path is created as an incentive mechanism to force this one. If in that case, Alice will get the Bitcoin without revealing any information. Here we can see that HA so the hash of one of the secrets, is leaked during the transaction, because we will need to reveal the secret that will correspond to the HA. Here we will leak the secrets from Bob, but here we don't leak. We just wait and we can get the Bitcoin out. So we did that because we can have a deadlock if nobody acts here. I will talk about it a bit more later. So that was the 2 Bitcoin transaction. Now we have 1 transaction for the Monero parts, where we move Alice Monero into the address that correspond to these 2 private keys. And this address is again generated in the initialization phase. So here we can see how Alice can buy the Bitcoin. She can sign with her key. She needs the secret S that is generated from Bob, and she leaked the secrets. Here we can see how Bob can refund and then cancel the swap. We see that he has to sign and he has to reveal his secret parts. And here we see that Alice can claim the refund without revealing anything, but after some time lock, so if Bob doesn't react, he will lose. So this forces Bob to react when the refund is triggered. And for the swap, here it's basically the same as the graphic we had before. So we see the S secret that Alice needs to know to trigger the buy. She needs her own private secret. She needs the Bitcoin transaction, and this will consume and transfer the Bob's Bitcoin if she do the buy by revealing to Bob this information. So what happened if Bob never shared this S parameter? After some time in the first transaction here, after some time this refund can be triggered. So if Bob never share the secret to Alice, and we are still in this state, the refund can be triggered. And with the refund, Bob should directly spend the refunds, or Alice will be able to claim it. Now, what if Alice doesn't buy? Bob shared the secret, so Alice should be able to do the buy, but she doesn't do anything. Then Bob also, after the first time lock, can do the refund and directly spend the refund to get the Bitcoin back. And by doing that, he will reveal the secret, and then Alice can take her Monero back. And now if Bob doesn't refund, again, we have the claim from Alice. That is the incentives to Bob to refund. And that's the full protocol. Now, the non-limitation or open problems we have still is the zero knowledge proof part. So what we need to prove is that the secret we will reveal on chain is really related to the hash and to the public key we send in the initialization phase. So we can show it like that. After the initialization, what is exchanged is the point on the curve that is used to get the Monero address. The 2 points are added to get the full address, and the hash that is used in the Bitcoin transaction. And it works because we want a relation between those two. we want a secret that will end up to the hash and that will end up to the point. So this is the zero knowledge proof that we need. Thank you everyone for attending the talk. We are like really open to have any feedback or community contribution on this paper or the libraries. And if you wanna reach us, we also have a Petrinet that represents the whole protocol, and you can play with it. We will also release a small video where the Petrinet is a bit more explained. Here we put just like a partial view of the system with the graph. So yeah, feel free to reach us and chat about it. I don't know if we have time for questions. Yeah, we have time for questions, so any questions?
Hi, thanks. Is it possible to see, like, once the transaction is done, that on the Bitcoin side I participate? Is it possible to see that I participated in this cross-chain atomic swap?
So what you can analyze on the Bitcoin chain is you can see this script. If the swap goes through directly, you can see this script with this transaction that will reveal the information. So that will be for sure in clear, and you can match everything that has this pattern. This will reveal an information about the Monero part, but this information is not enough to get anything to do any relation to the Monero part. So here you can maybe assume that the person is not the same anymore in the Bitcoin part. But that's the only information you should be able to get.
So these Petrinets, like, they really model the whole protocol execution. So if you, because it's a bit, we could not make it simple enough to be able to display it here. But if you want to visit any possible path of the protocol, come to us and we're going to play the Petrinet, and you're going to be very clear, like, every potential protocol execution that can happen. So we did this yesterday with the help of Statebox, and we thank them for that. Okay, thank you.
Hello, everybody. I'm stepping in for our lovely host, Diego, and give him his first break of all of the CCC. And thank you for your talk, Joel, on atomic swaps between Bitcoin and Monero. And I think we're ready. We have 5 minutes. Oh, great. I get to kill some time up here. How's everybody doing on the third day? You guys? Whoop. Okay. Good. So we'll kill time. This is the hardest part of your job. Is it still working? Nope. Okay, good. So we have a 5-minute break. I won't necessarily kill all the time. I'll come on and kill a minute at the end. All right, so we have, is everybody ready? Come on, sit down, come on in. Anybody want to come into a great talk? Come on in, sit down, enjoy yourselves, get comfy. Our next presenter, next speaker doesn't necessarily need an introduction if you're from the Monero community, and if you're not, you're in for a treat. We've got Riccardo Fluffypony coming up to talk about his recent project Tari and about the Monero ecosystem itself. And I had the pleasure of meeting some of your Tari team at DEF CON this year, and they were great people, and I also think what you're doing is really good. So it'll be good to hear this talk, and enjoy, everybody.
Thank you. Hello. That was unexpected. Hello, CCC. Welcome. So, my name is Riccardo Spagni. You may know me as Fluffypony. For many years, I've been the lead maintainer for Monero. Now I'm just a maintainer. I don't know what that means, but it means I'm no longer lead. And for the last little while, I've been working on a project called Tari. I started a company called Tari Labs with two co-founders, Dan Tari and Naveen Jain. Naveen's over there in the back if you want to go and pester him later. And what I want to talk about today is what Tari is, how it's being built and architected, and what that means for Monero, and why anyone in this audience should care. So to start off, what is Tari? Now, obviously, as you guys know, we already have a really cool privacy cryptocurrency, pro-privacy cryptocurrency called Monero. So Tari is not a pro-privacy cryptocurrency in and of itself. It's a lot more than that. Tari is a privacy Trojan horse. And I'm going to talk about this a little bit. I'm going to talk a little bit in detail about how Tari is a privacy Trojan horse. But let me first explain what Tari does. So Tari is a decentralized assets protocol. Now, it's being architected as a merge mine sidechain with Monero, and I'll touch on that in a second. But digital assets are really interesting things, because digital assets are things that live their life digitally. So a physical asset would be something like gold, right? I mean, that's a physical thing, we understand that. But a digital asset, from start to finish, remains digital. So examples of this are in-game currencies or in-game assets. So if you play EVE Online or you play Fortnite and you have a Fortnite skin, that Fortnite skin never lives in physical form. The same goes for loyalty points. If you fly Emirates and you get Emirates loyalty points, you don't get like a physical check in the mail that says, well done, you've got 1,000 Emirates loyalty points. Those things live digitally from start to finish. Same goes for things like security tokens, digital collectibles, and software licenses, of course, an interesting one as well, because you buy a piece of software, you pay your license fee because you really need this text editor or whatever, and then you activate it and it phones home and activates the software, and then the company shuts down in 2 years' time and you can't use that software anymore because it can't activate. So if those were expressed in some sort of decentralized way, you would always be able to activate that software. And this is, just as a sidebar, this is really interesting to me because there are a bunch of games that I played when I was younger that required online activation, and those companies have since gone defunct. And you fire up Windows XP VM, and you're like, I'm going to play this game. Memories of my childhood. I'm playing Command & Conquer Red Alert. Such good memories. And then it's like, dialing into, Westwood for activation. Activation failed because the website doesn't exist anymore. So there's a lot of cool stuff that we can do. Even like DRM. Recently, Microsoft closed Microsoft Books, and they were like, all the books you bought? Yeah, you don't really own them. You just lost access to them. And that kind of sucks. I mean, DRM in general sucks. But I mean, wouldn't it be cool if we could do DRM at least in a decentralized way so that when you buy a token to access the thing that is yours because you bought access to it, that you always have access to it. So these are things that I think about that Tari could solve. Now, how's Tari being built? And I think this is, obviously a very critical thing. Tari is being architected, as a merge mine sidechain with Monero. There's no white paper. Over the past year and a half, we've spent a ton of time with the community, with the nascent community, really building out the RFCs, building out the architecture, figuring out what this thing's supposed to look like. The only decisions that we started off with were we wanted the base layer to be Mimblewimble, and we wanted it to be written in Rust. There are very specific reasons for this. One of the reasons was Mimblewimble is really scalable. I think Mimblewimble personally is a scalability technology with some privacy benefits. I don't think it's a privacy technology. And I think Rust is just a fantastic forward-thinking language. And one of the main reasons that we've built Tari in Rust is because we didn't want to steal any resources from Monero. We didn't want Monero developers who are C++ developers to go, ooh, shiny, cool new toy, I want to work on that. So that's been very specific things that we've, or very specific decisions that we've taken. We also have actual use cases, and we have good design as building blocks, and we'll get into design a little bit more. Now, in terms of how we've architected things over the past few years, we've had discussions on Freenode and the Tari dev channel, twice a week, architecture discussions. We've captured those, written them up, and these have been totally open. We've taken input from tons of like Monero developers, from Rust developers, from other open source communities, just in terms of how we should be building this thing. And we've built a whole set of RFCs. You can see them on rfc.tari.com. And the RFCs are still open. There's still some that are work in progress. There's a repo on the Tari project GitHub. And you can go in and you can say like, oh, I think that this should be done differently. And I mean, that's, it will be done differently. Obviously, the truth is in the code. So RFCs have a limited lifespan. At some point, the RFCs are no longer viable in terms of defining what happens in the code base. And so we've been writing code for a while. We're almost on 1,000 commits on the core project. Woo. And I think that's pretty important because things are really starting to come together in terms of things like the comms layer, which is basically entirely built. We're starting to be able to process transactions and blocks. We're starting to be able to find consensus, when we're merge mining and that sort of thing. So it's really coming to a point where things are taking shape in a very real way. Now, I've told you a little bit about what Tari is and how it's being built, but why should Monero care? I mean, apart from the fact that it's a merge mine sidechain, like, who cares? So the first thing I want to talk about is what Tari gets from Monero. We get an infusion of community members. We've had a bunch of Monero community members that have stepped up, that have gotten involved in various aspects of Tari. We have a great technical sounding board on the Monero side because when we want to do something that, when a little bit uncertain of, we can bounce that around and we can say like, hey, MRL or hey, Monero devs, what do you think about this? And then they can be like, that is the dumbest idea I've ever heard. And we go, okay, no problem. There's also a great carrying over of Monero principles. So Monero has a lot of things like on the Monero subreddit, no one talks about price. And that's a principle that we set like day zero. And there's a separate subreddit where people talk about price. But newcomers don't hit the Monero subreddit and see a bunch of like to the moon memes. They don't see a bunch of people talking about the price went up, the price went down. No one cares. People are there because they want privacy. And so with Tari, we want a lot of those principles to carry over. Skepticism Sundays is another great principle of Monero. It's a subreddit topic that happens every Sunday where people go in and talk about why Monero is going to fail. I think that's an awesome attitude to have. Let's be skeptical. Let's talk about all the problems that are facing Monero, and I want those principles to carry over to Tari. We might have to call it something other than Skepticism Sundays, like Terrible Tuesdays or something, but we'll figure it out. Obviously, we leverage Monero security model because we're merge mined. And then you just heard from Hashed on atomic swaps between Bitcoin and Monero. So we have similar ideas, either to use that directly, or there are a couple of blind merge mining atomic swap-based mechanisms that would allow us to have atomic swaps between Monero and Tari. Now, what Monero gets from Tari right now, and this has been happening over the past 12 to 18 months, Tari Labs currently pays for the Monero CDN. The CDN is very important because the CDN that we use is expensive. It's like $4,500 a month, but they have over 19 points of presence in China. So that means when a Chinese citizen wants to download Monero, they don't go through the Great Firewall. They download it locally in China without ever touching the Great Firewall. And that's pretty important, especially for open access to citizens of a country where the governance is, let's say, a little bit overreaching. We also have a slush fund that we use to contribute to CCS proposals. So we try and use that to finish proposals that are struggling. We also try and give it an injection to new proposals. So when someone comes and says like, hey, I'd like to do this thing, or I'd like to spend another 3 months working on Monero, and it's going to cost X amount, then we try and give as much as we can out of that slush fund. We're also strong supporters of the MRL. We believe that the Monero Research Lab is the lifeblood and future of Monero, because privacy is a cat and mouse game. You don't finish privacy. You don't go, well, we're done and now it's private and the NSA can't touch it. You keep pushing and they keep pushing back. So we've sponsored things like biannual MRL workshops where members of the MRL have gotten together in a central location and been able to really workshop new ideas and brainstorm things about things that could advance Monero's privacy and scalability. Now, why should anyone care? I mean, this is cool. You know, Monero gets some stuff, Tari gets some stuff. The thing is, and I mentioned this earlier, Tari is a Trojan private horse. Privacy Trojan horse, that thing. And the reason is because Monero is amazing, but it's evident now that people either won't use it or can't use it. Now, we can fix the UI problem and the UX problem. There was a great talk on that, on some of the advancements that are being made to Monero UX. But the reality is, most people don't realize they need privacy. This is not a thing we're going to fix. You know, you can go like door to door, knocking on people's door and being like, you need privacy, and they're going to go like, no, I don't do anything wrong. And it's true, they probably don't need strong privacy until they do. So I've spent the past 5 years advocating for people to understand why they need privacy, and I just haven't seen a shift in the market. I've seen a shift in some things, like I've seen Apple start to embrace privacy. That's great. That's fantastic. But I'm not seeing that wave that I was hoping for. And so we need to trick people into using privacy-enhancing tools. And one of these companies that are doing this really successfully, as I said, Apple's one of them. They're tricking people into using privacy-enhancing tools by making like a device that's really easy to use that people want, and they don't realize that they're getting the benefits of strong privacy. They just want the latest iPhone. Same goes for like Mozilla. Firefox is starting to do really good things on the privacy side, and people just use Firefox because it's a good browser. They're not using Firefox because they go like, oh, I need, you know, a Tor tab. They're going, I need Firefox because like Chrome sucks, or, you know, like Google's evil, and so therefore. Or like, you know, my system administrator pre-installed Firefox and hates Edge. And that's great. They're tricking people into using privacy-enhancing tools. So Tari can get them into an ecosystem where Monero is accessible to them. How? I'd like to show you a video. And this video is of an example of some of the stuff that we're designing, some of the resources that we're bringing to bear to make Monero accessible. So this is an example of digital collectibles on Tari. It obviously doesn't exist yet. So imagine a Monero Enterprise Alliance app. Just imagine it, I don't know. And you have this cool collectible in your Monero Enterprise Alliance app. This is a cool flaming Monero. It's the year 2023 edition. I don't know why we chose that year, it's so weird. And you can see it's got an estimated value in Monero based on its rarity and a number of other factors based on how much people are willing to pay for this particular one. It's 1 in 500, so we're able to do cryptographically, we're able to prove how many have actually been issued. And that's obviously pretty important as well. And then, you know, this is legendary because it's 1 in 500. There could be different classes of collectibles, but this one's legendary. And then we can set rules. So in this particular asset, we've set a bunch of rules like Fluffypony and the NSA will receive 5% of trades because we want to keep them happy. Collectibles may be used in authorized applications, especially those owned and operated by state actors, because wouldn't it be funny if the NSA had to use a Monero thing? And then iconic edition collectibles may be redeemed for a meet and greet with Fluffypony. Hey, what's up? So these are examples of rules. Obviously, these are jokes, but the reality is rules like being able to earn 5% on trades, that's a pretty like big deal. And I'll explain why in a second. You see, a lot of the things that you build digital collectible engines around, or you build things like in-game assets and in-game tokens around, are based on things that are held by copyright holders. Now, copyright holders, especially in the USA, but also in Europe, are incredibly powerful. They have been able to extend copyright law in the USA that had lasted for 120 years after the creation, even if the person who created it died. Now, I mean, that's just nuts. I mean, that is a crazy change in regulation. How have they been able to do that? They've been able to do that because we're talking about incredibly powerful companies. We're talking about companies that own artists, that own movies, that own TV series, that own musicians. They own, we're talking about really big companies. So when they go, copyright law, 40 years isn't enough. We need 120. Then regulators go, cool, rubber stamp, doof. Now imagine if those companies use Tari. And we're able to facilitate a lot of that because of the way we're building Tari and because of the things that we're building on top of Tari. Now imagine if those companies go like, yes, we want to use Tari. They're going to go, hey, but we want to do so privately, because they don't want to expose what the 5% is that they're getting on that rake. They certainly don't want to pay tax. So they're going to start embracing a lot of the privacy aspects of Tari and of Monero. And they will start pushing regulation that is pro-privacy because it serves their interests, because they're making money from things that are built on top of Tari. Now, that's not all, because Tari believes, and the Tari Labs at least, believes that Monero is a critical part of this infrastructure. So we're committed to giving radical support to Monero research and development. And one of the ways that we hope to do this is by creating something called a dev center. So dev centers we hope will be physical. In other words, in several cities around the world, there will be actual dev centers. And then online as well for people that aren't able to go and go to a physical dev center or don't live near one or whatever. Researchers and developers we hope will be able to apply for grants, and they will go, yeah, okay, there's this really cool thing I want to build. It's a mobile wallet for Monero that uses fuzzy waffle technology, and in order to do that, it's going to take me 6 months, and it's going to cost X, and I need my designer guy to work with me as well. And then there'll be a grant committee, which we'll set it up as something that's like really broad. They'll be able to facilitate these grants, figure out how they're apportioned. This is, of course, work in progress. We don't have like the perfect model for it. It's a few years out at least if it's going to happen. But we think that this could be a really cool way of pushing things forward. The CCS is incredibly powerful, and we don't expect this to replace the CCS on any way or on any level. But we think this could be a really cool way for people to be able to bring teams together and say, hey, I want to build this thing for the Monero ecosystem or part of the Monero core software. It's going to take me 12 months. It's going to take me 18 months. I need to have like the ability to do that and know that I'm going to get paid. My team needs to know they're going to get paid. So there's a lot of cool stuff that we can do with dev centers. So I hope that this gave you guys a bit of insight into what we're doing with Monero and Tari, how the two ecosystems interact and interoperate, and why this is important, how Tari can be a private horse, a privacy Trojan horse, I'll get it right eventually, and how that can really bring privacy-enhancing technologies into the lives of ordinary people, or normies as we call them, and how we can trick them into using privacy tools. Thank you very much. I'll take a few questions. We have a few minutes still. Oh, good, no questions. Oh, that's the best. Cool, there's no questions. Awesome. All right, catch me later if you guys want to ask anything. I'm happy to talk. Thank you.
All right, thanks for that. I think, do we have a break or are we just rolling into the next one? Still going? 5 minutes-ish. So we'll have 5 minutes break. We'll see, I'll get the next speaker up here. We're gonna go into moving into Bitcoin to the post-quantum world, which sounds very exciting. So, no, it's not happening? Yeah, that's the next talk that we're going into. Oh, there's 2 away. I'm not doing so great at my moderating here. I'm just learning from the audience as to how to do this. Okay, we've got the next speaker. I'm going to better introduce it in a minute then. Maybe I'm just excited about the post-quantum as well, but I'm just as excited over here. ready for the next talk, which now I know the schedule of. I got the correct schedule, and I'm genuinely also excited about this one because interoperability is a very, very important subject, and it's very, very current in terms of how we're going to actually bring these technologies together and how we're going to transfer value between chains. So Kostas is here to do this talk, and everybody give him a hand and welcome him on stage.
Hi everyone. This is fine, I guess. Okay. Cool. My name is Kostis. I work at IHK. I will be giving this talk with my colleague Dionysius Indros, who is a PhD student at the University of Athens. So I guess let's start. I also have a clicker. Yeah, that's better. Okay, so in this talk we'll kind of have a discussion about what a sidechain is, and there were some talks before that were talking about sidechains, but I will probably redefine what a sidechain is. And then we will basically see how we can build on top of a sidechain to build a two-way peg, which is basically an asset that is shared through different different chains, basically. And then in order to do that efficiently, we'll see proof of work, which Dionysius will present. So let's quickly talk about sidechains. This is actually a very nice diagram here, which shows two chains which are completely not related to each other, like they have different genesis, and we can see that this white block basically depends somehow on this black block, which is on another chain. And this is kind of the theme here. We want chains that are completely heterogeneous and different to be able to kind of see information about each other. So what happens here? I'm going to use as an example Ethereum and Ethereum Classic. It's easier this way. And so what we have here is these chains, like they grow over time until at some point some event happens, which we denote with this frog. And this event happens on Ethereum in this case. And then what we want to do is basically say, okay, we would like to know about this event on the Ethereum Classic chain. And here we denote the fact that we know about it with another frog. And we basically can react to this event in any way we could react to this event on Ethereum. So this is like the big idea about interoperability, right? We want to be able to react to an event on another chain. So we have some terminology here which will be useful to go through. Then we have, in this case, the Ethereum is the source chain, like the chain in which the event originates. And Ethereum Classic is a destination chain. We also call it a target chain. And so basically, here we have some requirements for this. We would like for the blockchains to be proof of work, but it's not a strict requirement, but this is a case we're going to look at today. And we have some examples of some cryptocurrencies that are proof of work. And then in order to do some of the more advanced stuff that we want to do, we also have the requirement that the cryptocurrencies also support smart contracts. And we are going to do some advanced stuff that will really take advantage of the smart contract capabilities. And this is kind of a departure from all the previous talks, which were kind of about Monero. Monero doesn't really have smart contract capabilities. So this is, I guess, a nice change of pace. When I showed the frog there, it's like it wasn't really obvious what it represented, and so we'll make it more specific. An event can be something like, okay, this transaction happened on some chain, or this block was mined, which I don't know has this particular property. Its hash has like 7 at the end or something, or changes in the account balances. And other kind of events like Solidity events. So for those of you who don't know, Solidity has events that can be fired and they're recorded permanently and they can be used by other applications. And we are actually going to make heavy use of those Solidity events. And now there's another thing which is important, which is, okay, someone could say, I can do this by having the miner on the destination chain, observe the source chain, and he can confirm, or they can confirm, what happened on the source chain. But we don't have to, we don't want to place this burden on the miner, and we actually, what we try to do in this work is we try to say, how can we do this without actually affecting the base layer, without requiring changes, consensus layer changes. So we have a property which we call miner isolation, which is very important, and what I'm going to present is actually does have this miner isolation property. So we are going to start with a smart contract, which is called cross-chain. This slide here shows that this is actually on the destination chain, and we're basically going to, like, our work in this will be to tell the smart contract that some event happened on the source chain, and this all starts with, like, all the smart contract knows is a genesis of the source blockchain. This is all the information it needs in order to operate, and this is what we denote here. So we kind of construct this smart contract with the genesis of the source blockchain. Now, we saw what an event is. Now, we'll see how we can prove such an event happened. And we have two important pieces. One is the event itself. Like, we want to have some description of the event. And another is a proof that the event happened. And when an event happens, it gets stored so that we can use it for other things later. And we'll see how we can use it. We will actually make use of it. So what does a proof look like? For now, we will look at very simple proofs, which are SPV, like if anyone's familiar with the term, which is basically some event that happened basically took place in a block. So I want to prove to you that this block is actually in the best source blockchain, and this event or this transaction is included in that block. So the way I do it is I provide to you the chain of headers, and I provide to you a Merkle proof of inclusion for the block that I'm interested in. And this is not what we're actually going to end up with. This is not, like, incredibly efficient, and there are ways to improve it with hyperpowers, which Dionysus will present in a bit. But this is not enough, basically, because so the information this contract has is very limited, and someone could lie about it. Someone could provide a valid chain that contains some transaction that is actually not in the best source blockchain. And how we avoid that is we say, okay, you claim now that this happened, but we will start a contestation period, so that if someone disagrees with you, we will provide them with the opportunity to say, okay, I disagree, and this is why I disagree. So they will provide a contesting proof that basically your proof will be compared against, and if it is found out that the person who contests is right, they basically gain some collateral. Otherwise, like, nothing happens. And when the contestation period ends, I'll circle back to the collateral thing because it's more important. The important part is here that you have fraud proofs in case the first person was lying. So this is, again, now a recap of the SPV protocol. So we have two provers. These are actually parties that submit things to the smart contract, and they submit their chain, the header chain, and both submit the chains, and they are basically compared. In this very simple scenario, the comparison happens by checking which chain is the longest, but it can also be which chain has the most proof of work, which is in Bitcoin, and so on. So let's look at the contract. This is a function that is, I hope this works. Okay, this is good. So this is a function that gets called on the smart contract when someone wants to say, okay, this event happened on another chain. And it has a proof, which is this pi, and it has the event that basically happened. So the event could be, this transaction happened to this address. And then the important thing is, before we go there, the important thing is when someone does this claim, they also have to put down some collateral, which can be taken from them in case they're lying, which is the thing I wanted to circle back to. So this if statement here is it verifies that they have actually put collateral, and then we basically store this event. that they say, okay, this is the author, which is the person who called called this function, and this is a proof that they use. And then we say, okay, now a contestation period begins, and it will end after k blocks. So this is a whole function. It's called submit event proof. Now, okay, now again, when someone wants to contest it, they have k blocks in which they are able to do it. And again, if they're right, they pay the collateral. They get the collateral as reward. Otherwise, if no one manages to disprove this event, then the original the original claimer gets this collateral. They get it back because they are the ones who put it. And so yeah, so there are some conditions this collateral should satisfy, which is basically at the very least it should cover the cost of submitting and the cost of monitoring the source chain. Now, yeah, submitted and monitoring not only the source chain but also a destination chain. So let's see this function as well, and let's get over it quickly. So basically, we have a check that says okay, this event exists and we are still within its contestation period. And now the comparison happens, and basically the two proofs are compared. So this is the existing proof, and this is the new proof, and then this is a scenario in which the original proof was actually fraudulent, and so it gets cleared up, and the person who submitted this contesting proof gets collateral. So when this happens, we basically assume that someone claims an event, and correctly so, because the event actually happened, but time passes and then the contestation period ends. So we have a way for the original claimer, or basically anyone else, to say, okay, now the contestation period is over, nothing happened, and let's finalize this. Oh no, actually the author does it. I'm sorry. Correct that. The original author has to do it because they have to get back their collateral. So when the contestation period is over, which is verified by this, the original claimer calls this finalize event function, and then basically their event gets added to a set of finalized events, and the author gets collateral back. And this is the happy case. And then this smart contract, which is basically, we've been talking about one specific smart contract all like during this talk. This cross-chain smart contract we will use as a base for other smart contracts, and it offers this nice API which says, okay, we have this event exists, and you pass it your event that you're interested in, and it can tell you, did this event happen? And in this way you can know. So now that we have that in place, let's look at how we can make a two-way peg. And let's first look at what a two-way peg is. So imagine you have some Ethereum on the Ethereum chain, and for some reason you really want to use them on Ethereum Classic because, I don't know, because you feel the transactions there are cheaper, or you have some reason, or you want to use them at a DEX, which is at Ethereum Classic. It doesn't really matter. The point is that you have some reason that you want to use this Ethereum on Ethereum Classic. So what you want to be able to do is say, okay, I now transfer this asset to Ethereum Classic and then use it as a like. I use it as a regular token. I send it to people. I send it to smart contracts. I do whatever with it. And then you basically want to say, okay, when I'm done with it on Ethereum Classic, I want to return this on Ethereum and keep using it there if I want to. So this is what a two-way peg is. And now let's look at how we make it, basically. So we have two smart contracts to do it, which both inherit from this cross-chain smart contract I showed already as a base. And the first smart contract is this X, which is on Ethereum. And there's a second smart contract, which we call Y, which is on Ethereum Classic. So the Y smart contract it basically represents an ERC20 token that mirrors Ethereum on Ethereum Classic. So what we want to make is you basically have a token that when you have it, it's like you have one Ethereum. And the way you get this token is by, the only way to get it, except if someone sends it to you, is by basically freezing your Ethereum in the smart contract X. When you do that, like your Ethereum in the smart contract X is locked, and then if you have some Ethereum tokens, some ETH20 tokens as we call them, on Ethereum Classic, you can basically take them back on, you can recover them on Ethereum by destroying them there. So this is like the same slide as before, but with the details we have now. So basically, if I have Ethereum, I move them in this contract, and then I somehow transfer this, and we'll see how it's done, to Ethereum Classic, which basically mints those tokens, those ETH20 tokens, and then anything can happen here. Like we can send them to someone else. That doesn't matter. But then at this point, someone who has them says, okay, now I want to destroy them and get Ethereum. And so let's for a moment assume that this can be done easily and this can be done easily. And when you burn X Bitcoin, when you burn like any amount, when you burn 5 Ethereum, sorry. When you burn 5 Ethereum, you get 5 Ethereum 20 tokens. And then when you burn, when you destroy 5 ETH20 tokens here, you get 5 ETH. If we assume this is true, which it will be, and we'll show how it's done, then there's an argument to be made that the price of this token is actually the same as ETH, basically. So it's a one-to-one correspondence. And the reason is that if the prices were any different, there exists some arbitrage opportunities. So if the Ethereum price is higher, then you basically buy the token, then convert it to Ethereum, and then sell that, and vice versa. So this is kind of an argument as to why these tokens basically will end up having the same price. And so with this, we now see that, okay, now we took ETH, we brought them to Ethereum Classic and back, basically. And now let's delve more into the details of how this transfer, basically, how this part is done. So I will start now referring to these chains by their genesis. And for a moment, stay with me and assume that Ethereum and Ethereum Classic have different genesis. So yeah, so the two chains, again, this says that they need to be Turing complete, and the important new thing here is that these chains, we have the assumption that independently they are secure. So this is an important assumption, the only one we have to make. And what we'll do is, and we kind of showed already, is that we make a token which mirrors the token on Ethereum, but here we call it G1. Ethereum called G1. So this is basically the code for this smart contract. Again, this is on Ethereum. This is sidechain 1, and it inherits from cross-chain. And again, the information it needs to know what the genesis of Ethereum Classic is, and like it does have it here of the other chain, so G2, and then it also needs to know the address of the same smart contract on Ethereum Classic. Now, again, this shows that the genesis is recorded, and this is an initialization that can only happen once, and before it's done, the contract is defunct. After it's done, it can be done again. So we want to basically record a specific event that happens here, and this event is that when we want to obtain funds on the destination chain or Ethereum Classic, what happens is, what we want to ensure is someone paid money into contract X, and they locked it, and this transaction actually happened. It's in a block, then this block is stable, and it happened on the Ethereum chain. And yeah, so we have a Solidity event that's fired when this happens on X, and then this whole event is basically the proof that it happened for the smart contract on Ethereum Classic. Does it work? Yeah. So what we do is we have two smart contracts. If we pay Ethereum on this one, we are able to send it over to Ethereum Classic. And if someone from Ethereum Classic has basically destroyed the tokens, they can prove it here and get it in Ethereum. And the same thing happens here. So let's see what this deposit does. This first deposit happens on Ethereum. And so this is basically a payable function, so we don't need to do any to mention the amount or anything here. And so we say, okay, we took this money, which is this message value, and we want it to go to this address, and then this is just a counter. And then this emits an event, and similar thing happens here. Here's on the Ethereum Classic chain, we have some token and we want to get it on Ethereum. What do? We deposit, which is basically an ERC20 token here. And this basically takes this amount that we say we want to destroy and obtain on Ethereum. It gets removed from our balance, and then this event is emitted. And again, this is the event. This is the other event. This is again the initialization. We went through it. And now we want to look at what, like the other side. So we saw how we take money by depositing. Now we want to look at withdrawing. So this withdrawal function happens when someone destroys their tokens, their ETH20 tokens on Ethereum Classic. It makes sure that this event was fired, the event that we saw before, make sure that this event was fired. And if it was, then it sends basically the color of the amount. And I think there's actually a mistake here. This should be target. And on the second smart contract, this is on Ethereum Classic. Someone calls this when on Ethereum someone has paid money into contract X, and this ensures that the appropriate event was fired, and then it credits them that amount as an ETH20 token. And now this is like the whole contract, which I think we don't need. And now Dionysis will come up and keep going with Nipopause, which is a way to basically improve this.
Okay, hi everyone, I'm Dionysis. Is it too loud? Okay, in the light, yeah, thank you. Sure. Okay, so the way Kostis presented these smart contracts, he talked to you about this central piece of these smart contracts here, which is called event exists, which verifies something happens on the remote chain, and we kind of kept it hidden. Kostis told you that, oh, you know, the way that this works is we have this parent smart contract that everybody inherits from, and within that smart contract there is this. It basically maintains the chain of all the blocks, all the block headers of the remote chain. So the way that it was presented, event exists essentially requires that every remote block header is sent to the blockchain for verification. So in our example, when we're working here in Ethereum, Ethereum needs to know every header of Ethereum Classic. Obviously, this is not very efficient. In fact, if you try to do that in practice, this will exhaust gas limits quite below before you reach the point where you can run these verifications. Here, you want me to stay here? Okay. Yeah, thank you. Okay, so obviously this is not very efficient. So we want, or it doesn't really work at all. So we want to see how are we able to do that without sending the whole chain. Before I get into the details of Nipopause, which is the way to do that, I just want to ask the audience if there's any questions on the construction we showed so far, because we will get a little bit more technical now. So any questions about the smart contracts that were presented previously? Okay, so let's move on to Nipopause. So the question with Nipopause is essentially you have this kind of situation where you have this verifier. In our case, this is a smart contract, and you have several provers, some of which are honest and some of which are adversarial, and all of them are submitting some information to the smart contract. The way we showed it before, we said they will submit the chain of all headers of the remote chain. However, we want to somehow optimize this. And the question we're trying to ask is, can we do that without submitting every header? Or do we have to submit every header, or can we do it in a compressed manner? Can we send less data here between those two provers to the smart contract so that this is more efficient and we can do it within the gas limits of the existing blockchains? And one thing I want to repeat that Kostis already said is that the point in these smart contracts is that we want them to work over existing blockchains. We don't want to build a new blockchain system where there's weird stuff happening, right? So we want to do it on top of existing systems. So the protocol we're looking for is both of these will send some sort of proof, short proof, Pi1 and Pi2. And these are not really the chains themselves, but they're some sort of compressed form of the chain that attests to the fact that there has been some work that happened on that chain, but without actually revealing all of it. And somehow the verifier needs to then know whether the event that it's trying to verify happened or not. So over here, the verifier is asking about an event. This event Q is what Kostis talked about, whether a transaction happened, whether a particular payment happened, or whether an event happened within a smart contract. And that event pertains to the actual chain that is the longest chain on the underlying protocol. However, here we don't want to send the whole headers. So the question is, what are these sort of strings that these provers need to provide to the smart contract so that the smart contract can perform some sort of comparison between them and know that this event happened or this event didn't happen. So what we're looking at really in reality here is that the adversarial prover, what they are trying to do is they could be a mining adversary, so they could be trying to extend the source blockchain, they could be trying to mine blocks, create forks, and so on. However, we need to be able, as verifiers, to reject their claims if they belong to not the longest chain of our system. If they belong to a shorter chain than the current longer chain, their events need to be rejected. So that's the question, how do we do that? So the basic idea is based on extending the proof of work equation that Bitcoin and Monero and Ethereum all use. It's all the same. So let me just remind you what this equation looks like. So recall that we're using a hash function. It could be like SHA-256 in Bitcoin. We pass it the block header, and then we check if it's below a certain target T. So if it's a small number, then this equation is successful, and this is a valid block with a valid proof of work. And we consider this hash function to work as a random oracle. So if you pass it, what does that mean? It means if you pass it some new data that you haven't asked it before, you can assume that the output of this hash function is randomly distributed completely uniformly over its space. Okay, so this is the interesting observation that we're making, and this is the basis of the construction that allows us to compress blockchains. And the idea here is that we want to have these sort of super blocks. Basically, we're not creating a new block type. We are looking at the existing blocks of the blockchain, and we're looking at certain blocks. We're naming those super blocks if they have a certain attribute. And this pertains to blocks of the source blockchain. And we call something a super block if it satisfies this equation. So let me just go over that. So all of the blocks satisfy this part of the equation here up to T. So the hash of the block is less than or equal to t, but some of the blocks that we are dealing with will satisfy this equation really, really nicely, much more than is required by the consensus protocol. In particular, if you're thinking of blocks as having a hash that starts with a particular number of zeros to make them valid blocks, what we're talking about here in terms of super blocks is blocks that have many more zeros at the beginning of their hash than are needed. And in particular, mu number of zeros that are extraneous and are not needed. So this is the so-called mu super target. And if a block satisfies this equation with an additional number of mu zeros, we call it a mu super block. So if it has an extra zero, it's a 1 super block. If it has 10 extra zeros, it's a 10 super block. And these super blocks get really, really rare as you increase mu. So if you make mu, let's say 10, then only 1 in 1,000 blocks is a 10 super block. And to be precise, this is the probability that a block will be a super block of level mu, given the fact that it is a valid block. So if it is a valid block, then the probability that it reaches that mu super block property is given by this 2 to the minus mu. So all blocks are 0 super blocks, half of them are 1 super blocks, then a quarter of them become 2 super blocks, an eighth become a 3 super block, and so on. Essentially, the number of blocks that are at the next level are half in expectation than the ones in the previous one. So that's what we mean by a super block. So our chain, this is what we call the level of a super block. You can actually write it out mathematically, but it's exactly what I described. So this is actually how the blockchain looks like if you render it under these lens of super blocks. So the chain is really just this 0 level. There's nothing changed. We don't modify the consensus protocol, but we just interpret it in a certain manner. And what we're looking at is we're observing that some of the blocks are 1 super blocks, like there, and some of the blocks are 2 super blocks, and some of the blocks are 3 super blocks. So you can see half of the blocks are 1 super blocks, then half of those are 2, and then half of these are 3 super blocks. So they become really rarer as you go up. And this is just an interpretation of the underlying chain. This is not new blocks mined on top. The chain remains the same. So using this idea, we can compress the proof of work that happened on the chain. And the way we do that is, by the way, this is a probabilistic data structure because block hashes are random, so it might not be distributed as nicely as is shown here. This is just probabilistically the expectation. And actually, it looks like that, but you might have some distribution that has some differences here, so it might not look as symmetric as this picture. Okay, so the idea in creating these NEPOPAUs, or the proofs from the provers to the verifiers that are compressed, is that we will just send super blocks instead of sending the whole chain headers. So we will send some representative blocks or block headers that somehow capture the fact that proof of work happened without sending the whole proof of work. And this is why we call these proofs of proof of work, because they prove that proof of work happened without actually showing all the proof of work. And this is called POPAU, proof of work, and the NE on the NEPOPAU means non-interactive, because we just generated one, send it to the smart contract, and then the smart contract can verify it on its own. So here's the basic gist of the idea. And so the way we do it is we choose a specific level mu. Suppose we choose a level mu is equal to 10, and then what we say is, okay, I will not send you the whole chain, the whole chain headers. I will just look at all the blocks that are 10 super blocks, and those 10 super blocks that are only 1,000th of the size of the blockchain, only for these I will send you the headers. And then what I ask the smart contract to do is compare who is sending the most super blocks instead of who is sending the most blocks. And based on that, again, based on how many are which proof has the most length, that's the one that wins. So the protocol now looks like this. You send 2 short proofs, which are essentially just super block headers, and they are compared like that. So you count the number of super blocks of that particular level mu, and you see which one has the most. And that mu, for now, you can assume it's just a fixed constant. You can think of it as mu is equal to 10. The smart contract fixes that. It checks that everything inside here has proof of work, which is with 10 extra zeros, and then looks at these chains to see how they compare, even though they have skipped many blocks. They have skipped 1,000 blocks for every superblock that is presented there. And again, the Merkle tree proof of inclusion within one of these blocks is fully included. And for the purposes of this talk, you can just assume that the transaction is a part of one of these superblocks, even though if it is not, we have mechanisms to actually show that it is part of the chain that is underlying there. Yeah. Okay, so one of the problems in this construction, as I showed it before, is that if you just send superblocks, there is no ordering in them, because there is no prev ID pointer as we're used to in Bitcoin or Monero, where we have every block pointing to its parent. So we need a mechanism to have these sort of blocks sorted in a way that is chronological, in the way that they were generated, in the same order they were generated. Because if we don't do that, then it's possible that the adversary will just reorder the blocks and cause us to think that the blockchain has a different order than it actually does. So we need to extend our structure to look a little bit like that. So we want the blockchain, instead of having a prev ID pointer between every two blocks, we want every block to also point to its most recent block at the same level. So you can see here, every 0 level block, of course, points to the most recent zero block, but every 1 super block points to the most recent 1 super block, and every 2 super block points to the most recent 2 super block, and so on. And by the way, if something is a 2 super block, if something is a 3 super block, it's also a 2 super block, because if something starts with 3 zeros, it also starts with 2 zeros. So we want these kind of extra pointers to exist between blocks. This is not something that exists in the current implementations of blockchains. However, there is, first of all, in Ethereum, there is a plan to add this kind of structure in EIP 210, which is going to be adopted soon. And even if it's not adopted as part of the consensus layer, we can actually extend the existing data structure of existing blockchains to include these pointers without a soft fork and without a hard fork. And we have some literature references at the end that you can look at for that. So actually, this is not a problem in what we're trying to do here. Okay, so let me just say a few words about how this actually works, because I skipped some of the technical details to make it a little bit more precise, because it's not sufficient to just send superblocks. And the reason being, oops, there we go. Okay, so the problem is, let's see. The problem is if you're trying to just connect, if you're just trying to compare two chains, that one happens on one is about Ethereum and one is about the longest chain in Ethereum. The other one is about a fork of Ethereum, and you just send superblocks. It's possible that these two proofs diverge really close to the end of, so they're really close to most recent blocks. And the problem with that is that you cannot really do a fair comparison of that. It has security problems. So the way that we actually build these proofs is that what we want to do is the verifier needs to be able to compare these proofs at any level mu that it chooses. So here's the construction. Let me show you the construction, and then I will talk about precisely how the comparison happens. So first of all, this is how the honest prover will construct a proof that it will send to the smart contract. So it takes the actual chain, which is the whole chain of all the block headers of the chain it's trying to prove things about. So the source chain, it takes a certain number of blocks from the end, k number of blocks, which could be 6, and those blocks it sends all of them in that proof. So the last 6 blocks of the chain are always sent. So that's called the suffix of the proof. Now, for the prefix part, which is the stable part of the blockchain, this is the long part of the blockchain that we wish to compress. So the way we do that is we have some sort of security parameter m, and that security parameter could be something like m is equal to 3. I will show the example with m is equal to 3. If you want to make it secure, this as a parameter you want to grow to a larger number, let's say around 100. The way we do that is we start with a chain. We start with a level of superblocks that has at least m blocks. So in this case, we're looking at m is equal to 3. We want to include the top level of superblocks that has at least 3 blocks. So in this example, there's only 1 3 superblock, and so that one we don't want to include that. But the top level that has at least m is equal to 3 blocks, which in this case is level 2, we want to include it fully. And then what we're going to do is we're going to look at the top level that has at least m is equal to 3 superblocks, and then we will look at the suffix within that level that has a length of 3, and we will try to fill in all the blocks on the level below that connect these two ends of this level here, level 2. So those are the blocks that we include from level 1. And again, we do the same thing at level 1. So we look at the last 3 blocks of level 1, and we fill in all the span here with 0 level super blocks. Okay, so we do this. Obviously, this is a toy example. In real Bitcoin, this is going to be like 30, 37 levels. So we start at the top level, and we start filling them in. But because we fill in, we just take m blocks from the end, this level here will just have 3 blocks included. This one will cover those blocks, and this one will cover those blocks. So what I want to argue here is 2 things. I want to give just a bit of intuition about how the comparison is going to go, and that's the first thing. And the second thing I want to show you is that I want to argue why this sort of proof is short. So why there's not too many blocks needed when you send this kind of proof. So about the second part first, these blocks here that I've highlighted are all part of this proof pi. So this is exactly what is submitted to the smart contract. We want this to be a short amount of block, a small amount of blocks, because we want this to be gas efficient. Okay, so at the top level, we're just including about m blocks because it's the top level, it's the highest level that has at least m blocks. So this will have about between m and 2m blocks. And let's think about why this is true. Well, first of all, it has at least m blocks because this is a requirement. We require to have at least m blocks. But I'm arguing that it will not have more than 2 m blocks. Because if it had more than 2 m blocks here, because this level has about half the blocks that this level has, then if this had 2 m blocks, then the higher level would have m blocks. And that would be the higher level, the highest level that has m blocks. So that would have been included as the top level. Okay, so the top level has between m and 2m blocks. Let's say it has about m blocks. Now, every next level that we fill in this manner will have approximately 2m blocks. Why? If this level we take the suffix, which is of length m, and we fill it in, because the level below will have double the blocks that the level above it has, the level below will have 2m if this has m. Here we take another suffix that is of length m, and we fill it in with the blocks of the previous level, so again that makes 2m. And then if we were to go on, we would again take m blocks from the end, fill them in, take m blocks from the end, fill them in, and so on. So for every level, we take about 2 m blocks. Now, I want to emphasize that the number of levels that we see here is going to be small. Why is this? So if the blockchain itself has C blocks, then the 1 superchain has C halves, the 2 superchain has C quarter blocks, and so on, until we reach a chain that has just 1 block, and then we're done. But how many times do you have to divide C by 2 to get to 1? Well, that's just the binary logarithm of the chain size. So the number of levels that you see here is just logarithmic in the number of blocks that have been included in the chain itself. So essentially, this grows logarithmically with time. The number of levels grows logarithmically with time. It grows really, really slowly as time evolves. So the argument here is that the number of blocks at each level is a constant that we choose. It could just be 100. The number of different levels is something that grows very slowly. Therefore, these proofs are going to be short. And in fact, we have some measurements that you can look at in our papers that show that this is actually the case. So this is the argument for something we call succinctness. Succinctness says that these proofs are exponentially better than actually sending the whole chain of headers. And if you want to look at it at asymptotic notation, this is the kind of expression we're looking at. It's the logarithm of the chain times m, which is so this is the number of levels. This is the blocks that we include in every level, and this is the fixed number of blocks that we send at the end. So the proof size is really quite small. It's polylogarithmic in the chain. It's actually logarithmic in the chain. So this is essentially an exponential improvement over sending the whole chain itself. So for the security argument, what we want to do is we want to compare two NIPOPALs that were sent by two verifiers. One is the NIPOPAL that the adversary is sending. The other is the NIPOPAL that the honest party is sending. And we want to see who's talking about the longest chain on the source blockchain. Who has the longest chain there. But in order to do that, what we're doing is as follows. And this will kind of give you some intuition about why we do this whole business with multiple levels, where we kind of try to fill in the level below with covering the blocks at the level above. Okay, so the way we do this comparison is the smart contract receives these two proofs, pi1 and pi2. Pi1 and pi2 are just chains of blocks that have some blocks skipped. Most of the blocks are skipped. And what it does is it tries to find a common prefix between these two. And this common prefix will be non-empty because, so what this notation means is just the common blocks between these two chains. These common blocks between these two chains will necessarily have at least one block because both of them have to start from the same genesis. And between these two common blocks, we find the most recent block. So that's what this means. So from this chain of the common blocks between these two proofs, we take the latest one. And now we want to do a comparison and say, okay, this guy's right, this guy's wrong. One of them is lying about what is the longest chain. So what we do is we take this the most recent common block between these two, and then I am using kind of a weird notation here. Let me just explain what that means. Is for every level mu, we are looking at the blocks of, so for every one of these two proofs, pi1 and pi2, we take only the part after that common block. We take the part after that common block, and we only look at one particular level of our choice mu. And the choice we make for that mu is we take the highest one, that in this kind of portion of the blockchain has at least m blocks. So the length of the proof from the block B and afterwards at this level mu has at least m blocks. If you look at the construction that we have, this will always be possible to do. And we have a very elaborate argument in the actual math that we do, but I hope this gives you the intuition about why this happens. So after we choose a level mu where this happens in both of these chains, what we do is we compare the lengths after this particular block. So the length comparison happens after the common block, which is time that the two different parties would have to have mined independently of each other. One of them cannot use the work that the other one has stored. So I know this is a long formula to take in within a short talk, but I hope this kind of motivates you to look at the work we're doing and the papers where more of the details are in there. Okay, I will skip these, but give you some of the references that we have so that you can take a look at these. So first of all, the non-interactive proofs of work construction is a paper we're publishing in Financial Crypto in February. So this has all of the mathy things where it talks about how you construct these proofs, how do you do this comparison, and why this is secure. Then we have this proof of work sidechains, which is essentially the first part of the talk that Kostis showed you that explains why the smart contract works. And this was from Financial Crypto last year. This is, I think, it's an easy paper. You can take a look at the smart contracts and even implement it. Then we have a proof of burn paper that shows how can you destroy money on one chain. And using the previous mechanisms, you can prove that money was destroyed and transfer it to a different chain. And then some of the other interesting things here are this compact storage of superblocks for NIPOPAL applications, as well as enabling NIPOPAL applications on Bitcoin Cash. These are basically an implementation in practice of these ideas. we were able to do this on actual Bitcoin Cash. We use Bitcoin Cash because it just has cheaper fees, but it doesn't make any difference. You can do the same thing on Bitcoin itself. So we did it on we did it on Bitcoin Cash testnet. Actually, this is Ghosty's master thesis, it was deployed and it was done without actually doing any soft forks or hard forks. So that's an interesting piece of work. And then there's another master thesis from last year that shows how to do this in an Ethereum smart contract. And this one also has a few measurements that show that this has sufficient gas efficiency compared to sending the whole chain. So yeah, I know this is a lot of math to take in. This is why we have all these references, and I hope you can take a look at these to dive in a little bit more depth in what we're doing here. We also have a website called nepopals.com that you can look at. It has all of these references and a few more videos that show you some of the details of how we do these things. Yeah, that's all I have. So thank you very much, and we will be taking some questions. We have some time for questions now.
Do you have any formula for computing the amount of the collateral of the deposit? Because I fear that even if the deposit is quite large, if the mining works for a long amount of time, no one has an incentive to actually perform the checking because there's never any gain made for it. And yeah, that seems to be a problem for me.
Yeah, that's a good question. So we have this kind of, you have it somewhere here, right, about the collateral. Let's see. Yeah, so we have it here. Like, we have some intuition here that it has to be sufficient to cover for fraud proofs. I get your argument that even if this is sufficient, basically, due to economic reasons, nobody's going to do it because they will always get caught. Yeah. So there is a more advanced argument on that on the TrueBit paper, which is not ours, that gives some mechanisms in which basically one way you can do that is you can sometimes conceal the fact that a proof was fraudulent, and then you get paid for finding that, so that you encourage people to find it, because you ensure that sometimes there will be some fraudulent proofs that will get paid out, but you hide the fact that they're fraudulent before actually revealing that. So these are some ideas that you can use. The TrueBit paper has some nice construction that I think. We don't have it implemented here, but this is something in our radar. So there's definitely interest for future work there. Thank you very much, everyone.
Great. Thanks, guys. We have around 15 minutes until the next talk, which is on post-quantum, which is going to be great. Bitcoin to post-quantum world. So yeah, chill out. Take a breather.
on. Sorry for that break that happened. Not the one that you just experienced waiting for the next speaker, but the Diego break. I know you guys didn't sign up for that. I know you signed up for me on this stage 24/7, but I needed to let somebody else have a chance, and lesson learned, never again. But we have our next speaker coming up, but we don't have video person yet, so I like to do these interviews. Come on up. We're going to interview you while we're waiting for our video speaker. Can you please introduce yourself?
Hi, my name is Dragos, and I'm a PhD student at Imperial College London at the Center for Cryptocurrency Research and Engineering. And basically my research topic is Bitcoin.
We're not ready for your research topic yet. We'll get there. But we have to start with the basics, like what your favorite fruit is.
Passion fruit.
Passion fruit. Whoa. Okay. Can we expect the same kind of passion in your presentation that we see in your fruit?
Hopefully, yes.
Okay. What is your least favorite fruit?
Tomatoes, I heard, are a fruit, and I really don't like them.
Okay, I mean, that's kind of a cheating answer, but I'll accept it. So now let's hear from the audience. What questions do you want for Dragos with the sh at the end? What do we want to know about him? Our video guy just got back. He's setting up, so we won't have to endure this much longer. But we do need one more question. What do you guys think? What do you want to know? Do you like pineapple pizza?
This is a very contentious issue, and I refuse to answer.
That's very wise. You want to give a presentation, you don't want to start a riot. Yeah. Okay. So we would ask definitely that we keep the political questions to a minimum. So no more of that. I should have known better than to poll the audience. Still waiting on the thumbs up. They're getting there. They've ambled on over. It's okay. We can wait just a couple more minutes, maybe one more minute. No, you guys want this now. You guys want this immediately. You can't wait. Yeah, okay, let's I want you guys to just throw up your fist. Okay, no, you don't have to throw up your fists because now I got the signal. We're A-okay. I'm going to hand this off to Dragos, and he is going to tell us all about Bitcoin in the post-quantum era. Spooky.
Hi, yes, so as I said, my name is Dragos, and basically what I'm working on is sort of this new technology appears, which is quantum computers, and how can Bitcoin like exist in this world, or like is Bitcoin and all other financial systems and all cryptography doomed? No. So we are basically finding a solution for something that it's not a problem yet. And how often does that happen? It's very good. Sort of the plan that I want my plan for today is basically to talk a lot about the quantum world. And I'm not going to go into very, very spooky things like entanglement, but I just want to make everyone understand the idea of superposition. And then I'm going to basically build up to Shor's algorithm, which is the thing we care about in Bitcoin, because this is what breaks the public key cryptography that Bitcoin has. Then I'll show the problem that appears in Bitcoin and one simple solution that we can have to solve this problem. In order to build quantum computers, we will need this concept of a qubit, which is the counterpart of the classical bit. And we can choose as a qubit any quantum system with a binary state. So for example, we can take an electron, which is like in a ground state of energy or in an excited state of energy. We can take a polarized photon or the spin of an electron. And it doesn't really matter if you don't know what these things are, but the point is it has to be a binary system, which when measured, will produce one of the two results, one of the two states. And the catch is that, if you probably heard of this superposition, it allows us, when we are not measuring this particle or this quantum state, the state can exist in a superposition of both states, both basis states. And in order to explain this concept, I will first explain what, like for example, I have here a hydrogen atom with an electron that's, one second, circling around the nucleus. And if I excite this electron with a laser pulse, for example, let's say 100 milliseconds, let's say it goes into the excited energy state. So that's all good. There is no superposition until now. But now what happens if I only shine the laser on this electron for 40 milliseconds? Well, it turns out that what happens is that 40% of the time, the system will evolve into the excited state, and 60% of the time it will stay on the ground state. And this is pretty weird, and I really want to try to kind of explain why this is happening, because it's not just magic. It's actually very, very, very much possible. What happens is that electrons aren't really particles, as you probably heard of the thing called wave-particle duality. What this means is that basically classical physics says everything is a particle. Then quantum mechanics comes along and says, no, 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 everything is a wave. And then afterwards, quantum field theory comes along and says, no, 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 you got it all wrong, everything is a field. And then our string theory is like everything is a string. So anyway, we're just going to stay at quantum mechanics, which says everything is a wave. So now if we have a wave like this, if we basically arrange this wave such that it lives in the same space as another wave, they will basically sort of add together and will create this more strong wave. And you see this in like waves on the sea. It's nothing new. Again, if the waves are like sort of shifted from each other, the interference is going to be called destructive. And what will happen is that this sort of pattern will appear. So it means that the water on the sea, it will be sort of stable. And you see this at the crests of the waves. Like you see that they are sort of stable. Like somewhere are waves, somewhere are not. And because electrons are actually waves, like this, what basically happens is that and I will need my hands here, if the electron would travel just through space, everything would be fine, it's a wave. But because it's going very close in a closed orbit around the nucleus, this wave interferes with itself, basically, creating something like here. So you can see that if it wraps around exactly the number of times, like in an integer number of times of the circumference, it will basically be stable. But if it offsets even just a bit, if like the wrapping around of the wave happens such that a crest doesn't match perfectly with the crest, but it's like a bit offset, like for example here, like we have one wave and then another one, but a bit offset, what will happen is that because this happens many, many times, even a small offset will lead to complete destructive interference. So what this means is that, for example, if we look at this picture, which you've maybe seen on the internet before, which basically shows how we take pictures of atoms. What we do is we just shine some radiation and we see the way it's deflected by the electrons, and then we can say an electron was here. And then we do this like thousands of times, millions of times, and we build some kind of a picture where we see where electrons are usually exist. And basically this first wave would wrap around in a sort of constructive interference pattern around this nucleus. And many, many electrons will be found here because the energy is stable there, because the wave exists. And then here, this is like a higher energy level. You can tell this by the fact that this wave has a shorter wavelength. And this is wrapping around at a further distance from the nucleus because it has more energy. And it exists there. And now the question would be, why can I not be in the middle? Why can I not be in between the levels? And the reason is because, as I was showing here, if the wavelength is not a perfect multiple, if the circumference of the orbit that you're trying to do is not a perfect multiple of the wavelength, then you will get a bit of an offset, which will lead to this, which will lead to basically dark spots, so places where energy cannot exist. And what this means is, it has like, this is basically the concept of superposition. So the idea is that it's not like when we superimpose these two waves, the resulting wave doesn't exist. It exists, and I'm not drawing it here just because it doesn't exist in the real sense. It exists as a complex probability wave, which is more complicated to show. But the point is that this wave exists, it's just that we cannot measure it. Whenever we would measure it, we would either get one of these two stable things, because if we would try to measure a superposition of these waves, we would get some kind of this effect where the result will just cancel out with itself because it interferes with itself. So it's there, but because it's interfering with itself, it disappears, and we cannot measure it. And what we would measure is just one of the stable orbits. So this is kind of what superposition is. Now, if some of you went to this talk in Borg about quantum computers, somebody there already explained Grover's algorithm. So, but I'll go over it a bit faster. The idea is that this algorithm, what we want to do is to search for some piece of data, let's say x plus 1 equals 5, in some unstructured data. Well, this is of course structured, but you can imagine where the order doesn't matter. It's like random data. And you will see how this makes sense. We can now arrange a quantum state where basically each possible value that we measure, each basis state, is it has equal probability of being measured. And so again, if we measure right now the quantum state, we get randomly one of these values. What we do next is we apply this sort of function, which basically verifies if x plus 1 equals 5, which is our wanted value, and it will change the amplitude of the wave. So what this means is that one of those waves that would add together to create the superposition, we are now shifting its, we are basically changing its phase such that the amplitude of the complex probability of this wave goes to -1. I don't want to trick you. The probability, if we now measure the state, the probability of this happening is equal to probability of this happening or of this happening, because in order to measure a complex, to get from a complex probability to a real probability, you have to square the number. So minus something squared is still the same thing squared positively. So it's still the same probability. But this basically, the fact that we shifted this phase allows us to do stuff like this. We then say we will reflect around the average. And I could explain what this means mathematically, but basically what is happening is that if we have a wave like this, and at some point the wave is like down, and now we apply some sort of electromagnetic field or like some microwave radiation or stuff like this, we will basically be able to change the amplitude of this wave up by taking energy from all the other waves. So we sort of make them smaller. And this way we basically made the chances of us measuring this thing much higher, but it's still under half. So we will do it, we again negate it, and we again amplify it, and in time, apparently after exactly square root of n, where n is the number of possible states, we get like the best probability that we could get, like the best that we can do. And I have here some mathematical description of this algorithm, and the reason I have this is because the next algorithm that I will show you, which is Shor's algorithm, is a lot more complicated, so I cannot just show you with just like some states. So I want to familiarize yourselves with like this algorithm base, this idea of notation like this. So what this says is that I'm going to start with an empty register, just zeros inside, nothing interesting for now. And then I'm going to put it in a superposition of possible states. So what this is saying is that for every possible state, like 0, 1, 0, 0, 0, 0, 0, 1, 1, every possible state has a probability of being measured, which is equal for all of them. So we call this superposition, we just add this possible state and their probabilities. That's all good. Now, when we say invert the amplitude of the wanted value, we basically just invert the probability. Again, this is just a complex probability. The real one would have the same value as the real probability of this one, which is alpha squared. So the superposition now changes into this superposition, which basically has all the states that are not our wanted value with equal probability, and this one negated. And then when we say inversion around the mean, what we do is we basically take the average and we say, now the state becomes 2a plus 2a minus what was there before. So in the case of minus alpha, we get 2a plus alpha, and in the case of just alpha here, we get 2a minus alpha. So this is very nice because obviously this is a higher probability even squared than this is a higher than this probability. So it means that we did something good. Like we are now more likely to measure this value which we want to find. So how is this useful in terms of Bitcoin? Well, if you think about what hashing, what proof of work does, is you're basically trying to find the nodes such that the hash of a message, which is like the block header and the nonce, is smaller than some threshold. So it turns out that, in fact, if you know that you are looking for more possible values, and you are looking, in fact, for t values, you can do better than just square root of n. You can do square root of n over t. And, sorry. And also, because we want maybe to run this computation in parallel so that we mimic the way classical computers compute hashes. We won't require, like the best probability we can achieve. So we won't do this many steps. We'll just do less, but in parallel, or multiple quantum computers at the same time. So this might actually be very profitable for mining. So for breaking hashes, not so much, because this is just like a quadratic speedup. It's just square root of n, which is still very large. And if I just make the key, the security size, the security parameter twice as big, I'm solving this problem. I'm back to the same security I had before. So this is not very impressive. But if I'm talking about mining, then yes, I might have a huge advantage. Still, though, quantum computers are quite far away in the future, and by the time we'll probably get to have them stable enough to do this sort of computations, they will probably also be popular enough, so more people will have them. So mining might just be done with quantum computers by default, because they have such a good speed up compared to classical computers. So let's not worry about Grover's algorithm and how it can affect Bitcoin too much, but let's just think about the fact that quantum attackers might be able to do proof of work much faster than other people. And now this is the problem that Bitcoin faces. Shor's algorithm. The idea is here that we are looking for something that has like a certain value, which is like in a database which has an underlying structure. So for example, integer factorization is a modular arithmetics. So every a certain period that we choose, the numbers will repeat perfectly. So there is some kind of structure underlying this group. And this is called a hidden subgroup problem. And it can be reduced to something called period finding, which just means I want to find the period of this function. Can I do it or not? And classical computers cannot do this. They can only do it in exponential time, which is not good. And Shor's algorithm actually can do it in polynomial time, which is very good. And only linear number of qubits compared to the security parameter. So with around 1500 qubits, we can basically break ECDSA in like seconds. So this would be very, very bad for Bitcoin. So I will try to sort of show you how this algorithm goes. We start from a superposition of two registers. Well, they are first empty, and then we arrange them in a superposition. So we put here all the possible values for x, like all the possible inputs that our function could have. And here we just put an empty register, because we want to store on it the value of x, of f of x, sorry. So we have now a superposition, which if we measure the state right here, we will just get an input value and an output value. That's it. So that's not very useful for us. What we will do instead is we will just measure this part of the computation. We will just measure this f of x. And of course, because we measure this value, the state collapse is one of the basis states of this register, which is going to be, let's say, value m. But the trick part is, like where the quantum superposition capabilities appear, is that the x register will not just go to one input value, because there are multiple inputs that could produce this m. And there is nothing that forced the quantum state until now to settle on one of them. So it will actually still be a superposition of all the possible inputs that would have f of x equal to this m. And I represent this by saying, some multiple of the period of the function r plus some offset L. And if I measure this, and I only measure this right now, if I measure this right now, I will get one of the possible input values. So again, that's not very useful. What I will do instead is I will run this computation again, and I will measure again this f of x. Now, if I measure it again with very, very high probability, I will not get m again. I will get a different m prime with a different set of solutions x, which are still a multiple of the period plus a different offset. So we are now at a point where we have these two states which are very close to what we want, because what we really want is to find the period. So now there is this function called the quantum Fourier transform, and from people who do like maybe sound-related stuff or who know frequencies or amplitudes, they know that the Fourier transform basically allows you to decompose frequencies into the basic frequencies that are composed of it. Well, in here, the frequency is just R, and it's offset by some L, so it's not very interesting to find it. But we still want to get rid of this different L and L prime. We just want to be left with this, basically. So we apply the quantum Fourier transform, and we will get back a state which is a superposition of multiples of the period. And now we just need to measure these states 2 times. So that's why we do this computation 2 times, because we want to guarantee that the multiple here is going to be different. So we will get one time J1R, and the second time another multiple of the period. And of course, we can just find the common divisor of these numbers, and that's how we get a period. Of course, if they are multiples of one each other, then we just do the computation multiple times until we get things that would basically deterministically determine a certain period. And yes, this is it with the quantum part. This is it. But what I hope you can appreciate is that in Bitcoin, we use this elliptic curve point exponentiation in a finite field, which is just elliptic curve digital signature algorithm. And in order to solve it, we need to solve the discrete logarithm problem. And this is a problem basically, it's discrete because it's happening in a finite field, again with modular arithmetics. And this function again shows a certain period. So it means that we can solve this with Shor's algorithm. And as I was saying earlier, we can do it with like around 1500 qubits, which is actually less than we can break RSA with, just as an aside. And basically once we can do this, transactions are not safe anymore, and we will see this. So we are right now in this place where it's all safe. I have my secret key, I generate my public key, I can give it to anyone, and everybody is happy. They can never find my secret key. But the problem is that Shor's algorithm will move us into this world where this is just trivially, like, it will be trivially for me to compute your secret key if I just see your public key. So just to measure how big the impact is, in Bitcoin right now, 10.2% of the Bitcoins are stored in outputs which are paid to public key, which means that the public key is just visible in the output. So anyone who has a quantum computer, which hopefully nobody does now, will go scan for these public keys, and he will basically compute the secret keys and steal the money. Then another 23.3% of the public key of the Bitcoins in existence are stored in scripts that basically reveal the public key when they are spent in the input. So by and large, 33, like a third of Bitcoins, if you would have a quantum computer, this would be like the pool of money, the prize you win for finding a quantum computer. You can take 33% of Bitcoins. And the other 66% of Bitcoins, the public key is not revealed, but in order to spend the money in that public key, you need to show it in the input. So that's also a problem we are trying to solve. Now, how do you sort of solve the problem of ECDSA? Well, it's not very complicated. We will just develop a new thing which is quantum resistant, and there are here some candidates for this, like lattice-based cryptography, multivariate cryptography, and they all rely on the fact that these groups don't present a certain underlying structure. The disadvantages are that the key sizes are larger, the verification times are larger, but we will have to make do with these things. Now, the problem appears is that, let's say, very nice, we deploy these quantum resistant signatures, we now have transactions, we spend using our classical signature ECDSA, and we create some quantum resistant address, and now our money is saved. But sort of what I'm trying to describe is the scenario where a user wakes up in 100 years, and he still has his money in some output that doesn't show the public key, but he now needs to spend them. And he doesn't know how to do that because the problem is that when you do this, if a quantum computer exists right now, he can just compute your secret key right now. There you go. And make a malicious transaction which basically front runs your transaction. So if he can do this, if he can derive a transaction which is malicious and get it in the memory pool and accept it in the blockchain faster than you can do, he is basically front running you. So this simple scheme with just the classical signature is not secure. We cannot rely on this for the transition to quantum resistance. So what we have to do is to basically create the idea of a quantum resistant surrogate. So once we have deployed quantum resistant signatures, we are now able to also verify them. We will add to the protocol rules some things that go like this. First of all, we require this stuff because this is still broken, like we can still break this, but this part we cannot. Like this is still quantum resistant. So again, we go this, in the transaction, in the input, we will add this quantum resistant signature. But of course, the problem is that we need a way to basically prove that the owner of the public key, the classical one, is the owner of the new quantum resistant public key. And this is basically where the transition protocol has to come in. And what we have to do is to basically give some proof that this owner is common for both of them. So the way we would do that, our proposal is that we will basically just implement a hash commitment scheme where we in a transaction that is very much ago in the past, very buried below many blocks, such that the quantum attacker cannot rewind the blockchain using his Grover algorithm to mine much faster than everyone else can. So this is like very much buried in the blockchain. And you have here a hash of the pair of the public keys that you're trying to link together, these two things. And if an attacker would try now to basically claim that no, my public key is the public key that should unlock this is actually this one, which is his public key, the attacker's one, he would not be able to complete this proof because he would need to, first of all, in order to publish this transaction, he would need to roll back the blockchain for 6 months in order to insert this thing. So there is no such proof that can be constructed. And yeah, as he cannot do this, the protocol basically looks like this. So you would start by having a commit phase where you generate a public key quantum, you generate a quantum resistant public key pair. You make this sort of transactions where you're just publishing the hash. And again, Grover doesn't help with just breaking the hash. It would help with mining because it's a speed up, but it still doesn't solve hashes. So this is safe, you can do this transaction. Then you wait for a long time, and we argue that this parameter has to be basically enforced globally. Because if we don't enforce it globally, if let's say people just say, oh, I will wait for 3 months, I will wait for 2 months, I will wait for 1 month, then it appears the problem appears that the quantum attacker can himself insert the commit transaction just like 20 blocks ago and say, yes, I waited for only 20 blocks. So it has to be something enforced in the scheme, in the protocol itself. Why 6 months and not shorter or not longer? It's a different story and quite an interesting argument. The idea is that attackers could try to basically create multiple forks to confuse the network and because they have more mining power, so it would be quite easy for them to do it. But we argue that 6 months of rollback is either impossible or the community would take out of bounds measure and would basically stop this fork. Like a fork that is 6 months old would definitely be stopped. This is my talk. These are 2 papers that we wrote on this subject. And you can find more information about post-quantum cryptographic schemes at these links. Yes, are there any questions? Yes, please. There's somebody in the back.
I have actually 2 questions.
Yes.
First is, this scheme would require a hard fork, right?
No, this scheme can be done with a soft fork because in here all I am adding extra stuff is the signature, and this is already in the input. And this we can put in a segregated area like Segwit was deployed. And yes, and we would still verify the classical signatures. So old miners would just think this is all normal, and the new miners would also verify the quantum resistant signature and this Merkle proof that this transaction exists.
Okay, and the second question is, what would prevent the attacker to publish the commitment transaction?
What? Can you repeat?
What would prevent the attacker to actually outrace the honest user in the commit phase?
So I think what you're asking is, when I make this commit transaction, what prevents the attacker of front-running this? Well, he can, but he won't be able to put in the value that he wants here because this is a hash of the pair. So he would need to know my public key in order to make a link to it. And he doesn't because we assume it's not revealed. And if it is revealed and he has a quantum computer, then you are lost anyway. You cannot save it. Any other questions? Yes.
Can you explain how finding the period helps us find the factorization of numbers or discrete logs?
So there is a mathematical demonstration for this, which I don't think I can reproduce right now. But yes, I can basically, I can explain to you afterwards. That like it's quite complicated. Yes.
I'm a bit confused at the moment because I think that when it comes to stating the premise of your talk, you basically skip the toughest part of the talk in like 2 sentences.
The post-quantum cryptography.
Yeah, which was like, okay, how do I get how do I get Bitcoin post-quantum crypto is by just implementing a post-quantum crypto signature. Which I would have thought would be the focus of this talk.
So I understand what you're thinking, and basically these schemes are actually post-quantum cryptographic schemes were developed well before the actual schemes we have, like 30 years before the ECDSA and RSA. But they were not used because of various reasons, and really much smarter people than me are doing this and are solving these issues, and they have been solved basically.
Well, this is where I would disagree with. I'm actually partially working in the field, and as far as I know, the NIST challenge is still open,
yes,
and
of course.
there is no form of any way of having a post-quantum crypto signature scheme available at the moment that has withstood only a limited amount of rigor. So far, we have 9 quantum signature schemes in the running in the NIST challenge, and none of them is anything that any person who takes crypto seriously by an inch would touch and call secured. So what I would basically propose as a rephrasement of your talk statement is that what you're showing is not getting Bitcoin post-quantum crypto secure, but what you're arguing is that given that the existence of a post-quantum signature scheme, you propose a scheme to implement quantum agility in existing Bitcoin schemes, which is a completely different claim from saying that you're making Bitcoin post-quantum secure, because you basically argue that there needs to be a post-quantum secure signature scheme, which we don't have yet.
In some sense, I see what you're saying, but I guess the point of the talk is how do you transition? Like, part of the problem is indeed what you're saying, which is what you're working on apparently, and it's way beyond my level of understanding of how this works, really. So indeed, once you have a post-quantum cryptographic scheme, my point is that even that is not enough, because you also need a way to move from the current one in the presence of a quantum computer.
And that would be the second one where I'm happy that you basically took that question from me, so that given we have a post-quantum crypto signature scheme, which is a big if at the moment, will approximately remain to be for the next 3 or 4 years, at least if we look at the speed of the NIST challenge moving ahead, and the talks like Tanya Lange and CJB just gave today. The next question is, have you done a formal reduction proof to show which crypto primitives are used by your transition by implementing the so have you done a formal reduction proof to show that even if I have a post-quantum crypto signature scheme, you have a formal reduction that Bitcoin is as hard to crack as the primitive?
That Bitcoin is?
Well, have you done a formal reduction proof?
So yes, given the assumptions of hash functions and the assumed assumptions of what a post-quantum resistance scheme, signature scheme would give you, then yes, you can find it in the first paper, which is this one.
So because I tried to read it last night and I was.
But I think it's sort of intuitive to see why this is happening. Like, it's just that
but
you are
it's
not
sort of intuitive to say that finding prime factors is hard and quantum computers do it. Isn't that what quantum computers taught us? That it's sort of intuitive to see that they can't do this, is what quantum computers have fooled us.
I would argue it's
time and time again that they can do the things that we do not expect them to be able to do.
I think like Shor's algorithm was done in the 1970s, so for a long time we knew that we can do this sort of calculations. Yes. It's just that practically we cannot. But this is like theoretically speaking, we can, and well, for quantum computers. But in this case as well, if you take some assumptions theoretically, you can see why this would work. Like you don't. But yes,
yeah, the point is, I don't see any validation of your assumptions. You assume basically that you think that you don't see an intuitive way to have a quantum computer break your implementation. So what you basically...
I think you're basically asking if there is another way that the quantum computer could break this that I'm not imagining because I'm not... okay, I see. Yes.
Because a formal reduction proof would protect you from that.
I see what you're saying, yes.
If you would do a formal reduction proof, you could go ahead, do a formal reduction proof on your Bitcoin setup, show that it is as hard to crack as the quantum primitives it is employing, and then say that due to the fact that you're relying
the
on
quantum resistant primitives.
Yeah.
Oh.
No, well, the crypto primitives, and since you are employing a post-quantum crypto primitive, then your Bitcoin is fine. But given the assumptions that you made, I don't see you doing a formal reduction proof on that.
So I think I'm not exactly sure anything, but yes, like you can find it in the paper. But the point is that
well, I didn't. That's why I'm asking.
Okay. I can talk to you about this later.
That
if you want.
yes,
we can talk right now. Is there the next talk or other questions?
Now, guys, we just heard them clapping, and we have to clap louder than they clapped because we have better guests than they do. So I want to hear it once more, but with feeling. Now they're all jealous over there. See, this is how we get speakers. This is how we get quality speakers to our cluster. Thank you so much. Thank you. Hope we all learned a thing about quantum computing and Bitcoin and how it's going to fare or how it's not going to fare. I'm going to have to rewatch that talk. I was very eating. So that's what was happening with me. We have, what is it? The last talk? Is it? It is. Guys, why are there talks going until like 1 a.m. over there? What is going on with this place? I'm just saying, my team, guys, we need to go until 3 a.m. next year. Okay? We can't be slacking like this. Last talk, guys. We got last talk for today is 3.8 billion users. Future email 3.0. So if email 3.0, blockchain 6.0, internet 7.0 interests you, if numbers are cool to you with O's at the end, then this is the talk, the premier talk that you're going to want to go to. You're going to be giving this talk. So we're not set to go for another 10 minutes, but you could stand here for 10 minutes if you'd like. We're going to take a break, so, just in case anyone's scheduled that they really want to come to this talk, we're going to let them get here, because otherwise you're going to start early. They're going to feel slighted. They're going to file a complaint, and then we're not going to be able to come back to 37C3, which, nobody wants that. So roughly 10-ish minutes, everybody, and we will have our last talk about email 3.0, 3.8 billion users' future. hey everyone, I have unfortunate news. Similar to the fact that I did not allow this presentation to start early. We're now past 9:30. We didn't start on time, so I'm not going to allow this presentation to start late either, which means we're going to have to cancel. Everything's done. You guys can go home. C3 is canceled. Germany is canceled. This is the cancel culture that we live in now, people. We got to be used to this by now. No, come back on the stage. We are going to get going, just waiting on the signal, just waiting on the okay. We all okay? No? Yeah? Yes? No? Yes. Those are thumbs, not middle fingers. So I think we are all good. All right. Can you go ahead and introduce yourself for us?
Sure. Hi. I'm Sam, and hopefully you can hear me because I'm making tongue love to this microphone. And yeah, so I spent 15 years in open source. I spent the last 4 years running an open source email marketing tech company called PHPList, which some of you may have heard of. And yeah, I'm a big fan of decentralization and open source, open standards, worked for FSFE promoting that. And today I'm going to be telling you what I know about email, where it's come from, where we are today, threats, and what I hope will be an optimistic future. So let's get going. What makes a good messenger? What makes for a good messaging app? This is a really interesting question, right? Because there have been literally hundreds of messaging applications which have come and gone over the last 50 years, both proprietary and open source. And I actually only have two hands, so I'm going to have to alternate between these devices. But when we look at the list of proprietary messaging applications which we are already familiar with, there is better, okay, then we will see many that we're familiar with. Depending on how old you were when you gained your digital stripes. You may have been familiar with AOL Instant Messenger, Google Wave, Google Plus, BlackBerry Messenger. That was a big one, right? Everyone thought that was going to be around forever. Groove, Twist, ICQ. My girlfriend met her first partner that way. MSN Messenger, Viber, all sorts. Proprietary messaging apps which have come and gone, many of them with a lot of investment, many of them which their firms and their shareholders of their firms believed were going to be the next big thing, and for some of them actually were the next big thing for a good chunk of time. But we are a more enlightened audience now, right? We're more pro-open source, so we're probably more familiar with some on this list which have yet to achieve global domination. My definition of success and failure for the purposes of these slides is something which is achieving like a global scale and which has stood the test of time. So let's say at least 5 years. So I used to be an avid Contalk user, Diaspora, Pump. Like about 10 years ago, I was big into these things and using them for messaging and hoping that enough other people would adopt them that I could use them as my primary messaging applications. But they didn't last so well. I don't know how familiar you are with Hemlist, which never actually got to the light of day, or Project Appleseed, some of these others, Mumble's still a thing. But even the open source messaging applications, sorry? IRC, yeah, IRC is very close to my heart. I don't know what Slack's offering that they're not personally, but yes, IRC, absolutely, taught me how to code. So whether proprietary or open source, it's really tough to make messaging applications which succeed, we've seen. And there's all sorts of reasons for that, which we're going to dive into now. Email, on the other hand, something about email which has really made it different. 103 trillion messages estimated to be sent every year using email. 103 trillion. As the talk of this title says, 3.8 billion users. Those are unique users, right? That's to compare to Facebook's 2.4 billion users they currently have. Email, yeah, it's still rising in popularity, estimated 6% new users in 2019. It's basically the undisputed king of digital communication. In fact, earlier this year, the Wall Street Journal saw fit to describe email as the hot new channel for reaching real people. That's in January, right? So that's a thing. And you might be thinking to yourself, well, yeah, but they're talking about email in terms of email marketing, and that's different to my use case. Like email marketing is maybe a separate animal, and you're kind of right. But the fact that email is so popular for marketing tells us a few things, right? Firstly, like email is still number one, like consistently ranked number one for return on investment for digital marketing spend. And that tells us that people are engaged with that content and they're acting on that content. So marketing does tell us something about how successful communications platforms are, because people, basically companies don't spend billions of dollars on communications channels that aren't effective. And if we look a little deeper, we can also see that actually there's really big business still being done in and around email. I was talking to some folks here at the front row about this talk just before it started, and they described email as an ancient system and protocol, and it is. Like, I mean, 50 years, I think it's fair to say it's ancient for a protocol that we're still relying on. But the fact that in the last 7 years alone, there's been $17 billion US spent on mergers and acquisitions of email tech companies says something about its relevance and its importance strategically. And many of these acquisitions of companies in the email space, they're by Facebook, Google, Amazon, Adobe. All these big American tech companies have got into the email game. They've all bought email tech properties during this time because it's really important strategically still. Additionally, there are hundreds of email clients available. Basically, every significant platform has multiple choices of email clients, which is something that we take for granted. We don't have multiple choice of clients for other messaging platforms that we use, like LinkedIn Messenger, for example, not viable ones anyway. And yeah, all examples of email really being king of the roost. So why is this? What's made it different? It's not just that it was one of the first to the table. There are specific things, and so I'm going to answer my own question now. Like, what makes a good messaging experience? Let's start with the user's perspective, right? It's like maybe the most accessible and the easiest to get going with. When we make our own decisions about what email applications we use or what messaging platform we would adopt, we need a few things. We need a free price tier. Gratis is basically expected of users for any kind of technology, even B2B technology. People expect a free tier, so we have to have something that's free. We have to have something that's like cheap to adopt, something that's easy to get going with. A lot of the newer systems, some of the open source platforms, they're not so easy to adopt as a user. Like they require some more technical steps involved. Anyone who's tried using Mutt or Asteroid messaging clients will have experience with this. Also, the messaging system needs to be easy to switch to from another platform. So it's not enough that if you're a new user, you're welcome, but it also needs to be easy to bring your contacts and content from somewhere else. And also, it needs a critical mass of users. Otherwise, you personally have to advocate to every other person that you want to communicate with using that system. So we require a critical mass of users so that when you adopt it, it's already there and useful to you by default, without you having to put in all the legwork and do the marketing for that system yourself. So that's on the user side. Now, in order to achieve those benefits for the user, there have to be other building blocks in place, and some of these economics. So specifically, it has to be like accessible. So the messaging system, it needs to be like available in your region. There has to be a server. There has to be a system that supports where you are and your language and be accessible. So that means it needs to be business backed. It means we need organizations which are basically vehicles which are sustainable, which will continue to provide this service and continue to deliver good quality service. For there to be businesses interested, we need viable business models to attract those businesses to be involved, and that's a separate thing, right? And additionally, we need an efficient market, which will mean that there's actually competition between different providers of hosting or different clients, so that not only does the messaging system get established and serve users' needs on day one and in year one, but also over time it continues to improve and continues to meet users' needs, that it continues to be adapted to new platforms regardless of like strategic needs of the companies behind them. So like Microsoft might not have invested in making MSN Messenger clients officially for Android because it was competing with that platform at the time. No, we need an efficient market of vendors effectively to compete to continue to serve users' needs. And that means that it needs to be a low barrier to entry for companies that want to produce new clients or new servers in this space, potentially. It needs to be easy for them to get involved, not have to pay license fees, not have to risk getting involved with patent wars, like the Unix wars. And also, it needs to be attractive for them to enter this in the first place, right? So it needs to be not only easy for companies to create new technology and create new services within this messaging platform, but also it needs to be motivating for them to bother to do so. This comes back to the business models, but like a monopoly or an oligopoly isn't really going to cut it. It needs to be more efficient than that. So those are the economic requirements. But again, if we step one step behind those requirements, we see that there are in fact technological and strategic requirements for the messaging platform to succeed. Like technologically, we need freedom of implementation. So it's kind of an obvious one maybe for we open source and open standards advocates. But for the world's leading messaging platforms which are not email, in most cases you don't have freedom of implementation for various reasons. APIs can change, you need licenses, you need API keys, etc. Yeah, that means you need freedom over both the client and the server level to experiment and to improve and to hack and to deploy and to localize. Also, there needs to be a separate protocol from the implementation so that the protocol's interests can continue to exist and thrive independent of the client and the server. Basically, we have different stakeholders here because the needs of the protocol can potentially diverge and conflict with those other two groups. And we need extensible functionality. So that can be built into the platform itself. If we think of XMPP, the first X is really important. It's extensible. And there are hundreds of extensions to XMPP which give us benefits that we take for granted today. Things like the ability to set a custom nickname on your XMPP account, your Jabber account, or to have a mood or a tune or even an avatar picture. Those are all extensions that were added as innovations additional to the core protocol. So we need the system to be extensible, and we need independence from a central authority for various reasons, also strategic, also so the company can't get bought. When we combine these things together, we see some really important effects, which are the fertile ground that messaging applications need to succeed. More specifically, we see efficient innovation and competition within the messaging ecosystem. So what this allows for is effectively the outsourcing of innovation from one company with one set of finite resources or one organization or even one community to a much broader global community of innovators. That means that people like the audience here at 36C3 can add improvements, they can spot problems and fix them, they can identify security holes and patch them. Basically, they're independent to bring their skills and innovation and resources without there being a bottleneck from a company like Microsoft or Facebook or LinkedIn. Yeah, both at the client level and at the server level, that is, because again, these technologies have different requirements at those levels. It allows for fast adaptation to new platforms and devices, so quickly we will see the messaging ecosystem extend when new devices and operating systems become available and become in vogue. And we can also see high-performance products, because ultimately the user remains a customer. We don't end up with a situation which we see so often with proprietary, centralized messaging protocols where the user is actually not the person who makes the decision about what application they use, which causes, basically the interests diverge. No, the user needs the freedom to switch. The server administrator needs the freedom to switch. And the people who develop the protocol also need the freedom to make decisions that are in the best interest of the protocol, irrespective of the needs of those other two groups. These are the effects of the strategic, technological, economic, and users' perspectives that all go together to make what we need for a successful messaging platform. So to boil this down, we have what I would call the magic formula for email success, which is a critical mass of users, extensible functionality, independence of a single authority over the network and also over the technology itself, an efficient market of service providers to continue to compete and produce new innovations and have a good quality service. And actually, if we look at email today, we can see that clearly it has a critical mass of users. It has more mass than any other system. And let's see how it stacks up against these other key points of the magic formula. First off, is email extensible? It's ancient, right? I mean, when you think of email, you may not think, yes, it's so easy to extend, it's so easy to improve. In fact, one of the criticisms of email I heard again at the beginning of this talk was that, yeah, it's broken in these ways, but nobody seems to know how to fix it, or it's too slow to get people to agree to make those improvements. Well, actually, it's super extensible, right? And the fact that here, roughly 50 years after email's conception and initial use, we're still using it. I mean, if you think about that for a second, that tells you just how extensible it must be. So let's even just look at the last 25 years of the use of email for how it's been extended in critical ways that benefit us and allow us to continue to use it. We had the first read receipts in '95. We had attachments and MIME types supported in 96. I'll say more about MIME types in a second. In 2000, IMAP extensions became a thing, which made it possible to extend the functionality of the core protocol, much like XMPP is extended in the way that I described earlier. From those XMPP extensions, today we can do server-level searching, we can move mail from one box to another more efficiently, we can find out the quota that we're using of the disk space, and all sorts of other features we take for granted. In 2001, MIME types were used to support OpenPGP, email encryption. And 2002, we had the first official support for HTML content, and that came with tracking pixels, which opened up a multi-billion-dollar industry today of email marketing, which many of you will hate, but some of you may also appreciate. It's also roughly the time that MailChimp was founded, around 2000, also PHP List. And in 2004, read receipts became official through the IETF, and in 2015, we finally got protected email headers. So those of us who are enjoying encrypted email subject lines, we have email's extensibility to thank for that in the last 4 years. If we look at MIME types alone as one example of how email has been extended successfully, there are today 1,841 different MIME types supporting different kinds of content which can be attached to an email. And if you look at how these are categorized, the majority of them are for apps, but we also have 153 audio types, which can be supported natively, like opened correctly by your mail client. And this MIME type system and ecosystem was so successful that it was adopted wholesale by all browsers. So obviously, you know, if you're downloading stuff, if you're using, I mean, any modern web server will be including header information to tell the user and their mail and their web client, their web browser, what kind of content should be used using the same MIME type system which has been devised through the extensibility of email. So it's pretty much extensible, I think we can agree. How about the independence of its authority? Well, let's have a quick recap about the architecture. So web is primarily client-server relationship. It's simple. It used to be one way. Now it's much more two-way. Every time you request a page, you're sending all kinds of data about yourself, which is patched together, as we know, and turned into demographic information, sold for marketing, and so on. But primarily, it's a simple architecture of server and client. Email is not that way. It requires cooperation between multiple servers, not clients, in order to make the message delivered successfully. So we have the sender's mail sent to a mail server that they have a relationship with. That in turn is looked like the address of the recipient is looked up using the standard DNS system, and then the receiver's mail server is contacted. The mail is delivered to them. Once the user that has a relationship with that mail server is online, then they'll receive their message. Now, this system is fundamentally different, and it has a variety of benefits that we really take for granted. So it's peer-to-peer. Again, it requires cooperation between servers that we don't see with web-based architectures. All peers are fundamentally equal, really important. They just use the DNS system. So long as you have a domain name that can be reached over the internet, you can have a mail server. No other barriers to entering this market. Messages use store and forward as a system, so it's quite resilient. It's asynchronous. It assumes that the network will have problems, that there will be latency issues, that maybe the other mail server won't be available sometime, and it's resilient to that. It will keep your messages happily waiting, usually until the recipient mail server is online again and able to receive the message, at which point that mail server will keep it until the user is ready to download it. Of course, you might be using push notifications, etc., but this is the fundamental architecture. So it's really different to just web-based content. So we have, from that, easy to deploy, easy to set up, and no central authority that can say no. You can set up your own mail server in Turkey or Egypt or China or wherever else technologies are blocked. So we see that we have independence of a single authority achieved as well. Now let's look at the last point, the efficient market of service providers. So there are a whole range of different business models based around email. Some of them are newer than others. I'm going to start with the biggest ones. Obviously, advertising is a really big deal here. This is both direct and indirect. So you could look at the success of Gmail as, I don't know, Google, they kind of achieved this quantum leap in their business model, like the revenue that they could achieve from email by taking a very indirect approach from the data that they got from your email, basically. So companies like Hotmail before, they were doing a pretty good job of getting direct advertising revenue by adding adverts to the bottom of your messages and the footer messages, and also having banner adverts and so on. Gmail's like, no, let's stockpile this, let's store this, let's use this to build up profiles, make it very indirect. It's less obvious to the user what's happening. It detracts from their experience much less, and they made a bunch of money from it, and they're currently dominating email. So advertising. We have also ecosystem lock-in. That's another big one. So the email address is not so much, I mean, the messenger in itself is not providing revenue directly, but it's very indirect. Think of when you need to create a new Gmail account when you first activate your Android phone. It's not a choice. It's something that ties you into the ecosystem. Then you can only receive certain kinds of communications through that. And one step after another, you basically get upsold to more profitable services, whether it be G Suite in Google's case, or whether it be OneDrive or Office 365, and you get pulled into an ecosystem, and they make their revenue from you in other ways. Another business model is more direct, more transparent, you might say, to the user, which is a monthly fee. We still see Yahoo Mail Pro, which only launched in 2017, for example, making money out of this. Proton Mail Plus, Collab Now, probably several of you are paying for your services, but unfortunately, history has taught us that most users, like the mass market, they are not prepared to pay the cost of the hosting of their email, which is why this is number 3 on the business model list in terms of popularity, rather than number 1 or number 2. Fourthly, we have it just as a cost center, basically, so it's used to get other things done. It's not really a business model per se, but that's how the costs are covered. And then the last two are to do with like softer forms of advertising, so ISPs, internet service providers. They want to use like the social proof of the fact that you're using them and their services, so they give you a free email address and you advertise to all your friends that you're using them, and they think, well, he knows what he's doing, or she knows what she's doing, maybe we should use the service that they are. And then finally, we have pay for association. So I just listed these 2 brands because these are ones I've been personally involved with. But yeah, like when you pay to be associated with something which you view as prestigious, so you can make a donation to these organizations, and in return you'll get an email address. Or also the Document Foundation is a little bit similar. If you contribute and become a member of the organization, contribute your time and skills, then you get access to one of their email addresses. So there's a variety of different business models here. And that's good, right? That's good for variety. And this is part of the reason why there's such a variety of hosts out there, because companies like Proton Mail are completely different to Google and Microsoft in their business model, in their motivation, and how they produce things. Like Proton Mail is investing in making open source PGP clients, for example, which is awesome. They have a totally different approach, different revenue, and that makes the whole ecosystem more resilient, because it means multiple business models here can basically fail for various reasons, and email can continue to exist, or the messaging platform in question can continue to exist independent. It doesn't have a single point of failure as far as the business model or the revenue goes. Now, as far as getting started quickly, there's some graphs here based on research that I've done into the use of open source mail clients and the geographic distribution of where mail servers are hosted. And the graphs in the middle are the ones I want you to pay attention to. So the vast majority, depending on which data set we're looking at, I've got 2 independent data sets here. The vast majority of mail servers worldwide are running open source mail transfer agents. So this is the software that actually sends the mail, basically. Most of these are running either software called Exim or Postfix. Both are old, very well established, open source. But we can see like 71%, between 71% and 96% of all mail servers in the wild that are reachable on port 25, they're running open source mail transfer agent software, which is pretty freaking incredible when you think about it, right? And this software is obviously free, it's enterprise grade, it's well documented, it's been around a long time, there's 10,000 configuration options, or maybe more like 1,000 configuration options. And long story short, it's pretty easy to get started hosting your own, I mean, relatively easy in the world of other kind of businesses you might want to get into. You can just take software off the shelf, put it on a mail server, scale it horizontally, and provide a service, right? I mean, that's pretty great. The tech is free. Lots of other people have done it. So this speaks to the ease of entering the market of being an email service provider. You can get this technology off the shelf, and most companies are already doing that with open source software. So we have achieved the magic formula for email, right? This is a large part of the explanation of why email is dominant today, why it's been so difficult to dethrone it, and why I don't expect it to go anywhere anytime soon. However, there is this thing called centralization, and it's a reality. It's a reality for a lot of things that we took for granted being decentralized in the past. And that's what these tables speak to. So here we can see the market share in Europe and the United States for mail clients. So it's really important to say these are clients rather than mail servers. But if you think about it, you can see there's a close association between the two. And although iPhone is number 1 as a mail client, Gmail being number 2 is an indicator of the number of people that are actually using Gmail, because most people who use Gmail are not using it with some third-party mail server. They're using it with Gmail's own mail servers, whereas most people who are using Apple Mail Client, they're actually using a third-party mail server with that. So Gmail is the one that really jumps out here. And before Gmail, there was no company that had more than 25% market share of email as a service provider, as an email hosting company, which is concerning, and it's a significant change. The success of the gratis plans like Hotmail, which was bought by Microsoft specifically to get control of that large user base back in the 90s, and also of Gmail being for free, and also if we look in Russia, Mail.ru and Yandex and ones like that, that's what drove the success of the centralization of these models, unfortunately. And it's actually really interesting, because if we think about what Gmail wants to get out of, what Google wants to get out of Gmail, yeah, like they haven't had much success actually with messaging. They kind of, they really, I mean, Gmail is their golden platform as far as messaging goes, and that's also because all these other projects didn't do what they were supposed to do. So some of these you're probably more familiar with others, like obviously Google Wave, Google Hangouts, Google Plus, Google Talk, Google Allo, then maybe some that you might be less familiar with. The bottom half of the list is companies that Google bought and either tried to run or shut down pretty quickly. So Pi, Orkut, Sparrow, Jakku, etc. None of these dominated in the way that Google was. I mean, look at the scale that Google operates at, right? I mean, these there's actually a list of around 160 projects which Google's cancelled on killedbygoogle.com, which is an interesting read. But when you look at the messengers alone, this is quite some money that they've spent, which hasn't really gone anywhere. And when we compare Google's position to like their biggest competitors in the messaging space, we see that they don't have anything to answer to WhatsApp or to Facebook Messenger, actually, which is really interesting, or to TikTok or some of the others in the Asian region. So they're really counting on Gmail. They're trying to take a different approach with rich communication services by basically moving one level up the technology stack and getting other third-party developers to implement Google's messaging system for them. But as far as I can see until now, the uptake has been pretty small. So that's an interesting to watch to see whether it pans out. But yeah, I mean, considering Google's position and considering they own the world's most popular smartphone OS, it's kind of interesting they don't have a messaging app that anybody uses, basically. So Gmail's really important for them strategically in this space. And understandably, they've been working to expand their position and their control of email as a medium. They might not frame it that way, but that's certainly how it looks to those of us in the open source space. So when we look at what some of the effects of email being centralized are and some of the risks to us as users, we see that we lack basic support for a bunch of stuff. Like those of us who've done web development in the past, we're familiar with the pain of having to support Internet Explorer. Anyone who's had to support like email design or done email development will know that Outlook tends to fill the same space still. So great, yay that we've got rid of Internet Explorer 6. It's something we have to support, but oh no, we still have to support Outlook for our email designs, which really sucks pretty bad. And we're still lacking support for really basic things. I mean, most CSS3 features or even linked files are not supported by either Outlook or Gmail at the moment. JavaScript, SVG, HTML Canvas. I mean, some of you will probably think, actually, you're really happy that there's no JavaScript and SVG in your emails. But once you start receiving more engaging, more dynamic content, which is more responsive, more pixel perfect, which basically uses open standards which work well across devices and platforms and resolutions, then you probably will be grateful for things like HTML Canvas in your email inbox. But it's very hard to get around these big players which have centralized control over such a large percentage of email inboxes when you want to push technology forward in the email space. And not only is it affecting the user-facing features and things like what content we can send each other within mail, but also it makes email much more vulnerable to being blocked in a way that it was designed to be resilient to in the first place. Like we saw how by default it uses DNS, it's resilient, it's distributed. But when so many people are using Gmail, for example, All you have to do is block specific IPs or specific domains, and all of a sudden Gmail goes down for people who need to use it and rely on it. So in 2012, Iran blocked Gmail. 2014, China blocked all Gmail traffic. 2018, Russia did, and I'm sure in future we will see Gmail being blocked again, which is something that just isn't really possible, at least not with the same ease and with the same approach if you're using email among a variety of hosts, domains, and mail servers as it used to be. Now, additionally, Gmail has benefited from the openness of SMTP and IMAP as standards, like the fact that they can just support these protocols and they can welcome with open arms lots of these users. Basically, they benefit from the low market entry barriers that I mentioned before. Like, it's been easy for them to become an email service provider. But actually now they say they're going to drop support for IMAP effectively in 2020 because their reasoning is that basically using Gmail logins directly is insecure. So anywhere that you can't use OAuth for your Google credentials, they're going to drop support for, and that includes IMAP, which means that although they've been able to harvest a good chunk of the global user base of email by saying, hey, you can use your own mail server, you can use your own existing domain aliases and what have you. We support IMAP. It's kind of a transparent system that they're providing. Now that they've reached a certain critical mass, it looks like they're actually cutting off. So they've used IMAP to benefit them, to increase their market share, and now that they've got it, it looks like they're going to shut it off once again. So it's going to be interesting to see if they go ahead with this, but this is what they've announced they're going to do, shutting off support for direct IMAP login. And additionally, they're trying to address some of these issues with a lack of support for more dynamic email content. But in typical Google fashion, dare I say, or maybe let me rephrase that, they have a history of doing it in this way. They're not doing it through an existing standards body. They've basically launched something that's proprietary, and then they've said, oh, whoops, people care about governance, let's pretend we have some governance. And that's what they're in the process of doing right now. They just introduced recently a technical steering committee for accelerated mobile pages, which basically includes 5 of their friends. And this is a great leap forward in terms of, so for those who aren't familiar with accelerated mobile pages for email, it's a subset of HTML, which is proprietary, which allows you to have more dynamic content within your emails, more interactive content, but it's controlled by Google. And as I say, it's a proprietary standard. And in order to even use accelerated mobile pages for email, you have to register with Google. You have to have a track record of sending the kind of content that they like. You have to have been sending to Gmail and meet some other criteria, which doesn't look very independent to me. So as far as the centralization perspective goes, they certainly are making some strong moves. And the effects of the centralization on the economic model that has allowed email to grow and remain competitive as an ecosystem is that we lose a lot of those business models, those revenue streams, which we talked about earlier. So the ones which remain viable primarily are indirect advertising revenue, ecosystem lock-in, and as a cost center, which cuts out a lot of those other smaller email providers. If you're wondering how Gmail centralizing email threatens Collab and Proton Mail, well, because Gmail makes it consistently more difficult to get mail delivered, right? You have to jump through more hoops. You have to play by their rules. You have to basically second guess what their policies are and how they're changing, register with Gmail, and make sure you have IPs that they like and so on. So they make it more and more difficult to actually get delivered, and they can dictate what it takes to get an email delivered. It's no longer the flat playing field that it used to be. Not all mail servers are going to be equal. Domains have reputations, IPs have reputation with Gmail that they don't have elsewhere. And if they want to block your traffic or permanently put it in a folder which someone's never going to read, there is really not much you can do about it. So it threatens the business models, unfortunately. However, email does remain alive and well, and there are some interesting innovations that I would like to share with you. The spirit is certainly not dead. There are some exciting things for developers like MGML, which is another approach to making email content easier to produce. This actually came out of a European startup, Mailjet, and it's a bit like jQuery was for HTML and JavaScript back in, I don't know, the early 2000s, and that it's basically a simple way to generate content which is compliant with all mail clients, so you can write once and generate content which will adapt, so it's an abstraction layer. Mailvelope, probably you're familiar with, makes OpenPGP encryption easy as a webmail solution. Chat over IMAP. So this relates also to Delta Chat. Hands up anyone who's using Delta Chat. I see 4. That's 5. Nice, nice. Awesome. So for those of you who don't know, Delta Chat is basically an attempt to implement a WhatsApp-like chat interface on top of IMAP, leveraging the benefit of these 3.8 billion users and all the architecture that's there to provide a kind of chat experience that people expect from modern chat applications without having to rely on proprietary tech stack. And chat over IMAP. Chat over IMAP is the other one I was referring to and promised to tell you at the end. That is being developed by Open Exchange, pretty well-funded organization. They have some nice videos and website. Delta Chat is, these are both open source, by the way. Delta Chat is already in the App Store. You can try it out. I recommend you do. Give it a go. I think it's beta status. Chat over IMAP is in development still, but they're investing pretty heavily in it. JMAP is another cool development that actually just got standardized this summer. It's aiming to be a replacement for IMAP over JSON. So it's solving some of the issues that people see with IMAP and making it more performant for mobile platforms, and yeah, solving a lot of issues that they see. And I think it's a really nice project. Wild Duck is it's a new like technology stack written from scratch over the last 2 years. It's kind of a replacement for those older systems like Dove postfix combinations. It uses Node. Uses other technology as well, but it's an example of something that's actually really hard to do, which is write a new piece of enterprise-grade infrastructure like from scratch. Like it's a new player in the field. It's a new modern player, and at that level of infrastructure, that's really significant, and we need more of that. It shows that there's still enough demand and investment in the ecosystem for that kind of thing to happen. Superhuman, some of you may know, it's beloved of CTOs and CEOs. It's an email automation system. It's proprietary, got a lot of buzz. People swear by it. People are prepared to pay, I think, $20 a month or so to have this service sort their email for them, automatically generate reminders, and so on. This is innovation on the user-facing side. JuicyMail is a new mail client, I think 2019. Also, BlueMail is another new mail client. They're both proprietary, but still, there's people who are investing in these mail clients on different platforms, proving that the business model is still working for them, or at least they expect it to. AMP email is problematic in the way that I've said, but it is also an innovation. It is centralizing, but it is also changing what you can do with email. So, you know, it's a complex relationship I have with that. And then Zapier is also really interesting. So those of you who may have used Zapier in other places, Zapier actually does allow you to do a lot with email. Growth hackers, chief marketing officers, they love automating their mail workflows with Zapier. You can automatically detect content, put it into this system, like put it into your CRM, extract leads or inquiries, like anytime somebody messages you on LinkedIn InMail and you get an email notification, you can set a trigger that will mean that messages you on Slack or various other things quite easily using Zapier without doing any coding. So that fits in nicely to the email ecosystem as well. And finally, there's this project called Lightmeter, which I personally am working on. What we're aiming to do with Lightmeter is make running a mail server easy again by automating and monitoring what your mail server is doing. We're starting out by supporting postfix, and secondarily it will be XIM mail servers. Yesterday, one of the tweets from the attendees here at CCC said that they wouldn't wish maintaining a mail server on their worst enemy in response to one of my tweets. That's kind of the problem that I'm aiming to solve with this and with our project. It's open source forever. It gives you a dashboard, what's going on with your mail server, and should make it as easy to deploy a mail server and operate it as if you had no experience running postfix at all. So this is my contribution and my next project in this space. So that's actually it from me. I tried to cover both the past, the present, and future directions for email. And if you want to find me, I'm there on the left. If you want to follow what we're doing with Lightmeter, the contact details are there. The first Hello World tweet went out today. Thank you. No time? No? Okay. So I'll take questions off stage. Thanks.
Yeah, sorry, we are past time to let our volunteers go live their lives. So Sam will go ahead and take questions off stage. I'm sure you are going to swarm him. A very charismatic, handsome guy. You have to see him up close. If you haven't gotten the real deal. So he's going to be over here. This is it for us for today, guys. Day 3, a great success. Thank you all, audience, for coming in and out, watching the talks. I want to give a great thank you to our volunteers, sound, video, the assemblies back there, all the speakers and the workshop runners. You guys make this, you guys make this cluster what it is. Sorry, I'm getting all choked up. Not for reasons because I appreciate what they're doing, but because there's something in my throat. So I would like to let's give Sam one last big round of applause. Let's give our volunteers a round of applause. That's it for us. We will be back tomorrow with more content. Go to decentral.community to see our schedule. We have more workshops. We have more talks, and then C3 is over. It just begun, but it's already almost over. So be free. Fly away, my little butterflies.